And it's important to point out that in these areas, there's very limited access to early warning systems. I mean, we have the heat wave in the northwest of the US was predicted by ECMWF quite reliably a while ago with some lead time. So there is a bit of time to prepare in the developed world, but in some of the global south, these systems don't exist at all. So we want to talk today a bit about early warning systems. And some of this was really triggered after some of these events where the UN Secretary General Guterres really mandated the community to come up with warning systems. And there has been a lot of activities in these areas, and a lot of this will continue. And in the future, I think initiatives like EVE or so really want to play a major role in there. And the question is how to combine all different approaches to this, physical models, AI, and other bits. But coming now to an event like flooding in Nigeria, how do you make a reliable forecast? If you look at many sort of traditional sort of climate models in particular, they wouldn't have the skill in these areas at all to do that. But we're just in a phase now where, okay, the movie doesn't work in my presentation. We'll see. So this movie won't work, but this is a very nice movie, I can tell you. But we're in a phase now where we can run global kilometer scale models, and we can resolve features that drive some of these flood events like convection and organized convective systems that we couldn't previously resolve. So what you see in this wonderful movie is highly resolved organized cloud features, mesoscale convective systems, really going by exactly this area where these flood events happen. And this is really, will be a transformative way to look at some of these events and provide early warning systems that we currently don't have. Where's the AI coming in? These models that I showed in the background, there at the moment you can run them for maybe 10 years or maybe 1 year at the moment at a kilometer scale on the biggest computers we have in the world. So these models don't scale just yet for climate bits. There's a lot of development in surrogate models, fast models, that the hope is to speed up some of these models. Can we trust them? These are good questions. So we'll have to do a lot of work on physical constraints. But I think it's a really exciting time. We have this advancement of physical models, and you have surrogate models, AI coming in. And we have to, as a community, make sense of this and see how we bring it together in the future. But these are just models, and you can think of in the future, we can see in the forecasting system and early warning system, we probably really have a big hierarchy of different models, but also we have to think quite hard how we bring in the observations. So global kilometer scale models look cool, they make good movies, but it's still a far too coarse scale to resolve key features. So we will still have to have a hierarchy of ultra high resolution models, DNS and other bits. We'll have to combine them with these high resolution models, but these models, at least the physical models, don't scale to long-term climate simulations either. So we have to work out how to bring this all together then also with the Earth observations in a meaningful way. And I hope some of the discussions we have today help us with this. So what are we doing here? First of all, we want to showcase some of the developments that are out there that really make this interesting for AI in the climate space. We want to discuss the role in future forecasting and warning system. And we want to facilitate discussions between different sectors. So I hope there's a mix of people here, not just from academia. I know there's a few people from industry here, but it's really the idea is to bring these together and to learn from each other, talk to each other, and develop new collaborations. The workshop is unfortunately too big to do individual introductions, which I'd love to hear where you're all from. So we won't do this. But we will have plenty of time for discussions after each talk. So each speaker should have about 10 minutes left at each talk. And please, if you ask a question, I think you have to press the microphone button here. So it's very professional here. Press the microphone button. Please say who you are and your affiliation. It's really nice to get a sense of who's speaking. And there is also Reinhard, who just got here, one of the other. Marcus, thank you, Marcus. I'm very happy. Yeah, you're not Reinhard. The last convener who just made it from the airport, and I think we're ready to kick off. We have a really nice program, which will keep us quite busy, but we have hopefully enough time of discussions in the breaks after the talks. So our first talk today is on AI for weather forecasting. It's from Marina Clare from ECMWF, and I'll hand over to you.
Well, thank you very much for the introduction, Philip. So as Philip said, so my name's Mariana Claire and I work at ECMWF. So for those of you who don't know what ECMWF means, we're the European Centre for Medium Range Weather Forecasts. And today I want to talk to you about AI for weather forecasting and extreme events and things like that. And so obviously I didn't make these slides alone, so I'd like to thank the names that you see on the screen here and many others who have contributed. And feel free to ask questions. I think there's lots of opportunity for discussion, but if you have any follow-up questions or if you want to get in contact, my email's on the screen there. It's quite easy to find online as well, but feel free to email me and yeah, let's start some discussions. So I just wanted to start off by giving sort of a brief overview of what we try and do in weather forecasting and what we try and do at ECMWF. The main aim really is to try and predict the future weather using the current state. And so every day we absorb 800 million observations from all over the planet into our model. And obviously we don't use all of these, so we have to sort of triage which ones we want to use and how we want to use them. But what we're trying to forecast is things like snow cover, precipitation, the temperature, the wind speeds, all those things that you see when you open your favorite weather app and you see, you know, the little icon with the clouds. That's all the things that we're trying to predict in our weather forecast. So how do we do it? Well, at ECMWF, we take a global approach, which we call the Earth system approach. And so we're trying to forecast all of these different processes and to predict how they occur. And so you've got things like the coupling between the sea and the atmosphere, the sea and the ice, the evaporation, the precipitation. And so these are all very, very complex processes. And you may, just by looking at this slide, you may realize that a lot of them are interlinked. So there's a lot that have, when we predict one process, that has an impact on a different process. So it's a very, very complex problem to try and solve all of these processes to end up with a single forecast. So that was a sort of very high level overview. So this is actually what we do in a numerical weather prediction center. So, and I should say that all current weather centers at the moment are using numerical weather prediction models. So Météo Suisse, Météo France, the UK Met Office, everybody is doing these numerical weather predictions. So this is very much what is happening at the moment. So we start with the observations, like I mentioned. So these observations can be coming from all sorts of sources. So from planes, from boats, from radiosondes, which is when we sort of launch something into the atmosphere to try and measure certain quantities. So there's a huge variety of different sources. And obviously they're not on some like nice little grid, which we can use to simulate our forecast. So the second step is something that Philip just mentioned. So data assimilation. And so basically what we want to do is we want to try and take all of these observations and get a best guess of what the current state of the atmosphere and ocean is. And so we do that using quite a complex numerical model, and we feed in the observations. And actually, this takes about 50% of the time that we need to compute the forecast. Then I promise these are the only equations in my talk, but once we have these, our best guess of the atmosphere, this is like the initial condition that we try and use. And then we're basically trying to solve these equations on the screen with some more complexities. And actually, we don't actually even know if these equations have a solution. And currently, if you can prove that there is a solution or there isn't a solution, you can currently win $1 million because it's one of the Clay Millennium Prizes. So, you know, maybe we can do that in the lunch break and win ourselves a prize. And then finally, so when we get, so you might have seen from these equations that, you know, these are things that we don't, like the general public isn't going to understand if I just tell you, the pressure or the velocity. You want it to be interpreted in a way that when you see the app, you say, okay, this is this icon, this temperature, this is what I need to understand. And so that's what we call post-processing and dissemination. And so that's the final step of the sort of numerical weather prediction process that most weather centers will do. So this is the 4 stages. And actually the machine learning, what machine learning is currently targeting, or most machine learning models, is actually just the 3rd step, the red box. So they're just trying to emulate the forecast model. So those equations. But I mean, I say just, I mean, that's still a huge task. But just so that you're aware, there are other processes that need to be considered. So let's get on to the machine learning, which I guess is a sort of a common interest for everybody in this room. So why is machine learning well suited for weather prediction? Well, as I'm sure you know from your experiences of looking at a forecast, often we will say that the temperature tomorrow should be 25 and then it's 20 and then you're upset because we've got the forecast wrong. So weather predictions are difficult. And why are they difficult? Well, it's a chaotic system. And as I mentioned before, all of the components are non-trivially connected. So if you get one component wrong, that's going to have an impact on your other components. Also, we simply just don't understand some of the processes. It's a science. It's still evolving. We're still finding out things. And then the final thing, which is something Philip touched on, is these resolution limitations. So if you imagine our current operational model runs at a 9-kilometer grid. So that means we've got a 9 by 9 kilometers. And if you want to simulate clouds, let's say on that grid, well, those clouds are not going to appear in your grid. So you have to start making approximations. And that's what we call parameterizations in the model. And so that means that we're making estimates. And so we're unable to actually properly, even if we knew the physics perfectly, to represent all of the model processes in that grid. So where can AI come in? Well, actually, there are a huge number of observations, and there's a huge number of a huge amount of data from the weather forecasting systems, and that's perfect for training a machine learning model. So I think this is why this sort of problem is becoming increasingly attractive to tech companies who want to explore what they can do with their machine learning methods. And also because, like all of you in this room, people are interested in extreme events and climate change and how they can improve our knowledge and improve our forecasting systems. So as I just mentioned, what the headlines are saying, I mean, as with everything in AI, it's all a big buzz topic at the moment. So there are lots, if you open a newspaper, there are lots of headlines about machine learning, improving weather and climate models, IBM, NASA, everybody collaborating with each other. So there's a lot of buzz, as with everything in machine learning at the moment, I would say. What I would also say is it's a very, very fast and evolving landscape. So the first paper which tried to show how we could do machine learning for weather forecasting was published in 2018 by Peter Bauer and Peter Dubin, both at ECMWF. And since then, the landscape has evolved very, very quickly. In particular, last year, we saw some huge improvements, starting with Ryan Keisler's paper, which used a graph neural network at a 1 degree resolution. So 1 degree is about 110 kilometer grid. So still much coarser than anything that we would do operationally. And then a big step again was NVIDIA's ForecastNet, which did a 0.25 degree grid. And I'll explain why all of these models basically from then on are using 0.25 degrees. I'll explain that on the next slide. But 0.25, depending on where you are on the globe, that's about 30 by 30 kilometers. And then we have Pangu, which is another model that I'm going to sort of mention more in this talk. And Pangu claimed that they have more accurate tropical cyclone tracks than our operational model. And it keeps on going. DeepMind, GraphCast, that was another big step because they showed that they were beating in certain metrics. They were beating our ECMWF's operational model. And this slide literally gets updated every couple of weeks because you'll see that, there's stuff from June 2023 here. I think in the, next couple of weeks, we'll do another update. So there's Alibaba's Swin RDM looks very promising. NVIDIA came out with another improvement on ForecastNet, which they call SFNO. So it's really, really fast evolving. And it's honestly quite difficult to keep pace sometimes. So I mentioned this 0.25 degree thing. This is because almost all of these machine learning models are trained on ERA 5 reanalysis dataset. And this ERA 5 is something that is produced at ECMWF by C3S. And the aim of this dataset, so I should say this dataset, the intention of this dataset was not for machine learning. This is a dataset that we use on a regular basis to explore things about, how the climate's evolving, weather impacts, and so on and so forth. And reanalysis is basically very similar to what I was talking about with before with the analysis, the data assimilation. So reanalysis dataset, we take past observations and we take a very complex numerical weather model and we try and fill in all of the gaps to get our best estimate of what the weather looked like in the past. And so now ERA 5 goes all the way back to 1940. And I think that there will still be progress we're still going further and further back, although obviously as we go further and further back, the observations become less good. So the reanalysis will also become less good. And so this is why it's very attractive for machine learning models, because you have this huge data set on which they can train, but they are limited because ERA 5 is 0.25 degree resolution, so it's 30 by 30 kilometers. And so that's why all of these models are at 0.25. And I should make a little advert. So ERA 6 is coming in 2026, I think, I'm just checking the slides. And ERA 6 will be at a finer resolution. So I imagine that there'll be another big step when the machine learning models get to train on ERA 6 rather than on ERA 5. So I'd like to focus on two models here in this talk. So the first one is ForecastNet by NVIDIA. And the reason I'm focusing on it is because it's fully open source. So you can go on GitHub and you can just take their weights. They've saved the weights of the neural network and they've got their architecture, and you can just run it yourself. And so that's what we're doing at ECMWF. We've just taken that model and we're using it to conduct experiments for evaluation. And so ForecastNet is an adaptive Fourier transform operator, for a neural operator with a sort of transformer architecture. And this is particularly attractive for us in the weather community, because when we solve our physical model, we actually use Fourier transforms as well. And so this was very attractive when this came out, because people thought, oh, well, they're doing exactly what we're doing, and we can sort of relate to this. So this is ForecastNet. The other one, similarly, is open for non-commercial use, is Pangu Weather. And so again, we're currently running it at ECMWF to conduct experiments to see how it evaluates compared to our operational numerical models. And it's a transformer architecture, so it doesn't have the Fourier transform nature, but it's got an encoder decoder inside. And I put the links to both of the papers, but also if you just Google it, you can find these papers pretty quickly. So I said we're conducting it for evaluation. So let's have a look at some of the results. So there is definitely an undeniable skill. So for those of you who know about whether this is the anomaly correlation for two variables, geopotential in the upper atmosphere and wind closer to the surface. For those of you who don't know, this is why I've got the smiley and unhappy face. So basically what we would want, what shows skill, is if the higher the score, the better the skill, and the lower the score, the worse the skill. And along the x-axis, you can see what you see as the forecast day. So this means, at forecast day 5, let's say, this means that this was the accuracy in the forecast when I was trying to make a forecast 5 days ahead. Then forecast day 10 that's the accuracy in the forecast 10 days ahead. So you can see that obviously the accuracy decreases the further forwards in time you're trying to predict the weather. And what you can see on this graph is for these metrics, Pangu is beating our ECMWF operational high resolution model. So there is definitely an undeniable skill in these neural network models. I should state that evaluating surface parameters specifically against observations demonstrates that ECMWF's model still has better skill than Pangu and ForecastNet, but they're still doing a very, very good job. So we wanted to look at extreme events specifically, and sort of thinking about climate change and extreme events. And one of the criticisms that people have of or one of the worries, I should say, that people have of these neural network models is, well, can they predict extreme events that they haven't seen? Or something that's sort of slightly out of their distribution. So this is an example with Storm Eunice, which hit sort of the UK and Northwest France in February of last year. So this is well outside of Pangu's and ForecastNet's test data set. And so this is something that we ran ourselves. And the top left is the analysis. So that's the best approximation of the weather. That's what we think is our best estimate of what actually happened. The top right is the ECMWF operational forecast, and then the bottom plots are Pangu and ForecastNet. And so what you can see is that both Pangu and ForecastNet accurately forecast that there was going to be a storm. They've got the shape roughly right, and they've got the intensity roughly right as well. There is definitely more features in the high res than there is in the machine learning models, but that's partly because the high res is being run at a 9-kilometer resolution, and Pangu and ForecastNet are trained on this 30-kilometer resolution model. So it's also sort of not unexpected that we've got more features in the HRES. What we have on the right is what we call a forecast verification diagram. So this is for the maximum mean wind observed in Heathrow on the 18th of February. And basically the idea is we want to look at how the forecast varies for a specific day up until, and we compare that with the actual observation of what happened. So that's the green dot in the top right-hand side. I don't know if you can see it. I don't have a pointer, so I can't show you, but yeah, if you can see the green dot. And so in the blue boxes was something that I haven't mentioned yet, which is that we don't actually, at ECMWF, we don't run just one forecast. We run an ensemble of forecasts to try and capture the uncertainty in our forecast. So that means we sort of perturb the initial conditions in the model because, you know, especially for extreme events, it's very important to understand the uncertainty and the risk. But what I wanted you to notice, so before it's sort of like between the 3rd of February and the 10th of February, it's sort of like predicting higher than normal wind speeds, but not doing, you know, it doesn't look like there's going to be an extreme event. And then on the 11th, 12th of February, suddenly all the models, so Pangu, which is in cyan, ForecastNet, which is in magenta, the high res, which is in red, and the blue boxes, which are the ensemble, they start all predicting higher wind speeds. And so that continues up until the day of the event. And so in the end, Pangu and ForecastNet have a slight under prediction of the wind speed relative to both our high res and actually what happened. But really, it's very, very impressive. It's, you know, it's really not that far off the high res forecast. And in fact, it's basically sitting inside the ensemble. So that's sort of definitely within the bounds of what we might expect from a model. And so this is certainly a nice illustration that these machine learning models can indeed capture some extreme events. The other example I want to show you of an extreme event is a tropical cyclone called Tropical Cyclone Freddy, which occurred in February of this year. And so particularly we're looking at tropical cyclones because they're interesting events and they're important, and we would like to be able to simulate them better because they have such a huge impact on people's lives when they hit. But also Pangu made the claim in their paper that they were really good at modeling tropical cyclones. So we wanted to have a look at you know, does that claim hold out? So on the left, what you see is the analysis. So again, as I keep on saying, it's our best guess of the truth. Our best approximation of the truth. On the top left, you have the high res. And here we've also shown the ERA 5. So that's what Pangu and ForecastNet are trained on. So we know that for tropical cyclones, if you have a coarser resolution model, you shouldn't be able to capture the intensities as well as you can with a higher resolution model. And so you can see that with, if you compare just for the moment, ERA 5 and high res, you can see that ERA 5 has a lower intensity than the high res. Having said that, definitely ERA 5 and high res are better than Pangu and ForecastNet. So Pangu has got the tropical cyclone in the right place, roughly. ForecastNet hasn't. ForecastNet has sort of missed where the cyclone should be. And both Pangu and ForecastNet have got a much lower intensity than actually what happened. So this is just one example, but it's something that we're actively investigating at the moment at ECMWF. And we found that, yeah, Pangu is doing an okay job with tracks, but intensity maybe not so much. So, you know, it can do, these machine learning models can do well for some extreme events and can do not doing so well for other extreme events, but it's still, you know, it's still impressive and it's still very much work in progress, I'm sure. And the big advantage, which has already been mentioned in using these machine learning models, is a potential gain in time and energy. So all of these machine learning models are relying on ERA 5, and ERA 5 has a huge cost, so that's the nice elephant. So let's say 15 billion units. But I should very much emphasize ERA 5 is not being run for machine learning models. We will run ERA 5 irrespective of whether machine learning models are going to be trained on them. So it's not really fair to add that as the cost to the machine learning model, but there it is anyway. The high-res model in comparison for a forecast takes 180,000 units. But Pangu, to run Pangu on our systems, it takes 0.3 units. And in fact, the biggest part of Pangu is it takes longer to save the data than it does to actually run the model. So now we're thinking, oh, well, maybe we shouldn't be saving the data. So it really is a huge improvement in time and therefore in computational energy and computational cost. You know, you could run Pangu on your phone. if you had the input data. Whereas there's no way you could run the high res on your phone. In fact, we have one of the biggest supercomputers in Europe specifically to run our forecast. So there are key challenges for machine learning models. So I mentioned before that they don't train on observations. So far they're only emulating the forecast. But incorporating this data assimilation step takes about 50% of our forecast computational time. So this is definitely a big thing that machine learning models could help with. And that you know, I'm sure people are starting to think, okay, how can we go directly from observations to forecasts? The other thing is the uncertainty. So as I mentioned, uncertainty is particularly important for extreme events, but it's also important for you know, everyday forecasts as well. So at the moment, we get the uncertainty using something like this plot here. We perturb the initial conditions and we perturb the model, and we run the model multiple times. So that's our ensemble. So machine learning model could take, you know, perturbed initial conditions. That would be fine. That's easy. But we're still sort of investigating, okay, how would you perturb the model itself in order to capture the model uncertainty as well? So that's very much an area of investigation. And then finally, and I think maybe the most important thing is how do we build trust in machine learning models? Because as I mentioned, there's a worry that they're not learning the physics. And so therefore, if you have climate change and the underlying sort of distributions change, or you have some extreme event that really is just, you know, never been seen before, how is a machine learning model going to cope with it? And I think part of these evaluations, like I've just shown you, those are really useful for showing how machine learning can help. For showing that machine learning is learning the physics or is not just learning some sort of statistics. But there's still a lot of work to be done, and rightfully so. These weather models are very, very important and important decisions about people's lives and you know, assets are made based on these models. So we should be focusing on how we can build trust. So finally, I want to end with a little bit talking about what I do, or rather the project that I'm involved in, which is called Destination Earth, or Destiny, which some of you may have heard of, and how we can incorporate machine learning into Destiny. So for those of you who don't know, Destiny is currently one of the European Commission's flagship projects, and we have two digital twins. The first one is called the Weather-Induced Extremes Twin, and it's run at ECMWF with some partners as well. And the point of the Weather-Induced Extremes Twin is for real-time decision-making, impact response and risk assessment from extreme events. And then we also have the Climate Adaptation Twin, which is trying to improve understanding of impacts of climate change from global to local and regional scales. And both of these models are the point is that we're going to run them or we are running them at kilometer scales. So very, very fine resolution. And so that's, you know, one of the ways that we can start capturing more of the local scale impact. So there's lots of potential machine learning applications within Destiny. And I should emphasize that the two twins are very different. So one twin is weather and one twin is climate. So not all of these machine learning applications can be applied in the same way to both of the twins. But one of the things that we want to do is to try and add uncertainty information. So as I mentioned, both of the twins have run at very, very fine kilometer scale. And so it's at the moment, at least, not affordable to run more than a single forecast. So we can't get this ensemble, which is what we're used to doing. And so we're starting to think of how machine learning could help us with that. So we could have machine learning emulators to generate ensembles, or we could try and use some sort of probabilistic neural network setup to generate distributions. And so this is what I'm working on. And there's also a tender within Destination Earth at the moment where people are applying with ideas of how they can do this. And I think in this case, it's very much for both of the twins, although obviously it's easier to build a weather emulator than a climate emulator. Now, the other thing that we think that machine learning has, could have a real impact in Destination Earth is for downscaling for both spatial and temporal resolution. And so even though we're at kilometer scale with these machine learning, with the digital twins, there's still some processes that that need even higher resolution. So if you imagine like a wind farm, you want to know what the wind speeds are at specific wind turbines, for example. And so that's something that could be achieved by downscaling with GANs and diffusion. GANs or diffusion models. And here we make a distinction again between the climate twin. So the climate twin, if we were trying to downscale, we'd probably have to run very high resolution forecasts and try and downscale towards them. In the case of the weather twin, we can downscale towards observations, for example. And then finally, this is something that's applicable for both of the twins, which is something we're starting to think about, is the point of these digital twins, and something that the European Commission really wants, is that they're accessible and easy to use by everyone, for everyone. And so we're starting to think, okay, so how could like a ChatGPT type model or a language model be used to interact with the twins? And this could be really helpful for your everyday user. And then finally, Destination Earth could also help machine learning, because it's going to provide kilometer scale forecasts on which we can train the machine learning models. So it's not a one-way system, right? There's always, we need to think about the synergies between machine learning and these new numerical models that we have. So with that, I'd like to conclude. And so, say machine learning models are showing great promise, definitely, and even show that they can do a reasonable job for some extreme events. There are still challenges to overcome, but it's a very fast evolving landscape. And it might be that one of you is already writing the paper, which is going to blow everything that I just said out of the water. And actually tropical cyclones are going to be great, and everything's going to be wonderful. So yeah, so thank you very much for listening. And I'd like to open the floor to questions.
Thank you very much. Really nice talk. We have time for questions, and I'll just open up. Yes, please. Help yourself to water. Yes, please, in the back. Just press the microphone button.
Okay. Hello. Wait. Hello. Wait.
Yeah.
Thank you very much for your impressive presentation. And I'm from WMO, and now I'm supporting the AI activities in WMO. And also, I have one question for your presentation. The first one is that you showed the machine learning model and the forecast net, and also the Pangu weather model.
Yeah.
So you are, according to your presentation, the two models are real-time running in ECMWF. So you compare the performance between them and the ECMWF's high resolution model. So do you have, does ECMWF have has any plan to run their own developed machine learning model? Thank you.
Yeah, so we're running them. So I should emphasize, we're not running it operationally. We're not producing forecasts with Pangu. Well, we are, but not for the end user. It's really for our purposes to evaluate at the moment with Pangu and ForecastNet. But we are also developing our own operational model, operational machine learning model. So this got announced a week and a half ago, I think. ECMWF operates with a council of all these member states, of all the flags that you can see at the bottom. And we got funding from council to develop our own neural network model. So that's sort of breaking news from about a week and a half ago. So we will be, developing our own model as well.
All right, is this working? Okay, thank you, awesome talk. I am Anu Mind, I'm from MIT Lincoln Laboratory, where we design and prototype technologies, including novel sensors for various applications. So earlier in your talk, you showed various complex models in the atmosphere, undersea, et cetera. Can you talk a bit about where are the biggest gaps in the observations that could make an impact on the performance of machine learning models? And also, when we talk about predictions and mitigations, I'm interested in learning the state of the art in predicting the impact of mitigations using the forecast prediction models. Is that something that you're involved in? And can you talk more about it?
Yeah, so I guess, so to your first point about observations, I mean, if I showed you a plot of the observations that we feed into the model, you'd see that they're very, very dense in the Northern Hemisphere. So you see in Europe, they're very dense. We have a lot of observations. And then in the Southern Hemisphere, it becomes more of an issue. So I guess this comes to Philip's point about the global North and the global South, but also because in the South, there's oceans and we have to sort of use this, observations taken from ships that are crossing oceans and things like that. So there's definitely a weighting towards observations in the Northern Hemisphere. So yeah, that might start becoming an issue for machine learning models. we've obviously developed techniques to try and deal with those issues for the numerical model. So hopefully we can take some of these techniques and use it if we wanted to use try and do the same with a machine learning model. And your second question was about mitigation for climate. So at the moment, the climate twin is more focusing on just trying to understand the processes. So it's not in the remit at the moment to do mitigation. But obviously the point is that we're developing these sort of, well, and the idea is to develop these very high res accurate climate models. And so then they could be used to try and do mitigation in later phases. So I should say Destination Earth is in phase 1. So we've got renewal for phase 2, but we're sort of still trying to decide what phase 2 is exactly. So yeah.
I'm not entirely sure.
Thank you for the presentation. It's super interesting. I'm from South Pole. It's a climate project company. And I was interested when you said that you compared your high resolution model with Pangu forecast. You said that it was very impressive in the upper atmosphere, but the surface parameters were much better. Do you know why?
Yeah, it's interesting. So it seems to be that things like 2-meter temperature aren't so good when you look at the machine learning models, things like that. I don't know specific, I guess, so upper atmosphere variables are better behaved, and also they look better at coarser resolutions. So Pangu and ForecastNet are essentially a 0.25 degree model. And so it's not that surprising that a 9-kilometer higher resolution model can do better at the surface, but in the upper atmosphere, where everything's a bit more smooth, it's okay to use this 0.25. So I think it's maybe something to do with that, but also maybe something intrinsic in the physics that it hasn't learned. So very much still under investigation, but yeah, those would be my 2 hypotheses for now.
Thank you.
Yeah, thanks also a lot for this very nice talk. I wanted to ask a little bit more about this, your point that was also alluded before on the observations, using observations directly. And I was just wondering how serious are you really about it? Because I thought that one of the big things is basically that one can train on a very dense reanalysis of era, and observations look dense, but they are at the end not very dense, particularly if you go to high atmosphere levels and so on. So is it really, do you think, or maybe what's the time frame where you think it can be done directly from observations, and is it desirable at all?
Yeah, so I mean, the time frame, I have no idea because machine learning moves so fast. I would, if you'd asked me a couple of months ago, I would have said it's several years away. But now, I mean, the rate at which it moves, I don't know. But I think definitely from our perspective, we think that if you really want to have a proper modeling system, you need to be going straight from observations to forecasts. So it's something that we're sort of starting to look into. Whether it can be done or not is a different question, but we think it's a good avenue to explore. Because also then you're no longer limited by the resolution of your reanalysis data set, or one of the reasons they can't train on the high res, right, is because we have so many model changes. Well, they can train and people are starting to look at training, but we have all these model changes. And if you go from observations, then you no longer have those issues, or you have them, but a different set of issues, basically. So, yeah.
Great, thank you. I think we have time for one last question, and I think it's you. But as a reminder, please say your name and where you're from. It would be really nice to get some background.
Hello, everyone. My name is Sabah Al-Khaldi, engineer in energy efficiency and also a writer in energy transition atmosphere. One of the challenges you mentioned is building trust within the ecosystem. And as we know, in machine learning, there is the non-bias variance trade-off, which means higher flexibility of models are typically hard to interpret. So how can the community make the balance between explainability and accuracy in predictions, and what do you see are the next steps in this regard?
Yeah, so this is actually a conversation that I have with my colleagues all the time. So I think that we should weight explainability more importantly than error. So if we have a less accurate model, but we can actually interpret it, I think that's really important. But if you talk to some of those names that were on the slides there, they would say exactly the opposite. So I think this is still very much under discussion. My personal opinion is that So just to be clear, not ECMWF opinion, but my personal opinion is we want to be able to query the model. We want to be able to understand why it's making the decisions it's making. And so therefore, I think explainability is super important, because ultimately we're scientists and we don't just want an answer, we want to understand why. But yeah, that's still very much under discussion in the community. And I think everyone has their own thoughts.
Fantastic, great discussion. So let's thank Marianne again for a really nice talk. We have more time for more discussions and questions over coffee as well. But before we go into the next presentation, is by Pierre-Philippe Mathieu, the head of ESA Phi Lab, and he'll be talking about the role of AI for Earth observations. And I think we have your presentation already. Probably. That is looking very promising.
Good morning, everybody, and thank you very much for the invitation. I have done a kind of melting pot today because I didn't know exactly what would interest the audience. I can see that we have a lot of diversity in the audience, so I will try to give a panoramic view. And I also have neck problems, so I will have to turn my head there to know where I am. So it will be quite challenging. So the aim of this presentation is not about AI. AI is just a tool. We have to remind ourselves that we, at least in ESA, try to use it to better understand this beautiful planet and to see the change. So we will talk about the intersection of observation and AI. And because we talk a lot about Copilot these days with AI, in particular GitHub, the idea here is to have a Copilot for the Earth, because AI is the best technique to do that, to scale on big data, and also to be extremely real-time and iterative in this relationship between human and the machine and the observation. So our goal here is to bring some elements of this. You can understand it's a huge thing. So I just wanted to maybe illustrate what could be an interactive Copilot, because we have this intersection of large language model and computer vision. So we call it Gaia, just to be original. And we interact with it, asking, for example, here, and it should have been an animation. So I use, please use your imagination, which differentiated from machine. We could ask in real time questions like you do on Google, but it would process it also understanding the image in real time. So it could process the Sentinel-2 on the fly to see, for example, the land cover that you would ask about. Or it would pick up the animation or the evolution and forecast of air quality because you do a tour in Brussels, for example, and you want contextual information. So it would be able to understand exactly what to pick in the different type of layer of data. If you are, for example, in the business of disaster management, it would put together a layer of flood detection with a layer of building detection, so you could quantify vulnerability. Same with different variables. AI is very good at this, at looking at the intersection of multivariable that the human eye cannot do. And Gustav and Marcus know very well about this. If you ask question about climate change, it could pick up the data for you, put it into the context of what you find on Wikipedia, what you find in the IPCC, etc. And we can continue this kind of animation. So in ESA, our core business is in fact to launch, prepare, design, and operate the satellite mission that will provide these global observation. I don't have the time today to go through this, but we have different family of this, going from pure research mission to operational mission for weather, but also for the environment, called the Sentinels. And these missions provide continuous data on the state of the planet and what we call essential climate variables that you can see here. It was born through the need to forecast the weather. We always come there. So it started with Meteosat, and now we had already the third generation. But you have a mission like Sentinel scanning in both the optical and radar, and also mission looking at the chemistry. So we've seen today that AI is really a potential for disruption of things. So it's not incremental innovation, it's really changing the way we do things by this new learning paradigm. So could this happen also in our business? We are exploring this because the speed of change is amazing. And the key to this is really the change of paradigm where it's learning and it keeps learning. And I find this fascinating this property of transferring the learning. So you learn something on some type of data like Sentinel, and you move it to other type of data like radar. So suddenly you see a radar data into a kind of optical framework. So this is really disruptive. So what we are doing, we are transferring technology at ESA. We are not trying to invent AI. We take it from cats and dog classification. We add some layers, and we reinvent the value chain of Earth observation, where most of the time is in the data augmentation aspects, you see here. And we try to find some innovative way to create annotations like this gaming. And if you Google ESA Blackshore, you will see that we just released the data set with 20,000 animation of crowdsourcing crops, but also cultural heritage around the Mediterranean Sea. So we create data set open for the community so that they can train their data set. So I find also fascinating the time we are in, given the speed of change, like it's a popcorn moment in a sense, you never know what happens. And it's also touching space. It's computer vision for cars, but this can be applied to robots going on Mars, so autonomy of robots. I will also talk about putting this directly in space on satellite later. And the big thing that came last year is generative AI with large language model. And I'm a real believer that this will be the ultimate interface to our data, because the uptake of this is just impressive. And we have missed since decades an easy way to talk and understand the data. And I believe this new technology will enable us to do that. So we are looking at this. We are doing some tests with large language model. We try to precondition them with information. It's full of hallucination still, but there are people doing fact-checking loop into this kind of thing. So it's really an emerging field for us, but also full of legal problems. And there is another session this morning. So it's a new territory, but really disruptive. And we start looking at it not only for pure data, but also for text, so that you can put the data in this context. And the new paradigm is really foundation model for us. So while we really see the scaling of the problem by having different bots looking at different things, you could have one for forecast, one for computer vision, one for interaction with the data, and chaining them. And it seems that when you do that, you need a lot of training for each task. But the new trend is really having a big model that learn a lot of things and then tailor this big model to specific tasks. And that comes from the large language model. So there will be a kind of unification between language, data, and geospatial that would enable us to have very fast learning for specific applications. So we are looking into this. I'll come back to it. These are examples on how the machine and human interact to optimize this learning. For example, a cloud detection scheme that we are applying on the Sentinel-2 data enable us to beat the normal algorithm for cloud detection and keeps overperforming, because at each iteration you understand the edge cases that do not work and you create annotation for this specific edge problem like shadow, etc. So it's active learning. And it's work going on with Capazeta. You can check the link. And the other big application is the fusion of data. I mentioned optical and radar. And what is beautiful about it is that it's created in this space that the machine understands and we don't understand, some people call embedding. And that could become a new product for us. Also for you to start from this product to do the machine learning. So we are thinking now about how we could evolve to generate these products. And once you have this embedding, you can fill holes. You can do in painting. And we have released an open source on this called FuseTS. We can do this in the ocean as well. It's called DNEOF. It's also open source. You can Google it. And the next aspect is also the enhancement of the resolution. The name is not fully correct because it's only some patterns that you can see below the normal scale of the resolution of the satellite, but it can be captured by understanding the time series of things. And we are looking at this, and it's very dangerous field because it's easy to see good results, but they might not mean much. So we are now trying to benchmark this, and we will have an ITT on this. Then the other aspect is prediction. We heard this morning, and we are very interested in this for Destiny. So we're organizing together with ECMWF this workshop that you see here. Check the link, and it will be next year in Esrin. And it's a very popular workshop. We receive a lot of contribution. We also see what the gaming industry is doing, what the chip industry is doing, because weather forecast is now still done by these new players. And combining these aspects of statistics and forecast for application, we're able also to help people like UNICEF here with the dengue, let's say, forecast of risk. And we got an award for SDG on this. So my pet topic is, in fact, to bring AI to space. And it has been demonstrated a few years ago that you can do that with the new generation of chip, because a lot of people are afraid of radiation in space, and that hamper the use of computer. But with the new generation computer like Intel Myriad, you are in fact protected from problems of radiation. So you can deploy machine learning. So we demonstrated this with the FISAT-1. And the big vision is to have a cloud infrastructure. And that would enable the satellite to operate in real time with different machine learning, different bots for different applications. So along the orbit, you could think of having something for sea ice when you're in the polar region, something for forest, and differentiate the forest along the orbit, etc. And to re-upload the latest version, just as you do on your phone. So this is really new in terms of concept. It's reprogrammable Earth observation. It already exists in telecom, but it's not very popular yet in Earth observation. But the new space industry is looking at this. You see here the evolution from FISAT to the first node of a cloud computer in space with D-Orbit, where one of the CubeSat is a supercomputer. The next step is to connect different nodes to create the Internet of Computing. And that enables things like we call tip and cue. You have one satellite bringing some information, intelligence in real time, that tells the other satellite to do something. So the system becomes much more responsive, and you can have latency below 1 minute for things that today take a few hours. So you can imagine you create a new market with this kind of thing. You can do this also for methane. You have one satellite spotting some anomaly and the other one satellite focusing on this anomaly. We try to work with community through challenges. Check out this platform. We have 2 challenges going on programming the FISAT-2 and programming a software on the space station. Very cool stuff for cognitive computing. But we will have other challenges with street view. We had some on super resolution, etc. So this is our main tool to connect. So as a conclusion, very exciting time. A lot is happening. We cannot keep up with it. We need your help. There is also this intersection of technology coming up. We are looking a bit at quantum, a bit of blockchain, but the evolution of the web and the evolution of computing is really changing the way we interact with data. And to address this, we are releasing some ITTs. You see the list here. You can check our website, and you can also connect with me on LinkedIn or during the coffee break. But what we're after is really talents, because it's very difficult for us to find experts which are both in AI, understand the data and the physics. And Augusto has a similar problem, I suppose. It's quite challenging. So we offer also opportunity to visit us in the ESA Lab, and with some condition. We have also vacancy notice for fellowship and also co-funded fellow. And we can go into the details separately. So I thank you very much.
Thank you very much, Pierre-Philippe. That was quite a whirlwind. There was a lot of information in there, but we have plenty of time for discussions. So who wants to kick off? Yes, please.
Hi, my name is Yevhen Bershevsky, and I'm representing ACAPS. At ACAPS, we do the humanitarian analysis. So we try to compare different humanitarian crises across the globe. And I'm actually part of the project on the natural language processing, where we try to build a system to help to make it faster. So my question is about hallucinations. You just briefly mentioned that you are trying to experiment and see how big of an issue that. So maybe the question is like, based on your initial exploration, how big this issue is for the use cases that you have been experimenting with, and if there is any like best practices, some feedback that you already learned how to overcome this issue, because this is something we will be doing as well. Thank you.
I didn't fully understand everything. What's the nature of the issue? Is it
So the
technical?
question is about hallucinations and your experimentation. So you said that you are putting together like a chatbot systems, right? And you already experiment a lot, like how much of the what responses are coming are true one, or there is this problem of hallucination. So the first question is how big this problem is for your use cases. So you have you have piloted it a bit, like is it like 10% of the issue, 5% of the issue, or and this is the question A. And the question B, is there any kind of feedback that you can share that you have learned through these experimentations how to overcome this issue?
Okay, so we are at the beginning of this, and there are different level of issue. First is technical issue. How can they ingest all this information we have? And there are limits with API, etc. Second, can we have our own model that is open source? Because if we rely on models that are done by big US ICT, we might have problems. And to do that, I think it's much bigger than ESA, and it's a European question. You need a lot of money, like several $1 million to train this kind of models. Third level is which data can you ingest with this? Because there are some license issue. And where is the information going at the end? So we are really opening this. What we see is the value of it. Because we have so much data, a human cannot process this. Even documents, we have different documents on technology. So imagine a robot could actually synthesize for you the state of technology, the gaps, etc. So that would be, I think, the biggest value we can find. And then imagine this bot can also understand in real time the images and ask questions about these images. And there we are experimenting technology, and it seems to work, where we are kind of hashing the images so that they can find similarities. So you can start browsing the data, saying, I need similar images, and how long has this building been there, etc. So I would say the problem is absolutely not solved. The issue we have is scale, legal in terms of license of the data we can ingest, and sovereignty. Are we relying on tools that we cannot at the end control, or will be locked in with someone?
I mean, from the UN World Food Program, when I'm looking at your slide here, you mentioned like AI has a today technology, and when I'm looking to tomorrow, there is metaverse and blockchain. So can you maybe give more insights on those two technologies and how you aims to use it for it?
Yeah, so all these words are what my colleague called buzz, okay? But the word big data was buzz 5 years ago, and it has changed, and cloud as well, and it has changed the way we operate. So I'm a believer these things will really change the way we operate. We are looking, for example, at blockchain because blockchain introduced trust where people have no trust. And you can put digital asset with a value on the blockchain. So it's the internet of value. And because data, and in particular observation data, is a digital asset, it's obvious to me that new way to interact and new business model will happen on the blockchain, where you could actually stream data with some kind of streaming benefits, or share data, for example, of a commercial operator that don't want to share the data, but could share actually the training of the parameter on this data. So federated learning, this is happening already with Google. Veracity of the data, when you release a helicopter for an oil spill, are you sure that you're actually using the data original, or are you downloaded it from a provider that has already repackaged them? So this is huge. This is, for me, the evolution of internet, basically, where you will have a distributed system with trust and value, so ownership of the data. And it could be that you could scale totally new way of doing business with the data with this. Then the metaverse aspect is the interaction with this. We talk a lot about digital twin. I mean, at the end of the day, all these destination Earth is for policymaker to make better decision by understanding what are possible futures. And to do that, you need to visualize and interact with the possible future. So you could stream different futures, etc. And then you have new computing technology like quantum. Some people have different time scale for it. And we believe it will play a big role in the hybrid machine learning pipeline, because it's good for some things, like, for example, self-supervised learning can cluster stuff much faster than others. But we're at the beginning of this with a few qubits, but a colleague from IBM can tell much more. And the convergence of this, you cannot predict what will happen. The only thing I can predict is that the value today of looking at tomorrow is very high. That this I can tell you, and people dismiss this because they are busy with the today. But we should look at tomorrow and after tomorrow, and that's why the Phi Lab has been created, in fact, to have the luxury to look at this, knowing that one day it might actually change things. We have seen it with machine learning and weather forecast.
Great. I'll sneak in a question myself. Actually, there's a lot of interest in ML on board and a lot of hype around it. Personally, it makes me always a bit nervous, and not all of you might know the history of some of this, but when the ozone hole was discovered, not by satellites, but by ground-based measurements, NASA went back and wondered, well, we had a satellite up for years actually already that should have measured ozone, and they didn't warn the world about the ozone hole. And the reason for that is the algorithm had a hard limit. This was way lower than expected. And so the algorithm was written in a way that there couldn't be an ozone hole because it was just not expected. So I wondered, with ML on board, it's sort of this being out of training, and how do we ensure that whatever we put on board generalizes to the unexpected when we put it up there? And I wondered, you must have given this a lot of thought already. I wondered if you could share some of this.
Yeah, I think that we cannot. That's as simple as that. I mean, the ozone hole story is a superb anecdote because it's a bias of human. People didn't think it could go there, so they told the machine not to look. So at the end, it was us. But we will need security system and safety system. It's much bigger than AI on board. It's about trusting algorithm. Our life is done with algorithm, and we tend to believe it's the truth. We were yesterday following a GPS blindly, and there was a problem in the app. So it's about education of people, and it's about including domain experts, etc., in the loop. But for the AI on board, I just want to stress something. I would differentiate the science community, like our colleague here at front, who will anyway need all the data, and the business people who need to make very fast decisions and need to have just a few information. These are not in conflict. You can have the same satellite that can store the data, beam them, and one part of the track that would analyze real time and send it to the user so that they can decide. But please do not filter data for scientists, otherwise we have a mess and we cannot revisit the archive.
That was reassuring. Questions?
Feel better now?
Yes, Jonas.
Maybe more a comment towards your question. I believe, like a lot of today, Jonas Weiss from IBM Research, sorry. I believe a lot of the machine learning models that we deploy today, they're targeted at a specific problem. but like in industry, in manufacturing, there is this like anomaly detection, which is very strong. So I think if you add like these anomaly detection algorithms on top of the specific problem solving algorithms on your systems, that could potentially help you if you like add different timescales to the anomaly, for example, to kind of exactly detect these kind of outliers, these patterns that you don't expect because it's just an anomaly, but you don't know upfront what anomaly that actually is. So I think there is techniques, there is schemes to not make sure, but like to increase the chance to not miss some of these like hidden indicators of something that's happening that you're not expecting.
Fantastic. Even more reassurance. Very good. Further questions? If not, then I think we're probably in a good position to move to the next talk. Thank you very much again, Pierre-Philippe. This was fantastic. And the last talk in this session, before we break for coffee break, is by Pierre Gentin. Unfortunately, Pierre Gentin is unwell, but he's still well enough to be at a computer, but not to be in the room. So he'll join us remotely. Thanks so much, Pierre Gentin, for making this happen regardless. And we hope technology doesn't fail us. So let's keep the fingers crossed.
Hey everyone, can you hear me?
Do we have Pierre in the panel? Okay, so then we can bring him on.
Is that working now? Or?
That's a good question. Do we need this? Is there sound for the room as well? I don't know yet.
Can you hear me?
Only here?
Yes, Pierre.
Or do we have speakers for the room as well? I don't know. We don't know. So maybe you have to
just wait a second.
Makes this look all very, very important. But if you had speakers for the room, it would be nicer, but otherwise we'll do it this way. Well, thank you. That's a good start, yeah. Pierre, can you hear me?
Yeah, can you hear me?
Fantastic. Yes, we can now hear you. We just need to bring up the screen the right way. I think we see it on Zoom, but we don't see it on our screen yet.
Okay. Is it full screen or?
On Zoom, it looks great. On our screen yet. So give us a minute to figure that out.
Okay, sure.
How do we get this up here? Sorry? Well, the presentation is up. We see it on top. We just need this. But we can hear Pierre nicely on the microphone. So that
you have to switch to the share content.
We have to switch to share content.
On the left.
On the left.
Next to the recording.
Next to the recording.
You see the red dot of the recording?
He's sharing. It looks good on Zoom. We just don't need it up in the room.
So next to the red dot of the recording, there's it says switch to share content.
Oh, switch to share content on top. No, on the top of the picture. Yeah, there we go.
Yeah. Thank you.
Oh, beautiful. Yeah, apologies for the delay, but we're actually
no worries.
Perfectly on time. So we just hand over to you straight.
Okay, perfect. Yeah.
Let's take it from here.
Thank you. And I apologize for not being here. So my wife got COVID and my daughter and then myself. So really apologize for that, but didn't want to spread it around. My talk is going to be quite aligned with what we discussed earlier. So talking about how AI can potentially help for climate adaptation and resilience in particular. And really a lot of those things you've seen throughout the day already, but trying to kind of have a bird's view as to how that could actually help. And about myself, so I'm director of the LEAP Center, which stands for Learning the Earth with Artificial Intelligence and Physics. So that's a new science and technology center, mostly at Columbia University, but we also have multiple partners over the US. And I'm also like part-time chief technological officer for Telus AI, which is looking at climate prediction using AI. So the current gap really is that climate predictive intelligence and for resilience and adaptation is really needed. So it goes without saying that climate change is really happening now, and you can see this is just taking a few extreme events over the last couple of months. So starting on the left-hand side in Florida, massive amount of flooding unheard of. Then looking at heat waves in India earlier in the spring, Spain that was baking back also in the spring in April, and then the wildfires. So those are pictures from just a month ago back in New York, where we basically had very unhealthy air quality for quite a few days based on the wildfires in Quebec. And so a lot of that is actually related to climate change. So it's very clear that climate change is not a prospect anymore, but it's really happening right now. But we are surprisingly too unprepared as it goes and we start thinking about climate adaptation and resilience in particular. And I'll try to explain why. And it's also very clear that the frequency and the intensity of those extreme events have been increasing over time. So that's also what is actually causing a lot of stress on society. This is just an example showing the number of heat waves recorded over the US. And you can see from 1960 all the way to 2010, there's been a dramatic increase in the frequency of heat wave events over the US and also in intensity as well. And of course, with that goes also an increase in associated costs. So this is just listing all of the different disasters that we've been witnessing also over the US here. That's based on NOAA record. And looking at basically the increase here in the number of disasters, but you could also look at the cost associated with that. Those are billion-dollar disaster events, and there's been a dramatic increase in the cost associated with those events. So basically the main point being that climate adaptation is really needed right now to basically reduce the cost on society, and so we can be better prepared to actually adjust to and be more resilient as a society. So the main way we can be more resilient is to start thinking about the prospect or the forecast of the future. And really, when we start thinking about the future, what we need to basically forecast. And to forecast, we basically need models. So those things have been discussed earlier today. And typically, especially when we start thinking about long-term, so couple of decades in particular, we use what we call climate models, so physically based models, so not AI based, but we are going to talk a little bit more about that in a second. And this is just showing a global metric here, which is used for policy making and for the Paris Agreement, which is this global surface air temperature. And this is an example here showing basically the spread that is being witnessed across different modeling centers. So you have many modeling centers across the world, in the UK, in the US, in France, et cetera. And basically they participate in this so-called CMIP, couple model intercomparison project. So that's the latest one, CMIP 6. And basically they compare the results from their model and the different forecasts that they have. And this is here showing just the spread. So this is the spread across the different modeling center forecast across the couple of different decades. And this is done for different scenarios. So if you're not familiar with that, but those are different socioeconomic scenarios looking at land use and cover change, but also emissions, greenhouse gas emissions. So from the more optimistic here 245 to the more pessimistic 585. But the main take home here is that there's very substantial model spread, meaning that we have very low confidence, even in some very basic metrics, such as global air temperature. So this is really, in my perspective, this is a major elephant in the room when it goes to, and we start thinking about climate change. So basically, the take home here would be that climate models forecast, or what we call projections, but we're going to talk about also shorter term prediction. do not translate into actionable adaptation. So there's really a gap here that we really need to address as a community. And this is true for global metrics, but I would say that this is even worse when we start thinking at the regional scale. And this is just a result from the IPCC report from a few years ago, trying to look at basically the forecast in terms of agricultural and ecological drought. So this is a synthesis even just of the observed change, but very much the same can be said about forecasted changes as well. And I want to point your attention here in terms of the confidence level that we have. So 1 dot means low confidence, 2 dots means medium, 3 dots mean high. Sorry. And the main point being that this is basically some subcontinents here. This is Western North America. This is North America here. This is Europe here, Africa there, and South America. And the main point being that basically there are very few regions, in fact, 2 of them, where we have medium confidence in human contribution to the change. And this is Western North America and the Mediterranean. Those are regions that are well known to have been witnessing major increase in droughts. There's been multiple examples looking at triggering records, etc., or looking at observations. And those are regions where we believe that there will be an increase in the frequency and the intensity of droughts. But beside that, if you look, there's very low agreement in most of the regions of the globe. And in fact, this is summarized here in the IPCC, the future occurrence of low likelihood, high impact events linked to climate extremes is generally associated with low confidence, but cannot be excluded. So basically, what it means is, as a society, we are basically unprepared and we don't know because we don't know what's coming up next. So that's a major, major issue. And if you think about water resource management, I mean, that should be your go-to place. You should have confidence in the future. And this is true on long time scales, but this is also true on shorter time scales. So typically we refer to those longer time projections here as climate projections. But shorter term, we typically call that climate prediction, more like the technical jargon. But the main point is that climate prediction is really no better. This is an example here looking at winter temperature. This is the North American multi-model ensemble on the right-hand side. So physical model projection prediction here of just winter temperature. And you can see that the correlation with the observations is almost 0 across most of Europe. So again, it means that we are in a very poor place in terms of the prediction for winter. This is for winter, but the same could be said for the summer. And I just wanted to point out that this is an earlier study, like way before like a lot of those much improved results. But this is showing using basic clustering here that machine learning could actually be doing a better job. The correlation is actually higher on the left-hand side than what you have on the right-hand side. So it means that fundamentally there's something wrong, and so that models are actually not that performant when it comes to climate. Okay, we know that climate change exists, of course. We know that temperature is increasing, but the specific details like looking at the changes in the hydrological cycle, their regional impact are very, very poorly constrained. And that's something really to keep in mind, right? I mean, that's something that will be actually where the impact acts, right? The impact happens at a local or regional scale, not at the global scale. So how can AI help? And here it's mostly a summary of things I found pretty exciting and really not based on my work, but just trying, that was based on the workshop. I thought that it would be interesting to see how can AI help actually in terms of resilience to climate change. So the first point is really on resilience itself. So more short term, like how can we actually tackle especially extreme events, because we know that those extreme events are going to be very critical. So how can AI actually help and support some resilience to those extremes? So one first example is flood forecasting. Flood forecasting tends to be very tricky, tends to be computationally very expensive. And that's an example from Google here, where they managed to actually get near real-time Google this flood forecasting infrastructure, where basically they can emulate a hydrological model and an inundation model, and really can provide that to an end user, and really can provide that so that people can be safe. So this is an example here on an app where you know the water levels now, and you will actually know the evolution till tomorrow. So this is on the rise, and you will know whether you will need to evacuate in that particular case. So this is very useful type of information. And that can really help actually in terms of resilience and saving lives and communities as well. Another pretty cool example is mapping inundation in almost real time. So within almost a day, sorry, of timeline. This is work from, they used to be called Cloud2 Street. So it's a startup in Brooklyn, but they are now called Floodbase, and they use very high resolution satellite data, meter scale resolution satellite, and they basically map inundation in near real time, especially in an urban context, so that they could actually map where the inundation took place. And they work a lot with insurance companies to potentially reduce the cost of flooding and inundation, especially in underdeveloped communities. So they are very interested in the global south, and the founders are very dedicated to having solutions that could help reduce the cost of inundation in the global south. So this is definitely a very good example of AI for good. Another example here is in terms of fire. So trying to think about early warning systems. So this is trying to basically look at the progression of wildfires using Sentinel data in that case. So satellite in almost real time at pretty high frequency resolution, and looking at, you can see that typically there's going to be, of course, a lot of smoke that is actually typically making the surface opaque, but they look at high temperature components, and they can look at this high intensity heat to actually track it over time, so they could actually know where the fires are actually propagating. So they can use that to really provide this early warning system. And this is used as part of this radar, this rapid analytics for disaster response from PNNL. So this is a very useful signal that can be used, for instance, for firemen, or to actually provide to make sure that people are safe and they can be evacuated on time. Another example that could be very useful is trying to think about hurricanes, especially if we could provide that a few days ahead. We could evacuate people and cities and communities as much as possible. So this is an example here from Zoom Earth, where we can actually monitor hurricanes. So I just took it from yesterday. You can monitor hurricane or tropical cyclones in almost real time. And there's been also a lot of progress trying to predict tropical cyclones' lifetime and maximum intensity as well as their counts. Those were things that were really challenging, but this is something that is getting much and much better. So we can start thinking about wind impact and the wind intensity. So that used to be really challenging because that tends to be at very, very fine time scale. The details of a hurricane tends to be very important to actually define the intensity of the hurricane. So those are things that can become very useful. And that's where deep learning in particular can become very useful as a tool to better predict those things, and therefore predict the intensity of those events, and therefore help tackle those or evacuate. This has been talked a lot throughout the day already, and how can AI help? It can also help in terms of improved prediction. So, and I will talk about different timescales, and several of those have been discussed earlier, starting with the weather timescale. And maybe one thing we haven't talked too much about is almost what we call nowcasting, so very, very fast timescale, which tends to be not really done by weather forecasting because it requires too frequent assimilation, but basically this next hour rain forecasting. And basically DeepMind actually showed that they could be very, very skillful and be almost as skillful as the radar. So this is the example here. This is the radar data of precipitation over the UK. And this is basically the deep learning emulation of that using generative models by DeepMind. And you can see that there's very close agreement between the two of them with very small details that are very nicely captured. And those are two other examples, so slightly older generations examples. You can see UNet is a very typical architecture that people use, and you can see it's way too smooth. It doesn't have all of the granularity and all of this crispness that you have in the target data. You can see that now we're actually able to do that. And once it's trained, it's important to remember that those tend to be very cheap to run in almost real time. So that's a huge advantage. So this is cheap and very skillful prediction at basically an hourly timescale. We can go to slightly longer timescale. So this has been mentioned before. So a big step forward was this ForecastNet, which was this global data-driven high-resolution weather model, and that's using what we call Fourier neural operator. If you don't know what neural operators are, so those are basically neural networks, but on operators as opposed to values. And they showed that they could actually do a very good job at basically capturing, even at couple of days lead time, they could do a very good job at predicting the weather. So this is the truth here at the bottom, and this is the ForecastNet emulation, if you will, or prediction. And you can see that even some typhoons were very accurately depicted here, and this was mentioned earlier today. The main point was that at the time, the forecast, so that's one example here, this is wind at 10 meters. So typically people start looking at what we call some skill score or here accuracy. And you could show that the accuracy here is actually slightly lower than what was actually provided by the IFS model, which is a physically based model with data assimilation. So there was still room for improvement at the time, and the forecast was for up to 2 weeks. This got improved. So this was also mentioned before. So the Pengu weather actually made some improvement, and now the forecast and the accuracy managed to actually go to a better skill and better accuracy than the operational model, which was the IFS here improved. So that was a big improvement, and you could see that some tracks, even of typhoons, seem to be better than actually predicted by the weather forecasting centers here, which is still state of the art to a large extent. So that's what was really impressive, and showed that AI could do not just similar skill, but potentially better skill. And that seems to be tested more systematically at ECMWF, but seems to be having really an edge and could be basically doing a better job than a physically based model. And there was also further improvements, such as the GraphCast that was also mentioned earlier by DeepMind. And also I would like to mention that those two actually showed even improvements or really new developments in terms of architecture. So we are really starting to drag a lot of people from the machine learning community into the climate and weather community, because things start to get really interesting from an architecture standpoint, right? We have 3D, multiple variables or multiple timescales. So it becomes really interesting in terms of architecture, and we can really start seeing a lot of developments happening at the same time. So this was using graphs at multiple scales and multiple meshes. So really, really interesting developments in terms of even deep architecture as well. But the main point being that now we can almost beat, it seems, and more work seems to be needed to evaluate that, but the skill seems to be almost on par with weather forecasting centers, but at a fraction of the cost in terms of running them. There's been also improvement in terms of longer time scale. So this is also at seasonal scale. So it's a very recent paper here published in June, showing that if we compare to every single climate prediction center at a couple of weeks time scale for precipitation and temperature, we can actually bias correct those models dynamically, which is the blue here. And you can see that there's dramatic increase in terms of the scale compared to the relatively low scale that there was initially with the models themselves. So it seems that there's really an advantage in combining a physical model with AI, especially when we want to predict ahead of time. Okay, and I would like to point out that why is the scale so low, you could say, in physical models, is because a lot of the physical structural errors of the model become more apparent when we start looking at longer time scales. There's been also improvement in very important phenomena such as El Nino, so on seasonal to yearly climate time scale. So this is a very cool paper looking at how we could actually harvest data and harvest climate models and then fine tune that using observations from El Nino. And the skill here, again, higher is better, was actually better with that model here, which was using this transfer learning and deep learning approach on multi-year and El Nino across, and you can see a dramatic improvement after almost a year compared to the basically state-of-the-art physical model. So this was a really big improvement at the time. I would like to very quickly talk about just a few things, the difference between weather and climate, right? So weather tends to be on shorter time scale. So we've heard about a couple of things or efforts in that aspect, such as Earth 2, Destiny. And in that case, at weather timescales, we have a lot of data. So we are basically in a data-rich domain where pure AI can really work really well because we can harvest a lot of observations that have been taking place. When we are looking at much longer timescales and climate timescales, the issue is that we have very few data points, right? How many years did we have? How many droughts did we have? And that's really where we are trying to work on, especially with LEAP, USmile, Marcus and Gustav are in the room, and M-square lines. We are really trying to combine physics and AI so we can better extrapolate to regimes that I've never seen before, such as climate change. So on that front, really what we are trying to do for projections, so longer timescales, is trying to use AI to improve climate models. And we are really trying to actually better represent physical processes such as clouds, ocean eddies, or photosynthesis, which are really at the source of errors and the source of spread that I explained before. And they explained a lot of the spreads, say, in global air temperature, ocean heat content, or even in the carbon uptake itself. So it means that we really need to nail down those physical processes because they are at the root of all of those uncertainties that I showed you before. And we really need to do a better job at representing them. And it's difficult because they tend to be very, very complex inherently. And that's because we are trying to represent them in models that tend to be very coarse in scale. And we need to do that relatively empirically. And we've been basically struggling to do that. And we call that a parameterization. So that's been very difficult to do that correctly. And that's been a struggle for the last 40 years, right? And that really explains a lot of the model spread I showed you earlier. So the strategy that we have is to say, maybe what we can use is we can use some of the very high resolution simulations that have been mentioned before at roughly a kilometer scale. We can use those simulations that are very detailed and pretty accurate, and we can use them and then coarse-grain them to use them for supervised learning, right? And then at that scale, on the right-hand side, which is comparable to a climate model, we can learn how we can better represent things, such as deep clouds, which we call convection. And then we can plug that into a climate model to actually improve processes and their representation. And that tends to work well. So this is an example here where we have plugged a deep neural network here directly into a climate model. And you can compare that to basically the truth, which is here at the top for precipitation. And you can see we can really get the nice structures that we are seeing in these cloud resolving, so high resolution simulation. We can nicely emulate that with a neural network. So this is very encouraging, and we believe we can do that at a fraction of the cost of the high resolution simulation. So that's really the advantage. We can still keep a relatively low computational cost. And that seems to improve a lot of things, such as precipitation extreme. So this is an example here where you have a typical low resolution climate model that tend to really miss all of the extremes in precipitation and tend to what we call drizzle too much, too many low intensity events. And we can actually do a much better job when we compare the neural network here in red to the high resolution model, which is in blue. In past climate or future climate, we can actually simulate future climate with a warming of 4 degrees. So that tends to be doing a good job. And that was back in the paper from 2018. And now we actually improved that even further using some new strategies. And now we are basically spot on in terms of precipitation distribution, again, at a fraction of the cost of the high resolution simulation. So it means we can really replicate really, really well the high resolution simulation. And that's nice because those precipitation distribution, especially the extremes, are really critical for inundation and flood projections as well. Quickly, the last thing I wanted to present is some very recent results where the other thing we can do with AI is to actually post-process in a better way climate models. And basically the idea is that we can correct models because they tend to be wrong. And I showed you earlier that they tend to have a lot of biases, especially spatial. And this is an example here where we take as the truth one model, one climate model, and we try to replicate that with an ensemble of neural network. And you can see we can do a very, very good job at replicating that here. And we can do that across different scenarios. So those are the time series of global air temperature here. And the little wiggly line here is the actual climate model. And then the smooth line is actually the ensemble average across different neural networks. And you can see we can do a very, very good job at actually projecting climate change using this strategy. So it seems we can do a good job projecting the future using a combination of climate models and climate models that are post-processed by AI. And this is just an example showing you how the future will look like. So this is what is projected by this strategy here. And this is the typical ensemble average. So the same as what I showed you before using the CMIP6 model ensemble intercomparison project. And you can see, we can see the so-called Arctic amplification, which is too weak in the models that is being corrected by the neural network, as well as some of the spatial features, especially in the Pacific, that are being corrected. And then the advantage is that we can provide better estimates of the future. So this is the example from this ensemble of neural network. And we can see that the warming is actually a little bit stronger than what we would expect from the unconstrained CMIP6. And we have much reduced uncertainties compared to the typical other strategies. So we are very happy with that. We believe this is going to provide better estimate of the future. So very quick summary. So AI can help in terms of climate change adaptation and resilience in many ways, for near real-time monitoring, wildfire, floods, or droughts, short-term weather forecasting, short-term climate predictions as well as longer-term climate projections. There are still some gaps. For instance, on seasonal to multi-year predictions, there's still not a lot of work going on. Also, we have a lot of empirical indices for risk, and those could be actually improved for using AI. And the other thing that was mentioned earlier is training. We need to train people that are well-versed in terms of AI and also in terms of climate. So that's one thing we are trying to do as part of our LEAP Center, but it's still a struggle. But I think we are still in a much, much better place now to face risk than we were just a few years ago. And as you showed, I think I showed in my presentation, it's not just an academic type of work, but there's tremendous private interest and the boundaries are becoming very porous. So with that, I'd be happy to take any questions.
Thank you very much, Pierre. That was really great. Really impressive overview. A lot is happening. That's pretty obvious. We open the floor for questions. Who wants to kick off? I'll start with, oh, there's one in the back. There we go.
Thanks. Thanks, Pierre, for the really great presentation. And I'm David from UN Climate Change, and I'm working in the intersection between frontier technologies and climate change adaptation. So first of all, I'm very happy that you chose climate resilience, whereas like many others like try to stay in the more safer realms, because as we all know, as also Pierre said, adaptation is like much harder to measure and to contribute to from an AI perspective. First of all, I wanted to say something that is probably something that is relevant also for the machine learning AI community, which is that currently under the UNFCCC, there is like a global goal for adaptation being developed, which could really help to provide focus also to those who are looking to do more in the AI ML world in terms of measuring adaptation. Of course, the goal itself will be quite broad. What we are hoping to also basically contribute some indicators and targets to that, which could then be used to measure and maybe could help or could use the help of the AI community. In terms of a question, I would like to actually pick a fight with you or provoke you a bit. I feel like the ambition of AI researchers or researchers using AI in the field of climate resilience still stays a little bit in this realm of weather, climate prediction. Flood is of course one that is nicely used for can nicely be used via Earth observation or catered to via Earth observation. But the question is, like, how can we go deeper? And because we all know that adaptation, the main challenge, especially in the global south, is vulnerability. So a flood in one place doesn't cause any big destruction. The same flood in another place causes huge destruction. So how can we look into, like, how can we use AI to understand better or do multi-factor analysis to understand, okay, what does or how can AI help to really find out who are the most vulnerable in many specific cases, and how are those, and how, what can we do to protect those? Also, from an accessibility point of view, I think it's good to further develop all the models. The question is, how can also, I mean, you said you're going to train people. What else can AI actually do in order to increase the accessibility, be it in terms of language, be it in terms of capacity building or something, or basically just a chatbot? We have now this chatbot for the IPCC report, which is great. So these kind of things. And then last question is like, what is the chance for open source model and solutions? Because we often see that we have this buy-in or this big solutions that are then propagated, but then we don't have, we pitch it to countries, but then in the end they lock themselves into the solution, and then it gets more expensive and more expensive. There, what are the chance for open source models and solutions here in the space to come? And sorry for the long intervention.
All right, Pierre.
Yeah, I will try to remember all the questions. The first one is on vulnerability. So I would think AI can be very useful, right? Because you can map basically the intersection between climate risk or physical risk, as we call that, and vulnerability and exposure. So I think that would be very, very powerful here. The second point, and I think I'm pretty passionate about that stuff, is inclusivity, right? I mean, that would be another way to frame that. And to me, AI and cloud computing is a tremendous asset, right? Because you can actually start thinking about compression, providing data at scale. A lot of the compute can be done on the cloud. In fact, as part of LEAP, we are partnering with an organization called Carbon Plan, so we can provide data, climate information to anyone in the world just on a simple browser. You can extract the data, and you can even transform that into storytelling. So that's, to me, is really exciting. And that goes back to your point, is where AI comes in is, I think, in terms of analytics that is being done really, really fast. Second is in terms of data compression, so we can actually provide data at scale really, really quickly. And the last one that we typically, because I think we are still part of a niche here, is that we oftentimes tend to forget about is language, right? So we can actually basically translate into different languages, and that's really the way to be more inclusive. So to me, that can provide a tremendous leverage in terms of how we translate the science we do into something that's actually more useful. I hope that answers your question.
Thank you very much. Further questions from the room? I'll sneak in mine then, which is good. You showed this nice advancement in parameterization development, the deep convection work, and obviously I didn't have time to go into, but in 2023 paper, it looked all perfect. Am I right to guess that it looks perfect as compared to the training data, which is probably the high resolution model?
Right.
Or
yeah,
was it
right.
in comparison to actual observations? And have you looked at how different this is? Which then might open the question is, could one learn from the training data and observations together?
Yeah, this is a great question. And I really love your slide, actually, by the way. I think you're exactly right. I mean, the way I have that in my mind is that this was compared to high resolution simulations. But as you said, even 1 kilometer simulation is wrong, right? And we need to be very careful when we say that they are Earth twin, because they are actually quite different from the actual Earth. And we typically cannot reuse them for climate change studies because they have really important biases, such as in top of the atmosphere imbalance. And so that's really how we are seeing that, is that first we try to match that, and that seems to be really good. And then for precipitation extremes, we know that a lot of those things will be quite close, and then we can just fine tune that to observation. So those are things we're actually doing and trying to compare that to observations and trying to improve those things based on basically some sort of data assimilation. And we are trying to develop a pipeline and workflow for those things. Yeah, this is a great question. But it's part, we always need to go back to the observation.
So let's get started. I mean, some thoughts have already been kind of shared. Okay, thank you. This is a slide I usually start also with like at a higher level discussion. A few years ago, I would have had to motivate it. Unfortunately, today, not anymore. things are changing. We are in the middle of change, or like probably rather at the beginning of change, but it's already quite happening. The mouse, okay, good. So there is going to be areas where we won't have enough water. There's going to be areas where we're going to have too much water, and people, or if you're going to be living there, you'll be asking yourself, will I be affected? When will I be warned? In many areas, it will be even more substantial, that you will be asking, will I be losing everything? Or how can I be even safe? Will I survive? So in order to solve or help solve these questions, the WMO, the World Meteorological Organization, has this program, Multi-Hazard Early Warning Systems, and I'm sure like today's session is not completely disconnected, also not at least partially motivated by that program. I borrowed this figure from the WMO. It's about how they look at things, and I think it makes very much sense. It's also very close to what we're actually working on explicitly at the IBM Research Lab in Zurich, together with our colleagues at a global scale. So we have to, if you want to tackle this challenge about warning people as early as possible to help being and get prepared, and we have to understand what disaster risk actually means. It's about what risks do we have and how is the risk composed. Only then we can actually start making meaningful predictions. And once we know, or once we think we know what's going to happen and who's going to be affected, we have to disseminate some warnings, and ideally create some adaptation strategies to become more resilient for whoever it is. And then you can go further back, and then you can start circling. And in our case, sorry, gotta get used to that. We are not a government organization. We are a for-profit organization. So somehow it's not just about helping people, it's also about helping organizations. So, and in order to help organizations, maybe kind of sending some alerts. This is like, we have a system that helps actually companies do that. Like if a hurricane's coming, try to understand when do we have to kind of shut down the servers and move the data and the workloads to somewhere else. But fundamentally, it's about like impact estimation in the longer term. So before companies make investments, they want to understand, does it make sense to build there? Does it make sense to kind of build up a supply chain with certain locations? And then the adaptation is not so much about like the safety of the people. Of course, that also concerns, because I mean, industries and companies, they don't run without people. I mean, people are companies, but it's about like protecting infrastructure, protecting investments through adaptation. So, but for the moment, let's get back to the original WMO scheme. And if you want to manage risk and become more resilient, you have to understand risk, right? So as an input, we have the climate change, we have the climate, we have extreme weather, and there is something called the risk propeller. Who in here has seen a risk propeller before or knows what it is? Oh, that's good. So it's even worth talking about it then. Good. So it's very simple, but it's important still. I mean, risk fundamentally is composed of vulnerability. So it means like how are you affected if something actually happens? Are you going to be affected intensively or just slightly? So you can see, I mean, if you're living in a hut or in a skyscraper, it's going to be quite different. It's about exposure. Where are the things happening? Am I going to be close or am I going to be far away? And you can imagine the worst thing is if you're vulnerable and exposed. And this is like typically also what the WMO actually is aiming this early warning system at. It's like the poor people, the more exposed people who are vulnerable. So they're vulnerable and exposed. They have the highest risk. And then the next part is, of course, we need to understand the intensity and the extent of the weather hazard. And clearly, Earth observation, satellite images, they're going to help us there a lot. We can do a lot with those. Now, what we're working on and what we're building, what we already have built, is something which is called CIMF, so the Climate Impact Modeling Framework. This is an internal term, so you don't really gonna find it on the internet probably. It's about building and running complex workflows to build and map weather and climate-induced hazards. What do we need for that? Data. It has been mentioned before, big data. It was a buzzword. It's not anymore. It's just like a reality. If you talk satellite data, we'll see in a moment, it's going to be really big. What we do then is, for example, we take the satellite radar data, which helps us to look at the flood. We'll see how it's done on the next slide. So we do the flood mapping of something that we can observe, so in the past. Then we have like an integrated flood model. Today, our models are mostly hydrological. So with like the digital elevation map, we're working or starting to work on AI-driven like graph neural networks, trying to accelerate the physics model, because the scale of having hydrological models at large scales, even just city scale, is quite challenging compute-wise. So we're trying to use AI models to get some acceleration there while not losing too much of the accuracy. But then the model also needs like data like elevation, land use, soil properties, like how much water is in there, how much water can it absorb. But then we need weather, right? So we need a precipitation pattern. I mean, in the past, we can just look what happened, but that's not going to help us a lot. So we would like to understand what's going to happen in the future. Can we predict the risk of a certain area? How much will the area be affected if we're going to have like an extreme weather event? And for that, we built something which we call the AI weather generator. Sometimes I wish the AI wasn't there, just weather generator, turn it on and off. That creates extreme weather patterns. You'll see more about that later. Once we have that, I wanted to just quickly point that out. Why floods? Because we're going to be talking about flood as an example here, but we can use other ones. If you're wondering why floods, is because if you ask insurance, it's like 70% of all the insured damages on a global scale are induced by weather events, mostly driven by water damage. So water is definitely, for a societal and economical like impact, it's one of the most severe events we can have. So let's have a look at AI flood mapping. We're talking radar as a means of finding or looking at water. Now, are you familiar with synthetic aperture radar? Some are. Good. Okay, I'm going to quickly explain it anyway. So a radar beam is being emitted. It's a chirp. You can ask me more about that. I've done that in my master's thesis at ETH like 20 years ago. The reflections are being measured. And the good thing about that is, if you think of like an extreme weather event, like kind of thunderstorm causing floods, what do we have? We have clouds. So a lot of satellite spectral bands don't really go well through clouds. So detecting water through these spectral bands is going to be tough, but the radar goes through clouds. So whenever we have these extreme events, we can see the water even through clouds. That's a good thing. The bad thing is that, for example, if you look at Sentinel-1, it used to consist out of 2 satellites, but one was declared dead I think it was last summer, like in 2022. So there's only 1 satellite at least from the ESA, from the Copernicus program. There's more private ones coming up more and more, but it has a revisit time of 12 days. So if you have like a flooding, and if it just passed, you're not going to see nothing, because like 12 days later, probably most of the water has already recessed and is not there anymore. So what you get from this radar is like images like this. And then the question is, where is the water, right? But the good thing is you don't need a flooding to actually be able to train your model, because there is permanent water, and the same signal reacts also to permanent water. And then what we do, we use something which is called the UNet. You've heard it before, it was mentioned. Probably most of you are familiar with it. It's an encoder-decoder kind of network, mostly based on the ResNet retrained convolutional kernels. What it does is it gives us a pixel-wise map of the image that we put in, and tells us which pixel is water, which pixel is not water. So, and then fundamentally, if you have like a permanent water map, you just do the difference, where is permanent water, where is now water, and then you know where the flooding happens, right? The challenge about like this is, if you want to train a model like that, you also need to have like a pixel-wise ground truth. Meaning there's not so many data sets with very accurate flooding maps on a pixel level, which we can actually use. So there's a challenge there. We'll get back to that. So now we have the flood mapping, which helps us to validate the model in the past. Let's have a look at the AI weather generator. I could imagine that maybe you're curious about that. You know, autoencoder, probably I don't have to explain anything here, right? So data in, latent space, reconstructed output. Now, if you imagine that could be weather, and we just look at the decoder part, could we maybe somehow probe, trigger, ingest something that we just can say, I would like to have bad weather, and then the thing creates as a bad weather output without actually having to input bad weather, so that the information in the encoder is kind of implicitly, it's there, that we can use it as a weather generator. Now, it's unlikely that like if you just do it like that, that it's going to work, because the latent space is not regular enough. It has not enough structure to allow us. I mean, there's like extreme weathers that could be very close together, like extremely good and extremely bad. So you might have a bad chance to actually get what you want. But there is hope. There is a trick that is used mainly from the variational autoencoder space. It's that to not have actually kind of every point represented as a point in that space, but more as a distribution. And then you can start sampling the distribution around the point, which gives you more meaningful results. And this concept, not exactly this, but this concept together with extreme value theory is what my colleagues in Brazil are exploiting to create and to sample around these spaces and to create these extreme weather maps. What they can do with it, if they sample specifically the long tails to get rare events, they can get like create statistically sound weather patterns from like, at least based on the observations they have. They cannot create something which is completely off at that, but at least statistically, they can create something which would represent a 1 in 100 or even a 1 in 1,000 year precipitation pattern that can be then fed into the model to create a flood extent estimation or a flood risk extent estimation for the future, which would help us understand like what is the risk in a certain area if we have like a 1 in 1,000 year event that we're going to be flooded. What do we have to do to not be as affected as much as we might without any changes? Now, once we have either the flood extent kind of mapped or estimated with the model, which is fundamentally just visualize it and then put it into context. For example, this infrastructure is like just showing a power plant, so you can better understand how are you going to be affected by the floods. In a very similar way, we're also doing like wildfire risk forecasting. Again, we're not forecasting the wildfire, we're forecasting the wildfire risk because we want to understand where do we have to do something. It's less about immediate warning. It's just about trying to understand where do we have to look at. And besides wildfire, there is like a whole lot of other use cases that we tackled with customers based on a specific data set that we have, which is about 6 petabytes, but this is not the topic of this presentation. So it's from greenhouse gas monitoring over disaster, irrigation in the agricultural space, but also logistics planning or geospatial asset management. Now, if you start working with these geospatial data, sooner or later, I already mentioned 6 petabyte data corpus. So that's kind of when we started understanding what the challenge is working with these kind of data. This is not something you just move from A to B. It's not just a floppy disk or a USB stick or a pen drive. So you have data gravity. This stuff is huge. I mean, we have 6 petabytes. Typically, if you want to have like quite an extensive repository of data that you can work with in many domains, you're in the hundreds of petabytes of data that you'd have to store. And it's not reasonable for everyone who actually works on that data to store with it. So it's too big for one organization. But if you want to do some meaningful AI machine learning algorithms, very often you need these different modalities. I mean, you've seen it on the previous slide. There is like soil properties, there is like climatic data, there is digital elevation maps, there is whatever you want. So there is a good chance that you want to have like quite a few of these modalities which are present there. So you probably have to think about distributed data. But then on the other hand, even if you know where the data is, then again, you have the data gravity. How do you move? So the moving data back and forth is expensive. That's why, for example, federated aspect like federation concepts, federated learning, as like Pierre-Philippe mentioned, come increasingly into play. But then there is also something about, it was kind of, I'm not sure who mentioned it before. Even if you have people who are willing to collaborate, they might be legally bound to actually not fully share the raw data with you for some legal constraints because of competition issues or whatever, but would still be willing to say, hey, if you just want to look at the data, but without getting the data, fundamentally running a model, that could also be interesting. So I would be willing to share the data. That's what I wanted to say. So if you don't have to get the raw data from me, but just want to work on it and just get some features out of it, I'm going to be fine with it as long as you can't reconstruct the raw data from the features that you extracted, right? So security and privacy concerns, right? So if you look at all these challenges that we have by working with these large amounts of data, it kind of becomes clear that you want to look into distributed AI workflows, which are distributed at a global scale. And this is what we try to solve or help solve with what we call the geospatial discovery network. It's a network that we started building up, which is about data sharing. It's connecting. We have like ECCC in Canada. We have our own data corpus. There is like discussions with DLR. I think more recently, even with some other large corporations, like organizations which are represented here in the room. It's about connecting these. Now, in order to connect these, typically it's like high performance compute centers which store these large amounts of data. You need kind of a stack. Don't worry about the stack too much, but you need kind of ideally have a stack that not just these large corporations can actually come on board and collaborate in the network, but maybe also kind of smaller organizations. And for that, the stack must not be kind of dependent on a high performance compute infrastructure, because you typically cannot get it on the cloud. That's why we're working kind of on this cloud native AI stack. It's not really very sophisticated. It's just about like putting the tools that you use anyway together in a meaningful way, such that whenever you deploy it, you can easily connect to kind of the other participants in the network. On the bottom, it can be either like really cloud, like public cloud where you run your own stuff, can be on a bare metal, or you can use this kind of, especially from IBM, just recently it developed like AI cloud supercomputer with some specific AI accelerators, like similar to GPUs, but still different. This is kind of the things that in my view, you can do to tackle some of the challenges with data gravity using these large geospatial data. Now, you mentioned, I quickly mentioned the challenge of you have this segmentation and you have a lot of pixels that you need to kind of have as a ground truth, and there's a lot of work in doing that. So very often you're in the challenge that you have very few labels. And I'm presuming that large language models and the way they're being trained is probably halfway kind of known in this audience. It doesn't work exactly the same way in the geospatial way, but you can actually adopt these exactly the same concepts that you say, we're going to predict the next word, the next sentence, we're going to complete the sentence where a word has been picked out. We can do exactly the same thing in a base task, what we have here, like this self-supervised learning, but that's where we don't need the labels, right? We can do it in the climate space, but also in the weather, in the weather space, and then fine-tune the foundation backbone towards the downstream tasks. And this is a stolen image, but it pretty much shows exactly what we're doing. So we're taking an image, we're masking certain patches from the image during training, and we just have the autocode, like the encoder decoder system, try to reconstruct these missing patches. So very much what the large language models do with language, we try to do in space. And then in the end, we just add like a classifier, segmentation, detector, or change detector head after the kind of the foundation model backbone. When we do that, here you see some results from the backbone training. So from this like basic task, you see original, mask and prediction, like different kind of textures. And I'm not the expert, but if I look like on the bottom, all to the left and all to the right, and looking how little information actually is available from the mask, I'm quite impressed to see how well these models actually start to learn the structure of geospatial Earth observation data. So I think it's actually quite impressive. Also, on the next slide, you looking at different bands. Of course, if you have there's with different ratios of masking, you can't expect too much kind of matching of the output of the predicted if you have so little information, if you look at the original. But the structural content of how it looks like, the appearance, it really seems to me that the model is capable of learning the structure and how Earth observation actually looks like. Here, what we actually built. So this is we have the foundational model backbone. We have different versions ranging from 50 to 300 million coefficients, parameters. Now, if you're familiar with the large language models from GPT-4, GPT-3, they're in the trillions of parameters. So I think that it works to some extent quite well already with hundreds of million parameters is quite promising. So I mean, talking to or thinking of having AI in space on satellites. I mean, these are models that you can potentially run on your laptop for inference. I mean, they fit into a satellite. So you can put these models on board of satellites and run them there, right? Then in order to get to the actual head, since the embedding space, the latent space of the backbone is not exactly the dimensions of the image that you feed in, we have like a projector head that just does the size adjustment, and then the thing that's being trained is then fundamentally the convolutional output head, which does the downstream task. Now, to give you kind of an idea of the performance of what we have today, so this is, I think this work started only about a year ago. So I think it's really, in my view, that the progress is quite good. Are you familiar with intersection of union segmentation metric? So just for those who are not, down here the picture. So it's about like a performance metrics, how well you can segment the picture. It's about you do the ratio of the overlap area over the union area of the area that has been segmented. And so the better the things match, the closer you get to 1. Now, what we tried as an experiment, we used like a pre-trained foundation model backbone, and then retrained it with the downstream task. This is like for flood mapping. We'll get to that in a second. You see, this is like pretty much like the best you can do in this configuration. Then we use the same model, but we just randomly initialize the backbone. So we don't use a pre-trained on the basic task backbone. Do the same thing. It just takes longer. And one option is, of course, that you say if you, as soon as you start going into really large models, where you say computing the whole model is going to be like training is going to be really expensive. That means once you have the backbone trained, it might be interesting to not touch that part, but only the head for the downstream application. And then you can see with the yellowish greenish line, you can also get very close to the performance of the fully retrained and fine-tuned model. On the right side, it's not, unfortunately, not telling the full story, but it just shows the trends that the foundation model is actually capable of working with less training data. We would have to show a little more here, but you can see at least the trend that even by reducing this data set by just reduction by 87.5%, you can still get quite decent segmentation results. But we'd have to talk more about that if you're interested in that. Do I have a minute or two? Yeah. I'm almost done. Yeah. I'm almost done. Okay. So very quickly, we trained in the US and we tried to see how it generalizes over the world. It does mostly well. There's still some work to be done. So it's early results. And then we have the mapping and just the result you see. I mean, with this pre-trained model, we kind of can really meet the state-of-the-art segmentation performance in terms of intersection of unit, but also with the F1s for the water class. I'm gonna skip this and just gonna summarize. In order to understand the risk, so in getting back to the WMO kind of early warning, multi-hazard risk for all, we need to understand what risk is. So for that, we learned about the risk propeller. So fundamentally, risk is the exposure times the vulnerability times the intensity of the event. In order to do the mapping and the prediction of the events, we use Earth observation data. There we see that the transport, model execution, they can be challenging. So we need to have like look into sharing of data, federated learning, moving, not moving data around, collaboration, reaching people. If you talk about the WMO, is quite challenging. So ideally we use the channels. That was the last slide. The channels that already exist, because people, they need to be able to receive the message with the device they know, over the channel they know, in the language they know. But this is a challenge that I haven't been really talking about. So it's an interesting problem to discuss in a separate discussion. And in the end, to become more resilient through adaptation, we need this actionable insights. So it's really models that show us where the impact happens, where we can quantify the impact such that we know where we have to invest our money to become more resilient. With that, I'd like to close. Sorry if I was over time. I was just too comfortable up here.
Fantastic. Thank you very much. And one word
Of course, there's a huge team of people behind that. In Zurich, in the UK, in Brazil, in Yorktown, in New York, and in Tokyo, in Africa, in Kenya, South Africa. And I'd like to acknowledge their contribution. Thank you.
Fantastic. Thank you. Let's open it up for questions. Who wants to jump in there? I'll kick off. Oh, go ahead.
It's an easy question.
Can you press your button?
Okay, so it's an easy question. Thank you very much for the interesting presentation. I wanted to ask about the work with foundation models that you presented. Are there any publications about this work? I mean, this is the work that you mentioned with NASA, right? So I would assume you're using Landsat kind of archive.
Yes, I was speeding over that. It's like the harmonized Landsat Sentinel, the HLS model that we have a collaboration with NASA. It's not just a fuss; it's actually working. But yes, it's a collaboration with them, and they are. It's this challenge about for us what is being published and what not. To be honest, I'm not directly involved in that project. I'm pretty sure there is publications. If you want, I can look them up. I can ask my colleagues and send them. There's also always the question about like public domain. Is this going to be open source to the model or not? So from the NASA perspective, I'm sure sooner or later part of the model will be open source. Of course, again, we are a for-profit company, so we have to see what we're going to open source and what we're going to just make available to our collaboration partners. But I'll be happy to, if you leave me your address or send me a mail,
I'll leave you a card.
I'll send you the link to the publications.
Thank you so much.
I think that is an interesting theme we can maybe pick up later on as well. Again, I think openness, I think it's really important, obviously, for the climate community. We only have one world and very limited time, but I see there's a tension between different players, but it's something I would push very hard for. There was a hand up in the back. Yes, please.
Okay, many thanks, Jonas, for your great presentation. I'm Ben from WMO. As some of us you may know that WMO has two strategic plan recently approved. One is early warning for all, another one is greenhouse gas monitoring. And I'm wondering if there is you also mentioned during the presentation, I'm wondering if there is any AI-driven system or platform that have been developed to monitor or track greenhouse gas emissions recently, or on national or city, let's say, different scales.
I haven't been working on it personally, but I know. I mean, you've seen on my slide there is like greenhouse gas monitoring is part of the activities that we pursue with also with clients. But I'd have again. I mean, the details for it to the extent I think it's really something we do. But I'd have to dig out another slide on how it's exact. How exact? I think there's like Tropomi, the P5 from Copernicus is involved somehow. No, that was methane. Sorry. For the greenhouse gas, well, methane is a greenhouse gas, right? So I have to look it up.
Okay. Thanks.
Sure.
But there are initiatives out there. I mean, there's big sort of initiatives that go through all the data to capture carbon emissions. There's small scale work. Even a student of us, we just look for unknown emission sources where you just look through satellite data and look for coal plants that are in none of the database. So I think, yeah, there's all these things out there. It's how to put them all together and make them useful. I think is a challenge. One question.
I think that's exactly the challenge. It's like there's so many disconnected activities going on to make data and results available to everyone. That's a challenge.
Yeah. Further questions? If not, I think then let's move into a slightly more general discussion. And thank Jonas again first. And this is really not meant to be too prescriptive. I think it would be nice if it was bottom up and people could raise maybe some more general thoughts they had from the morning. Are there themes that stand out that you think are worthwhile digging a little bit deeper? We also have a panel at the end of the day, but I think any more reflections that people might have at this point? So I think I can reflect on two things, maybe to kick things a little bit off, and maybe the speakers can comment on it again. I mean, so I heard sort of two big themes to some degree, or two themes that stood out for me is a little bit. Obviously, Mariana has given a great presentation on what the future sort of weather modeling, weather forecasting might look like, and Pierre has touched on this quite a bit. And I think, so paraphrasing very crudely from Pierre's talk, is sort of current climate models aren't not yet suitable for adaptation. They have lots of flaws, and we agree with them. They have lots of benefits too. That's not bad, but they're not right on the right scales just yet. And then there's a lot of applications to piece together the puzzle. And then maybe from Mariana's talk is really, this one theme was they have a really strong physical model, and discovering or being pushed into discovering almost that the machine learning models can outperform their own models based, even though they're trained on the same model. But I mean, maybe a general question is there how to put this all back together. So you have all the different pieces. How do we put this all back together? I don't know if anyone has any further thoughts on this. Or more specifically, I could put Mariana a little bit on the spot, if I may, because there must be. Okay, and okay, Pierre, you also have your hand up. Sorry, I put Mariana on the spot first, and then Pierre will come in there. I mean, I guess the Met Office will, if you mentioned there's a new project, new initiative, develop your own machine learning forecasting model. All the current initiatives sort of are based training on ERA 5 and some ERA. What's your strategy then in the future? I mean, is the strategy to just keep going strong on the physical model and always have a surrogate model as a production model, or where will it lead to?
So I think that's probably a question for the director or the council specifically, but I think we're certainly looking into developing a machine learning model and seeing, you know, maybe we have two forecasts in the future, sort of where we have the machine learning forecast and we also have the physical model. I would say that on your comment about the difference between what Pierre was saying and what I was saying, I think machine learning model for climate is a much harder task than a machine learning model for weather. And so I think that's why these machine learning models for weather, they have a huge data set that they can train on, whereas climate is much more complicated. And I think ultimately we will need to put some physical constraints into it. I would say, and also where does the future go? I think people are already starting to look at training beyond ERA 5, because ERA 5 has this limitations because of, you know, the resolution, and ultimately we want to be able to resolve things at higher resolutions. So that we do know that there are people starting to train on the what we call our operational analysis. So that's what we use to initialize our model, so at 9 kilometers. But that comes with a lot of challenges because you don't have this consistent data set. Our model changes every year in different ways. So I think that'll be the next step, people training on higher resolution models, but yeah, it's not easy.
Well, that's interesting. And speaking to undisclosed industry players, it's hard to fit them on a chip anymore. So you can't, when you now want to train on kilometer scale models, at the moment, you just can't pack it on any system that exists. So that's challenges. Pierre, you have your hand up. So basically we have to be really hybrid. So we have to get our headphones sadly in again because we don't have a speaker in the room. Pierre, just unmute yourself.
Can you hear me? Sorry about that. Yeah.
Yes, we can hear you.
Yeah, on that front, I would say, I think there are a couple of points. I mean, the first one is that the machine learning emulators at weather timescale, they look good, you know, but at the same time, we should not forget that they use the weather forecasting initialization, right? I mean, so they will still need at the end of the day, some weather forecasting physical model, at least for now. So I think that's actually a very important point, you know, and they look better because I think they are implicitly correcting some of the structural errors in the model, right? I mean, there are issues in those models, and by learning that from like a long time series, they can actually correct some of that. So I think that's why, but you know, it's really in between, right? I mean, there's some benefit of the physical model and then benefit of machine learning. They cannot really be used for climate time scales because by definition, we are extrapolating, right? We don't know what the future is going to look like. It would be it would be a huge mistake to say you want to predict photosynthesis in the future based on the past, right? We know it's going to be very, very different because of CO2 effect, right? So that would be a tremendous mistake, you know, so to do that, you know. And so I think that's where really there's an edge to be on in between physics and machine learning, you know, where there's some regularization or some component given by some knowledge, whatever that is, you know, and trying to use that to predict, you know. So I would say on that front, and also we are very limited in terms of data. So and maybe just one last thing for weather, I think it's when we start thinking about extreme events, I mean, to some extent, especially if we train on historical data, we will need to continuously train, like almost like online learning, because there's a shift in the distribution, right? So if we were to train like 10 years from now, all the way to 2010, we will be missing a lot of big events. So I think that's also a challenge as well.
No, these are really good insights. Thanks, Pierre. I mean, in particular, it's similar to the storyline approach in climate modeling, where people look at past extreme events and really look at what they look like in the future. And yeah, sadly, they don't always look the same. No, thanks for sharing these thoughts. Any other themes or questions that people might want to throw in? I don't want to steer the discussion too much, in particular from observers maybe who've seen, also heard stuff that they just haven't maybe thought about before. This is your chance to get your questions answered. But I will steer the discussion if you don't do it. We can come up with ideas. I mean, the other bigger theme, I think, that stood out between sort of Pierre-Philippe, I mean, there were a lot of things in it, but between Pierre-Philippe and Jonas maybe is sort of geospatial foundation models and how these can be useful in the future is something that stood out to me. And it's, again, it's a bit like ML on board, something that's exciting and makes me nervous at the same time. So I wondered if we can gather some more thoughts from people and experts in the room a bit. I mean, how do we deal with hallucinations? I mean, it basically fills in plausible features in these gaps, but they're maybe not real at all. They hopefully have the right distribution of the right features in it whenever you fill it in. But then also when we distribute a data set, if ESA has now a foundation model and distributes a data set, how do we communicate this to users? What is the real information content from observations and what is an AI model? And how do we deal with uncertainty in this context? That's something I still struggle to understand yet.
Shall I take? Okay. So first, I think you should relax a bit. You seem to be really nervous on all these questions. There are also opportunities related to that and also big concern. I'm afraid I cannot answer this because we are learning by doing here. And as we work, we discover new problem as well. Also on releasing this kind of things, because we are quite used to releasing software in ESA, and especially openly. But now this software has some information embedded in it. So it's a different type of software. In fact, it's knowledge. And we are learning how to do that. Hallucination is a big problem. So the issue of trust, we will have different activities of this. It's like everything. For optimizing the uptake, at some point you need to understand. And that's where scientists, and in particular Gustav, will pass the floor to him to this. Sorry to put you on the grill, but about causality and all these things. Also, some aspects of using things does not need necessarily full understanding. If it's robust enough and you have a very long set of use cases where a self-driving car is a 99% security, you will go for it even without fully understanding. So there is also a balance there to have in order to use these tools. But again, we are discovering this. So sorry, Gustav, to put you on the...
No worries. Yeah, just a couple of thoughts, maybe picking your words and also try to link it with what Pierre just said. I think that everything boils down to extrapolation. And we have seen like a couple of examples today. But for example, there was this example on floods, right? And trying to learn on a latent representation with variational autoencoders that you can sample from and eventually come up with, realistic realizations of that. But there are caveats. I mean, you're learning from a limited amount of data, and actually these autoencoders are arguably demonstrated not to be successful in modeling details. So, okay, I mean, I can trust the methodology, of course, but in the end, you have to rely the data as well, and the knowledge that you can put in the training of these machines. No? Yesterday, in a different meeting, we have like almost a philosophical discussion about Plato, and there was a very famous sentence by Plato, like 2000 years ago, something like, the good decision is based on knowledge and not data. But data at that time mean observations, right? So there's like this dichotomy, right? In putting knowledge in the models, or trying to extract knowledge from the models, right? So, and this has accompanied us like for a long time already. So one thing is extrapolation. Can we actually extrapolate? Can we actually detect streams from models that have been trained with what we had just seen? Very limited in a way. This is one thing. And this speaks to what Pierre just said, right? There are like errors, right, in the models that we are also learning from, and probably that we should just live in the middle, in the interplay between these models and the machine learning, let's say data-driven models as well, right? So, and then I pass the floor to Marcus. So you can link it to hybrid modeling.
I didn't want to. It was too obvious. No, but I mean, I totally agree with what has been said. And that would be actually also a question to you from ECMWF. I mean, it's actually interesting that those models, like I know GraphCast a little bit better. They actually do not conserve mass and energy at all, but it still works. So, but one could, maybe it wouldn't be too difficult to make them also hybrid in a way that you model some of the coefficients or so, but still obey kind of mass and energy conservation. And I'm wondering if then maybe some of the longer term predictions or some more consistency would be even achieved. But I don't know if these kind of things are discussed in ECMWF or not.
Yeah, so actually this was a point that I wanted to raise after Pierre spoke, which is that actually, so we think, when these models first came out, we thought, okay, well, yeah, maybe they're getting some of these improvements just because they're aiming towards analysis, and so they're essentially post-processing. But actually, for example, Pangu, when we look at Pangu, has a huge bias problem. And so I think that we shouldn't just assume that they're just correcting for these errors. And like you say, they're not conserving mass or energy. And so I think but that's a good thing, because yes, we can start thinking, okay, well, we can improve these results. We can actually do better by putting on some constraints, or simply just by using the statistical post-processing methods that we've always used in the weather and climate community. So yeah, but I think it's dangerous to think that it's getting, that it's not got these systematic errors that the NWP models have.
Yeah, thank you. Yeah, I think that by the time we are building models which are more complex, we are opening also the gate for something that are more harmful, or that can be more harmful in terms of hallucination. And I think there are two ways to mitigate it. It's either like we do kind of reinforcement learning by integrating more human in the loop, or we are doing further development and putting more technology to white box somehow the models and adding some layers of interpretability or explainability of the output of the model.
I guess we're coming back to some degree to the openness, that the more open these models are and open to public scrutiny and so on, it and accessible to everyone. It sort of takes some of this away, but it can obviously be misused or misconstrued. I mean, sometimes, I mean, I'm right, I agree with Pierre-Philippe. Sometimes we worry too much about some things. I mean, the climate modeling community was very worried to make their models open source at some point. They were terrified by the thought because then people would just misuse the models and publish nonsense. And yeah, that happens, but I don't think it has changed the science because it goes under scrutiny. So I think the openness in all of these initiatives has rather helped rather than slow things down. Any further thoughts? Yes, please.
I'll dare to open up a new discussion at this late point. Moritz Weigel, I'm with the UNFCCC Secretariat. So what I found quite interesting is that that aspect of reaching the one in needs was actually only on the slide of IBM from Jonas. So that focus, the only private sector entity that presented this morning, while there was less focus on that important aspect from the public funded entities. And so in that context, what I'd be interested to understand basically from all of the speakers is really on that aspect. So the focus on what these great developments then mean for adaptation and resilience in developing countries that are already most affected by climate change. There were, I think, some comments in terms of open source applications being available, but we also know that that is not enough in terms of just having them out there. So in designing those programs and the models and also the outputs, I guess, in many ways, to what extent is that perspective included from developing countries? So from a data perspective, focus on data from that part of the earth, if it makes a difference. And then from a usability or accessibility perspective, how does that look like? Is that factored in, or is that all the work that was presented this morning really more on the model and at a higher level, and is not thinking of the end user application in those country contexts? And maybe one specific question to Jonas from IBM. I mean, you highlighted quite clearly and transparently the profit-drivenness of IBM, which is, of course, known, and still you also focused on your summarizing slide on reaching those in needs and highlighting the different challenges with that. So I was just interested in, where's the business case from your perspective on exactly that point? Thank you.
Well, that would have exactly been my answer. We're still trying to find the business case, the business model. It's like with healthcare for the ones in need. It's very, very difficult to find a value chain that actually in the end results. Everyone wants everything to be open, to be available. Even if you have like collaborations with governments, then they require fundamentally even that you're almost like your cloud servers on which your stuff runs must be kind of made open if you want to work with them in the project. So sometimes these relations are quite difficult, but I'm quite confident that in the long run we will find, because the need is really there. And maybe also in the context with WMO, with certain programs, that we can actually start to infuse some of the technologies and make some of parts of the technologies which can be crucial for these areas, make it in one way or another accessible, which is acceptable also from their perspective. But it's a big challenge to create a value model, a business model with these specific applications.
Yeah, maybe before giving it back to the speakers, I mean, I should comment briefly on this. I mean, I mentioned in my introduction slides that there are these discussions about how to make this a bigger global vision, this Earth virtualization engine that are being discussed in Berlin at this moment. And the idea there would be really, you would have a number of global hubs with big centers substantially underpinned by funding and research in different regions, and obviously also in the global south. But I think even in they're not limited to it. I think the early warning and forecasting, particularly for the susceptible societies, is really high on the agenda. The weather, I pointed out in the beginning, the weather, ECMWF does fairly good weather forecasts already for many parts of the very well developed world. And we have early warnings in place for many of these things. In the global south, we don't. So I think it's definitely a consideration from the public actors as well, not the private only, but it's really how to include everyone in shaping some of these visions. And the idea is, say, if you had a hub of one of these future high resolution digital twin centers, it would really have to include all the stakeholders from the global south as well to shape the vision, not just sort of use the data. And I think that technology of data access is probably solvable because you don't need to move the data anymore. You can do it in a browser on your phone. But how do you really engage stakeholders from the global south in defining the questions and also defining the development of what these models should do? So I think it's definitely up on the agenda. It's more, maybe we could have maybe had more an explicit focus on this, but I think it's a really good point to raise. I don't know if these speakers want to add to that as well. Maria?
Yeah, I should just make the point that so all of our data, ECMWF data, is available. So we run the forecast, and I don't think it's quite in real time, but you can download our data from a couple of days ago and have our forecast data. So in terms of the user perspective, that's exactly what that is. We're always thinking of the user. That's sort of our goal, our role as a weather center. And we do make global forecasts. So we don't just, even though we're called the European Center for Medium Range Weather, we always run global models. We don't have a local area model. So our scores are better in the Northern Hemisphere than Southern Hemisphere generally, but they're always, so we're always working towards closing that gap. And also in terms of your question about, I think you were talking about extreme events and climate and things like that. That's exactly what Destination Earth is trying to do. These digital twins sort of provide real-time information to users about risks from extreme events and climate. So that is the end goal, really. I hope that answers.
Oh, that's helpful. I should challenge you on having an early warning system a few days after is obviously not the most useful application for susceptible society. But I know exactly what you mean.
Yeah, no, I wasn't saying necessarily. So we provide, when I said we provide it a couple of days, sort of a couple of days behind, that's for any public user. We obviously provide the data to all the Met offices in a timely manner so that they can use them for their forecasts. But I'm saying even if you wanted to go online, you could download the data from a couple of days ago.
Great. I think this is a good time to wrap this up. It's exactly 12:15 when we wanted to stop. We have a lunch break now. Somebody must know where we can get lunch. I don't, but I'm pretty sure it's probably in the cafeteria where some people found coffee already. Otherwise, yes, I see a thumbs up from the back. So follow this knowledgeable man in the back or anyone else. And we start again sharp, I think, at 1 o'clock.
Okay, good afternoon. Hope you had a good lunch and are excited to go into the afternoon session that is pushed by Gustavo and myself. And I give just a very quick introduction, a bit of framing of the afternoon session. A lot of things have been already said in the morning, so some of that is almost a little repetition and wrap up. But starting maybe with the topic of early warning systems, we have seen that this morning in a different way, but there are these four pillars. The new initiative from WMO, which indeed motivated also this session a bit, and they are having, I think, two new things. One is this multi-hazard early warning system, and the other one is the early warning for all. So I think it's quite some progress that's being made conceptually. But if you look at the different aspects here, you see that vulnerabilities are mentioned, but they are actually not mentioned in the detection, observations, monitoring, and analysis and forecasting, but more on the general knowledge. So I think there are still some disconnects, and also artificial intelligence is not so strongly mentioned in the document. So that's basically the gaps that I would see. AI, then the question of ecosystem and societal vulnerability, so beyond the atmosphere, if you want, and then also risks and impacts that are not only multi or compound, but are also kind of systemic and are cascading in the sense that systems interact with each other. And I give you maybe one example, and we had here that this morning already also, that the same weather can have very different impact. So even if we have the perfect weather forecast or something, we don't necessarily have the perfect impact forecast. And we have been seeing that exactly that in Germany last year, where on the left-hand side you see the picture of the floods in Western Germany, which have been the highest damaging natural disaster in Germany since at least the Second World War, with 200 millimeters of rain over a day. And the interesting thing is a very similar synoptic event has been happening a couple of months before in northeastern Germany. And you see here where there was some water on the streets, and maybe one or two basements were flooded, and nobody died, and so on and so forth. So why is that? It's not because the weather was different, but because the landscape was different. So in Eastern Germany, we have sandy soils, pretty flat terrain. While in Western Germany, the soils are different, and then you see already on the images hilly landscapes, which then funnel the water into those villages. So that's something to be considered. Kind of the interactions between, on the one hand, the physical systems, the atmosphere, the biosphere, but also, of course, society, the anthroposphere, really needs to be considered if we think about early warning. And this is a bit then the emphasis on the afternoon. The second aspect has been also mentioned already a bit. So the question of how do we create an effective warning? So it's not only about prediction, and it's not only about natural science per se, but it's about communication. So how do we communicate that there's a risk coming? And just saying, oh, there's 200 millimeters of rain or a river level of 6 meters or so is for many people much too abstract. So one can do visual communication. Work from Chris Rekina from our group here, who looks more in the climate space, how a landscape can develop with different temperature and precipitation, for example. And they will talk a little bit more about that for early warning systems in the afternoon, Vitus and Chris. Flood forecasting, not only forecasting, but also really showing kind of how the landscapes look like, or even going into photorealistic generative models, where basically then you can see your property, how your property is looking like, given a certain hazard that has been happening. And last but not least, Pierre Philippe has also mentioned that. I think that's really an important point, also to leverage large language models and interactive AI for a better communication of risk, and also kind of two-way communication in that sense. So overall, last slide here in the introduction, what I think we should aim at overall to have AI really integrated along the whole early warning chain, from observation to weather forecast to hazard forecast, impact forecast, and the warning, where communication plays an important role, and then into the decision making. And that's also how one can see how this workshop is overall organized. We had in the morning, we had an emphasis on those parts here on the left-hand side, and of course with always some overlap. That is very good. In the afternoon, we more focus here on the right-hand side. And so I'm really looking forward. We have a really nice lineup of speakers in the afternoon. We take advantage of World Food Program and IDMC also being around, DeepCube project that has been meeting yesterday, and then also Alice fellows that are around. So we have, I think we get a broad view. And Gustavo is sharing the session.
Okay, thanks everyone. Yes, as Marcus said, we have a fantastic lineup today, treating a lot of topics, as you will see. We have talks about, I want to read this because I don't want to forget anyone. We have early warning system for food systems, forecasting drought impacts with deep learning. We have internal displacement data for anticipatory action, and also applications of machine learning or causal inference as well to understand and model the problem of food insecurity and migrations. We also have a dedicated talk to deal with deep learning for wildfire danger forecasting, and also more, let's say, machine learning provocative talk and anomaly detection for attribution and forecasting. And do not forget about the last session, the panel session, that will comprise a couple of people from the first morning session and two from the afternoon session. And lo and behold, questions, of course, from you guys, but also from ChatGPT. It will be fun. Okay, so I think that without further ado, I think that our first speaker, Julia Martini, she's coming from the United Nations World Food Program, and she will speak us about early warning for food systems.
Yeah, while I was waiting my flight this morning, the New York Times actually gave me some help, because 2 days ago, this article was published, and which is titled "A New Kind of Disaster Aid: Pay People Cash Before Disaster Strikes." So while actually the article focuses on the type of humanitarian aid in cash, what I think is very interesting for this session is the second part of the title, which is "Before Disaster Strikes." So to pay people in cash before disaster strikes, we need to know if the disaster will strike. So the article cites two situations in which WFP gave some cash relief before disaster. The first one that is cited is in 2020 in Bangladesh. So it was projected that an area would be hit by extreme floods. So about 23,000 families were given some cash aid, and some external review, I think from Oxford University, checked that these people actually faced the challenges that were caused by the flood much better than who didn't receive it, not only in the short term, but also 3 months afterwards. The second example is related to Ethiopia, where it was forecasted that will be a long drought. So also in that case, there were some cash aid, and people used this money to buy food, medicines, and pay loans and food in general. So I think this shows that preventive action can be taken to avert or minimize impact of food crisis, which already I think shows the importance of the topic that becomes even more important if we think that we are facing the worst humanitarian crisis since World War II, that is driven by COVID-19, of course, the war in Ukraine, and climate crisis, plus various conflicts in the world. As of today, we estimate that there are about 345 million people that are facing food insecurity in 79 countries where WFP provide assistance and where data is available. I think that this number is even more interesting if we look just a few years back in time. If the slide goes. Thanks. Indeed, if we look at 2017, the numbers that were considered acute food insecure in the 51 countries where back then WFP was active was 24 million. With the onset of the pandemic and this development, the number reached 283 million, and which I think is even more surprising if it's that we look at the number of beneficiaries reached last year. So after also the onset of the conflict in Ukraine, you can see that is 160 million, is higher than the number that in 2019 was estimated as food insecure. So even if the number of beneficiaries for 97 million increased to 160, in 2022, WFP was not even able to reach half of the people that were estimated in food insecure. In such a problematic situation, we understand, I think, easily that food security monitoring and early warning systems are crucial. However, the standard face-to-face assessment for food security presents some criticalities. So I think all of us are very accustomed to have real-time data. Every time I get in the car in the morning, I check an app to see what's the fastest way to go to my work, to the office, which is the way that has less traffic. Or after going for a run, we check how we perform. So we are very used to have real-time data. However, in certain contexts, it's really difficult still to have real-time data. Face-to-face assessment for food security usually have the problem that are collected, for example, for a period of time, for a month, but then these are published 2 months later, so they can be already updated. Moreover, there is a problem about access. Face-to-face food security assessment, of course, are difficult to and dangerous to be conducted in areas of conflict. And we know that about 70% of the population that is food insecure lives in areas with conflict. Moreover, there are problems related to sensitivity. Classic food security assessment are conducted twice a year. So maybe we collect the data in January and then again in July. What happens in between, we don't know. Maybe the number that we collect in July are published in August, and the situation is it's already too late. We are already outdated. Moreover, traditional face-to-face security assessment are rarely leveraged to collect cross-sectoral data simultaneously, and this usually requires additional research or is difficult to triangulate data. To face all these challenges, about 10 years ago, WFP started what we call the real-time monitoring. So it's a system of data collection that is conducted remotely through live calls. In these calls, the same indicators for food security that are collected also through other assessment are collected in order to being able to validate and to compare these numbers. The numbers are usually representative on national and subnational level, and the data is automatically analyzed and published, so almost in real time. So the product that my team mainly works on is the hunger map, that we can consider as an integrated global hunger monitoring system, where we collect food security data, food security metrics, but also we try to triangulate with conflict, weather events, economic data, all the information that are considered to be the drivers of food insecurity. And we do this across nearly 90 countries. The hunger map is live, so I'm happy if then after this presentation you Google it. I will also share the link afterwards. So about these 90 countries, in some of them we collect data through calls, and this is for about 35 countries at the moment. And for all the others that are still of interest of WFP, the data is estimated through a predictive model that does daily estimates. That's what we call our nowcasting model. So we have 35 countries that are in real time, and 54 countries that at the moment are estimated through nowcasting. So real-time monitoring data, of course, without collecting this data, a lot of work couldn't be done. So once we collect this data, we can kind of play with this data and do a lot of things. The first thing that we do is a data triangulation and setup of alerting system. So based on certain threshold, we can define food security alerts and also alerts related to food security drivers, for example, climate. But also we can use it for machine learning applications. So one is the one that I just mentioned about nowcasting. So to do daily estimates of food security indicators, where actually we do not collect real-time data, but also for forecasting. So we do up to 90 days food security forecast in countries where the real-time monitoring data is collected. So just to give you a bit of a feeling about this alerting system, we define what could be a possible food crisis if we have a food security alert. So we see the numbers of food security deteriorating. And also we defined, based on certain threshold, a climate, an hazard, an economic, and a conflict alert. Plus, we also consider some sort of continuity criterion to smooth out some possible noise from this data. And we see that, of course, when there is an overlap of these, we see clear trends of deterioration. What I think maybe is even more interesting for this session is how we apply machine learning in this context. So as I mentioned, we have our nowcasting and forecasting models. So nowcasting is used to estimate the current levels of insufficient food consumption, and is used in countries where we do not have the real-time monitoring. We use a decision-based tree model. It's XGBoost, and is deployed in 52 countries. But we are also working on forecasting models where we estimate future levels of insufficient food consumption. We have results for 30, 60, and 90 days ahead. And this is using countries where actually we collect data every day. We have different methodology. for this, we are testing an approach based on reservoir computing, and previously we also tested something based also on XGBoost, so in the same algorithm that we use for nowcasting. And we are also trying some hierarchical Bayesian modeling, just to have multiple versions and to be able to compare and see the pros and cons of the different approach. For the forecasting, we have the pilot in 4 countries at the moment. And for both of these, the models, if you're interested, we also have some peer-reviewed papers, and I'm happy to share them after the session. So related to the nowcasting, we do estimates at first level administrative areas, so a subnational level, and we have 2 models actually. The one that estimates the prevalence of people with insufficient food consumption and the prevalence of people with crisis or above coping strategy. So these 2 different food insecurity indicators that measure 2 different dimensions. The predictive model that we are using at the moment is on production and is fit on data spanning 78 countries, collected along 17 years. We have, of course, a set of input variables that capture most recent state of the country, province for the different key drivers. And then we have daily estimates with a confidence interval that is based on a bootstrap approach. Okay. What maybe is interesting is to look a bit more in detail what are the input variables that we use. So as I mentioned, all of these are related to the key drivers of food insecurity. So we use the number of conflict-related fatalities. This comes from ACLED, it's an open data set. We use market prices. These are also data collected from WFP. And then we use some economic indicators, so as a food, headline inflation, and currency exchange, but also GDP. And also we use some climate variables. And in detail, I would like to show you what are the input variables that we use related to climate. So at the moment, we are using some historical and rainfall and NDVI values, but also we consider the anomalies, the 1 and the 3 months anomalies. We are trying to extend a bit the data set that we are using. So using also the seasonality calendar to grasp what is, in season, out of season, and also to just differentiate the rainfall and NDVI values for crop and pastures. Of course, if you have any suggestion, we are happy to receive them. For what concerns the forecasting, the input variables that we use are very similar. But as I mentioned before, if the nowcasting makes estimates daily, in this case, we look at the future, trying to make estimates 30, 60, and 90 days in advance. This, of course, would be ideal for any early warning system, any anticipatory action. We have this still in development, but we have the privilege to be working, of course, with the country offices that have knowledge of the context and their needs, so we can really work together and tweak our approach and our output. So one of the things that for me was actually a bit surprising is that for country offices per program, the number itself is not really interesting. If you say, the number of people that are food insecure is 72 or 73, it's not too interesting, but can be very interesting just if the estimate can be interpreted as categorical. So what is actually happening is a sharp increase, is decreasing. So this would be good enough. So, we can sometimes focus on something different than you would maybe be very interested in academia, because maybe you are interested in looking at the mean absolute error goes below 1%, while actually this is not super relevant, but it's more important that you never miss the correct trend. So of course, interpreting the results as categorical can have certain benefits. So as I said, we just look at the direction of change rather than the magnitude. It can be easier to interpret for people that are not super technical. I also think there are some kind of cons, that is, at a certain point, you need to introduce a threshold. So what is sharply increasing or sharply decreasing? Why is stable? What is the range? So this is something that, of course, comes as a con. And yeah, I would like to show you an example of how the forecasting model at the moment performs for Nigeria. So this is one of the 4 countries where we are piloting the model. And you can see in the top 3 plots, we have the dates, and the prevalence. So we always estimate the prevalence. So it's always a number between 0 and 1 because it's the percentage of people that are food insecure. The blue points is the data, the collected data, so the real-time monitoring data. Of course, the model was trained until the prediction started, and then we make the predictions. So you can see that for especially Adamawa and Yobe, the predictions are pretty good and all pretty completely in the confidence interval for the 30 days ahead. And on average, in this case, the error was about 4%. We have certain limitations, of course, with this approach. So the model relies on a high amount of data and should be of also high quality because, of course, very noisy data would influence the model. The model cannot react to influences outside the input data. It can be trivial, but if in the input variable we don't consider certain things that are very relevant, this will never have an influence in the model. The time horizon is still limited because at the moment we have good predictions for what concerns the 30 days forecast, but for the 60 and 90 days is still too unreliable. And of course, we always have unpredictable factors that we cannot take into account. Yeah, I've been working in the team for about 3 years, and of course I learn a lot, and I think that these are very crucial aspects that we should consider when working in this context. So the expertise from the field is crucial. I'm based in Rome and I miss a lot of course, I don't have the knowledge of someone in the country office, food security experts that know the context, know a lot of things that as a modeler or as a data scientist, you might miss. So leveraging our experience is very crucial. Sharing and having contact with the country office for us was very valuable. Also just to identify the relevant input variables and actually evaluating if the results are good enough. The drivers of food insecurity are of course somehow general, but they're also very specific. So for example, we noticed that including in certain countries, the period of Ramadan had a huge impact on the performances. So this is also something to be taken into account. The quality of the data that we collect, of course, has a huge impact on the model. I mean, this is pretty trivial to say, but when you have real-time data coming in every day with the hundreds of thousands of calls done every day, you need really to set a data quality system that would flag any possible issue with operators, bias, weighting methodology. So this is something very important. And of course, the extensive consultation with stakeholders is an imperative to realize what actually is needed in the sector. As a next step, we are working on multiple fronts, of course, including additional data sources that can capture better, especially small changes, small variations. Improving the model, as I mentioned, especially for the forecasting, we are trying to have also multiple versions and with different tweaks to understand what makes more sense to have it in production, to triangulate the output with different data, and of course to collaborate with the institutes of research, universities, can bring a lot of values. We are also very happy to provide technical support and capacity transfer to enlarge the work done in the field. And yeah, thank you.
Thanks very much. We have plenty of time actually for questions and discussion. No, come on, it's beautiful. So, okay, I see already Nuno, Marcus, okay. And then there's someone else, yeah. Okay,
Thanks a lot. I have actually one technical and one general question. You basically showed the evolution of the food insecurity, and then you mentioned these different categories, which seem to be more like the first derivative of the curve. You said increasing, decreasing. Did I misunderstand it, or?
What we actually do, we have a regression problem. So the output is just between 0 and 1, and then we say, let me go to the slide so maybe it's easier. Okay, yeah. So we just do a normal regression. So our output is still between 0 and 1, but then we classify the output based on the variation.
Yeah, that I understand the categories, but I don't understand why the upper one is sharply increasing. Let's say if the curve would go down in the red area, then it's not increasing anymore. Or
yeah, no, that's correct. Yeah.
So it's not
just based on on the situation at that point. Sorry, of course, this will be just based from that point. The reference point now, what is it, the November?
From that reference point, it's going up. Okay.
Yeah, so from the reference point,
then
sorry.
I understand. No, good. I understand. And the other question I had was more general. So what do you actually think is really the limiting factor in being kind of successful, basically from the data? Well, either to the prediction. I mean, you commented on that, but also on being successful operationally. Yes, exactly.
Yeah. So first of all, the quality of the data, of course, like from very practical point of view, data collection is very expensive. So in this case, we have data collection at the moment in place for 35 countries for the forecasting. So you need to collect data that is representative, for example, at subnational level. A lot of times we get requests for having something representative of admin 2 level. So it means really enlarging the sample size. So of course, a cost to have very thorough data collection. There is, I think, still a bit of skepticism. So that's why I think our effort in having peer-reviewed papers, having contact with the country office can help, because there is a lot of times machine learning is seen as a black box. So that is also something I didn't mention it, but we worked on, especially for the nowcasting, to something that we call like demystification. So how to interpret the estimates, why there is a change between today and 3 days ago, why there is this jump, so which input variable caused it. So I think try to open a bit the black box to the stakeholders, especially who is not very technical. So I think this is the other challenge, a bit to make it understandable and interpretable to everyone. Yeah.
Thank you so much for the talk. I'm really happy that you touched this aspect of explainability now. My question is related to your first slide, that is an intervention. And I'm actually wondering if or how you are seeing this perspective of an intervention to have a change in the index, like from a modeling, but also from an experimental point of view. It seems that you have a very good setup and actually maybe data that can allow you to. Especially because you have different tools. I'm sorry, you have different tools in which you can intervene. Like cache is one of them, but you could have many that would speak then to the actual variables that are causing the very interesting.
I'm sorry, I don't have a slide, but what we do for the nowcasting model, so as I mentioned, it's a XGBoost model. We use the SHAP values, and I know there are a lot of cons of using the SHAP values, but I think what is pretty effective is that using the difference of SHAP values. So we take the estimates for today, we see the SHAP values, which is just the difference from the baseline of the null prediction, and then we do the difference with the SHAP values of 3 days before, so the moment in which we want to compare. And at this point, you remove the baseline and you just see the impact of an input variable. Of course, I mean, this is strongly driven by how the model is fit and by the methodology, but we are having a fully data-driven approach in this case. So, I mean, this explains why the model predicts that. If this is actually the reason. So at the moment, we haven't done, but for the nowcasting at least. But as I was mentioning, we are having a partnership with the LSE University, and to explore the use also of Bayesian, the Gaussian process regression. So to have a fully statistical model which allows for explainability, because yeah, sounds good.
Peter Spencer. Yes, thanks for the talk. It was very interesting and very impressive also to see the performance of your models. I was wondering if you have these nowcasting results now in the map, are they, or what's your experience? Are they being used in decision making or in the processes the same way as the actual real-time data, or is there large differences?
So far, everyone was from Vienna. But you can. Okay, thanks. So any further questions, curiosities, remarks? Philip, please.
I already said who I am. Very interesting talk. A comment and a question. So one of your indicators on your warning charts, you say climate in one of these bits. I think what you probably mostly mean by that is weather. So there's the distinction between weather and climate, because I think there's a possible confusion of the people looking at it, thinking it's attributed to climate change yet, which it wouldn't be. So I wonder if it would make sense to tweak that, because the attribution problem is super interesting, but it's probably not done yet. The other question is, obviously it's a super interesting problem, but also a hard problem, because you probably have massive distribution shifts. So if climate is changing, then your model would be out of training. And I guess the probably bigger changes are just land use changes, where people just mess around with the landscape. What are you planning to do about it? Or is it something, how do we get away with it?
And it is more related to climate. So we, of course, rely on their support. I'm not, and we are not in general my team, like say, climate experts. So to be discussed, I would say. But happy to have a conversation on this and also get your input maybe on this.
Interesting.
Yeah, thank you.
Please.
Hi, Claire from Jena. I'm wondering, you deal with a lot of uncertainty in your noisy data, and you are predicting something who's uncertain. How do you deal with that? Yeah, both the noise that in the data that you are collecting, and you are predicting something. I mean, if I well understood, with stakeholder is something really important. Sorry, with the stakeholder, the uncertainty is really important.
Introducing the confidence interval is something that yeah, I was really pushing to, because I think it's important to be done, but it can create confusion. It depends on the stakeholder, I would say. But for example, in the moment that you have an estimate with a confidence interval and you see that your real-time data falls within the confidence interval, this usually helps also in understanding and validating somehow and getting accepted. If you just give an estimate and you see the difference without knowing if you are inside, outside, at which point of the confidence interval, yeah, this is usually not that much informative. So related to the noise, let's say, in the quality of the data that we collect, we are trying to set up some sort of automatic data quality system. At the moment, we have part of our team that checks the data. We check the operator. We might need to retrain the operators. So, for example, how questions are asked. We have a weighting methodology that can differ for country to country. So this is something that we need kind of to monitor constantly, how the data is going, how the quality of the calls. So I have colleagues that listen to the calls, to the recording, also to be sure that the questions are asked properly. What we do, so for example, for the nowcasting, we don't use all the data points. So for example, for the real-time monitoring, we sample it. We do some sort of sampling to try to reduce also the imbalance in the data set, because the countries, the real-time monitoring started at different time in different moments in time. So we also, sorry, have a very unbalanced data set. So we do some sampling.
Question out there? Christian?
Hey, everyone. Christian here, also from Jena, Max Planck. I have a question regarding to the drivers and what to me seems the most important driver looking at this hunger map that you showed before seems to be probably conflict and political instability. How difficult is it to forecast those?
Very interesting, because the conflict variables is the one with which we are struggling the most, in the sense that we have ACLED, which is a pretty good data source, has a big coverage in terms of country, as a daily resolution. They are updated, let's say, with the 1 week of delay. So this is pretty good, but the struggle came to how define the input variable. So for the XGBoost model, of course, we need to define the input variables. We don't use just the raw time series. So which subset of conflict to be used, because I'm not sure if you are familiar with this data set, but the conflicts are classified in riots, battles, so different categories. So shall we use all of them, just some subset? What do you use? The number of events, the number of fatalities, in which time span do you aggregate? So we really worked hard on this, and what we saw with another project we carried on the side, it was that if you could filter the conflicts for food-related conflicts, so for example, conflicts that reduce the access to markets, for example, or that destroy fields, crop fields, they have higher correlation. But actually, a bit counterintuitively from what you would expect us from literature, the input variables related to conflicts is one of the one that has the least importance in the model. So this is for us something which we are trying to work on to also get it, to improve.
Thanks very much. I think that it is time to move to the next presentation. Thanks very much. Let's thank the speaker again. So now it's time for a dual presentation. Are you guys doing it together? No, are you doing it? Okay. So now we are moving to forecasting drought impacts with deep learning. By Vitus Benson from Max Planck Institute of Biochemistry in Vienna.
Tracing slope, etc. The weather surface interactions, they can be quite complex. So we've seen in Marco's slide already that the same weather event can lead to different impact on the land surface. And then there's also a lot of like memory effects. So it actually matters how was the previous season for the current season. Yeah, but now we have big data available. So we have all these massive amounts of Earth observation data and climate data or weather data. So maybe we can actually use deep learning as a solution here. Good. So what am I talking about? The data. So this new data set from Africa. We created, colleague created this very nice animation where you can see that we sampled really a lot of locations, sort of stratified by land cover class. All over Africa is 50,000 different locations. And for each of these, next slide. For each of these locations, I'm going to show you how one location looks like. What if you use the we are stuck in the matrix, apparently.
It's a good animation. It's nice that we see it a few times.
Yes, let's go. Okay, so each of these locations, for each of these locations, we create a mini cube that is contained of both very coarse resolution weather variables such as precipitation, temperature, sea level pressure, and actually some more in the newest version. And then also an elevation model. And then if you play the animation, you see our target data, which is this time series of NDVI images or satellite images that really goes through time, and we will use that to take some part as context and to predict the other part. So let's do that with one machine learning model. So on the bottom left, you see a context period data sample, so a couple of satellite images from one location here that contains agricultural fields. Then on the bottom right, you have what we want to predict, which is the target. So it's, in this case, 100 days captured in this 5-daily NDVI that just starts after our context period. Then we have a machine learning model, more details in a bit, that basically does a prediction and actually looks fairly well. So it seems to, in this case, predict a decrease in NDVI over time. If you compare spatial patterns, and it's actually capturing them quite well, and only in a certain, when it's really turning from high NDVI to low NDVI, then maybe there is some uncertainty there. And if you would aggregate this to like the whole cutout, then you look at the red line and compare it with the blue, the black circles, then you can see how our model is nicely capturing the mean NDVI. And also, if you look at the blue line, that is just a particular pixel, which is in the top left of this cutout, sort of, then that is actually also quite nicely captured. So we capture both the variability and the mean in such an image. Of course, now you could say this is cherry picked, and this is, of course, very true to some regard. So what we want to do is we want to do a quantitative comparison. So for that, we first need some baselines. So the most naive baseline is maybe the persistence baseline. You say, okay, maybe the vegetation is just going to stay the same for our full target period. And in this outperformance score, we can go into details later. This persistence metric actually has a very low score of only 24%. Then we put out a challenge in 2021, actually, which was the EarthNet 2021 challenge. And there, the leading model right now on the leaderboard is the Earthformer. But actually, if we evaluate it now on NDVI, we realize it only has a 46% outperformance, which is not convincing, because what is our true strong baseline is the climatology. So we know that vegetation follows a strong seasonal cycle. So every year it sort of is repeating the phenology, the green up, only with a variation due to climate primarily. Yeah, and we need a fake climatology here. It's a technical detail, but Sentinel-2 image is only there since 2017. So I guess real climate people would not call this climatology because it's only 5 years and not 30. But it gets close to it. Then we compared to a time series model. So you might know, if you're coming from business, that there is this Facebook profit model, which is used to forecast, for instance, sales in online businesses, etc. And there it's very useful. And you might think maybe our task of NDVI forecasting is sort of similar. Doesn't matter so much what is around, just a single pixel. And actually it does better than the climatology if we run this local time series model here. But if we run a model that can take spatial context, and this is this conv LSTM, so conv stands for convolutional, LSTM stands for long short-term memory. So it has both recurrency in there and sort of spatial capturing of features, then that one is really a lot better. And in fact, we compared then to two state-of-the-art models. One was the PRED-RNN, which is #1 on one video prediction benchmark, KTH. And then the ZimVP, which used to be #1, but then I checked again yesterday and now it's #2 on this other video prediction benchmark. But actually, for our case here, for the Earth science task, for vegetation forecasting, they don't outperform this conv-LSTM, which is sort of maybe it's a little bit of an older model. It comes from 2017 already, but it seems to be more robust. Okay, so we've assessed that the conv-LSTM is a fairly good model. The best we have right now. So what does it do? We want to look at some weather scenarios. In this case, this is a place in Greece, so central Greece. And we made this scenario where you have different rainfall and different temperature. So from left to right is increasing rainfall, from top to bottom is increasing temperature. And then we did sort of a forecast of the green up season. We took extreme scenarios here. So what you see on the images is very extreme in the response, but this is on purpose. So it's not very realistic, but it's on purpose to better understand the model. And you can see nicely there is this diagonal gradient. So of course, it's better for the green up if it's not too hot and if there is enough rainfall. But then you also see some local patterns. For instance, really the north-facing slope that is going to this northern arm of the river is always still even in the very extreme scenarios, less affected by the heat or by the drought than south-facing slopes. Okay, and these sorts of scenarios is just one example. When we look forward, and the goal here is really to go into this anticipatory action that we've already heard about. So here I borrowed a slide from, or a figure from OCHA. So the idea there is, if you have early warning signs, then maybe you can do something before a disaster strikes. And in that way, you really reduce the impact that the disaster has on livelihoods. And our idea here would be to use, okay, we say we have the seasonal weather forecast in samples, maybe even from AI models, like we've seen this morning. And then we could use them to downscale this into vegetation impact scenarios. And then maybe they could potentially be a trigger. And this is really something we would also like to get into a discussion about, a sort of, so we can get community scale triggers for anticipatory action. And then I guess those experts from the anticipatory action community would then have to say what to do with them. But for instance, there could be the distribution of drought resistant seeds before a lean season as one example. Okay, so from our side, what are we doing in the next steps, or currently actually? So we are continuing work actually in the Deep Cube Horizon 2020 project on drought impacts in Africa. So there really the goal is to understand this drought in Africa on the big data set that we have now available. Then in another project from ESA, actually, we are looking at, or Melanie, who's also in the room, is looking at compound extremes globally, so heat and drought at the same time. You are also welcome to join the efforts, as well as the people online are. Our data sets are open data and the models are open source. We have Python libraries. You can just try to access the data there, and of course send us an email if there's any questions. And you can also join the discussion. We are continuing the discussion at another event at the World Climate Research Program Open Science Conference in Kigali in Rwanda in October. So it's a little bit sorry for the little bit of advertisement here, but the idea there is to really understand how artificial intelligence can be used for climate risk mitigation and really get into the dialogue. It's jointly organized with the German Red Cross and the Croix Rouge Malagasy. Okay, so in summary, what have we seen? We have seen the EarthNet concept, which is predicting impacts on vegetation from weather. We have some data sets ready for Europe. It's EarthNet 2021, already a little bit older. For Africa, it's EarthNet 2023. We have the state-of-the-art model, which is the ConfLSTM. It outperforms a strong climatology baseline. It captures the land surface response to diverse weather scenarios. Of course, there's also some caveats, and for sure there is room for improvement. And our next steps are to study climate extremes and to discuss anticipatory action. Thank you very much. I'm allowed to show a visualization from our colleague Lazaro to finish, and to leave you with some nice impressions. Thank you.
Thanks so much, Vitus, for the very nice talk, very visual. Are we expecting something to happen with this? No. I don't know. I was just curious, man. Yeah, we have some time for questions and curiosities, remarks, whatever. Okay, there.
Yes, thank you very much for the question, and very interesting. I'm not sure how to directly quickly apply our models. We do check on forests. For instance, the example in Greece was on forests. So I think they do show some performance there, and you might use them to understand better how your forests would react under certain seasonal weather scenarios. I don't know if you could give some more details about your project, then maybe we can discuss. Maybe later, yeah, it's nice. Yeah. Yes, interesting aspect. I mean, it would be probably very rarely seen on satellite images. I think compared to vegetation, the buildings are changing far less. So we would really have to search in this big space on the whole Earth surface for the right cases where to look. I know there is some people who work with satellite imagery on sort of change detection and even change prediction. Or that might also be hard to say. I don't know.
Yeah, Joachim Denzler from Jena as well. So I'm curious, did you somehow make the comparison with the Facebook thing fair in terms that you not just looked at the individual point prediction, but did some smoothing to make it more consistent over the area? So it could be just smoothing or even a micro-random field that tries to make it more consistent with spatial.
Yeah, good point. I brushed a little bit over the details. So actually, I would say the comparison is unfair towards the deep learning models because the Facebook Prophet, we give it a very long context time series. So it learns on the full 5 years of data for each individual location. So it's also fairly expensive to run. Whereas our deep learning models, they only take a very short context and then predict. We didn't do any spatial smoothing or so. I'm not sure that that would drastically change the performance, but maybe it would. So we could check. This is post hoc, right? So we can just take the predictions and it's a good idea.
Philip, please.
I was wondering, okay, disclosure, I never liked NDVI much. Because it's an index derived because that's what you can measure. And it's sort of always sort of a bit frustrating. So I was wondering, could be the even more interesting question to put to yourself to predict something you like or something that's really interesting, like the full vegetation, more about the vegetation, and then derive NDVI from it and just evaluate from it. Or is this the first step in that direction, or are we really interested in predicting NDVI? Because
yes, it's a fair point. I mean, luckily NDVI correlates at least to a certain extent with many of the interesting variables, right? So the aspect here is that we have a lot of observations of NDVI. We not necessarily have a lot of observations of, say, GPP or so gross primary productivity or some more carbon-related variables, or also of food security impacts of food prices and so on. You wouldn't have them at the granularity. And we didn't do the step yet, but maybe the hope is that you could take our NDVI predictions, feed them into another model, and then turns them into something even more physical, or yeah, I don't know. Or the other direction that you maybe propose is to do some sort of hybrid modeling, right? That
sure.
we predict
ecosystem
quantities, and from that,
and with this as one of the outputs.
I would just maybe comment on the note that's totally correct, but actually also, I mean, one could also maybe predict the individual channels first, and that's actually what Chris did for the landscape. But then there are also advantages in predicting indices, no? Because the channels also depend on the BRDF basically, and so on and so forth. And so if an index is a little bit more stable, so it's, if you want, it's first case, and then from there one can either go for other indices, so kind of as a proof of concept, and one can go to other indices, or what it is also said, I think the goal should be really to have then a prediction step towards tangible quantities, like how much biomass is there, how much carbon has been taken up, how much harvest is expected, and so on. So that, but I think our idea is basically that once we can predict these complex things at the pixel level, the mapping from there to other properties may be simpler.
Yes, one more question on the back. Yep.
Yeah. You triangulate your work around like vegetation, precipitation, and temperature. did you think to consider like any soil moisture data or water body data?
Yes, very good point. We are sort of treating soil moisture as a latent variable that we don't observe, which is of course not true, because you can observe it to some degree, and then maybe that would help. We've so far tried to navigate around it because it may also cause problems, but I guess especially for droughts at some point we will have to really engage there. Do you have experience with soil moisture? Or?
Yeah, we can discuss it later. And I think for water body, you have like this new satellite that has been launched by NASA last year. And I think it's performing quite well to identify like water stream and water body. So it can be a good complement to your model.
Yeah, thanks.
More questions? I have kind of a curiosity because you were starting this story with the different accuracies with the different bars, right? In the bar chart. And at some point you said something like, okay, and this is seasonality, this is a model, let's say, right? And apparently when you introduce like, you know, more features, either spatial or temporal features in this common LSTM, everything becomes like to flourish and become like more accurate in a way, no? But I was really curious about the domain shift or the covariance shift, right? Because in a way you're probably alleviating the problem of, you know, different distributions along the way with this more sophisticated, I mean, compensating with the spatial or temporal features, no? But the common LSTM doesn't know anything about that, right? So are you expecting kind of an improvement when you try to use like, I don't know, other techniques from domain adaptation or transfer learning or these kind of things? Because apparently that's the problem, right? It looks like, no?
It's a very good point. So I think I don't know how many of you know about distribution shifts, but the point is that of course we might want to apply the model somewhere where we didn't train it on, and then can it really do generalize to this different sort of circumstances? And we try to alleviate this mostly by training it on as many locations as possible, and especially we wouldn't directly apply the model that we train in Europe, for instance, or in Africa, in South America. Rather, we would collect another data set for South America and then train a model there. I guess there is techniques that you could maybe use, but I'm not sure the distribution shifts are so strong that it is really going to give a lot of benefits.
Welcome back, everyone. Let's start now with Maria Teresa from IDMC. Yeah, she will be talking about potential of internal displacement data for anticipatory action. Thanks for coming.
Thank you. Thank you, and hello, everyone. So I would like to introduce my presentation by saying that the angle that I'm going to present is slightly different from what has been presented before, because more than presenting the application of the work that we do and the data that we have for modeling, I'm going to present the data in itself and the potential that it has in some projects that we have and some improvements that we are planning to implement in our data. And the context of this presentation and the title is From Hazards to Impacts, presenting the potential of internal displacement data for anticipatory action, just for that. Because first I would like to walk you through the work that we do in IDMC. You know that in 2022, the global average temperature was the 6th highest ever recorded since records started. And the impact of, well, different weather-related events and geophysical events have different impacts that were negative for different populations, causing loss of lives, several livelihoods were impacted. The economic losses estimated from several disasters that occurred in 2022 were estimated to be around more than 200 billion US dollars. And different disasters occur all around the world, having different types of impacts. For example, in Australia, extreme rain and flooding affected parts of the eastern regions of the country, displacing thousands of people, like the second highest figure in terms of displacement ever recorded for this country. Then if we move to another part of the world, if we go to Madagascar, the last year was the first time since 1988 where 3 different storms impacted the country, creating several floods that impacted areas that already were affected by droughts in years before in the same year. Then even in Europe, in France, we had particularly warm and high temperatures that fuel severe wildfires that displace also thousands of people. And in the US and Cuba, the tropical storm Ian landed in Florida and passed by Cuba, shutting down all the grid network in the country and affecting a lot of people and displacing a lot of people in the US. I'm starting my presentation with this global overview, just to say that internal displacement is a phenomenon that happens all over the world. And part of the work that we do at the Internal Displacement Monitoring Center is to basically collect and harmonize all the data and information that is collected worldwide. IDMC was first established as a project in 1998, and since then it has become a reference in the only global repository of harmonized and consistent data on internal displacement resulting from disasters and situations of conflict and violence. Basically, our organization in itself was created as part of a call from UN that was calling for more comprehensive and coherent data on internal displacement. So we responded, we created our global database, and since then our global database also has been recognized and supported by different UN resolutions. This map that you can see right now illustrates all the population movements triggered by disasters that we recorded the last year in IDMC. Overall, in our database, we monitor, we identify more than 2,300 disasters that occur in 148 different countries and territories, and that overall trigger 32.6 million of internal displacements. When I talk about internal displacements, I'm talking about population movements, because in different contexts, in different parts of the world, one person can be displaced multiple times by different disasters. A good example was the first one that I presented in Madagascar, where in one single month, 3 different storms landed in some regions of the country, affecting the same population. And when we have an overview of all the disasters that trigger displacement, we can see the 98% of the disasters that trigger displacement are weather related. This covers floods, landslides, storms, and the rest of the displacements are triggered by geophysical events like earthquakes, for example. And that was the overview that I wanted to give you about the work that we do, who we are, and why do we collect the data. And now I would like to present you more or less the workflow that we have in IDMC, and I would like to show you how the data is collected. So in IDMC, we have a team that is called the monitoring team. That is a group of experts. There is a team that is composed, by a group of experts that find and collect data all around the world. We are not in the field. We are not an operational agency. Therefore, we are based in Geneva. And what we do is we are a data center. We are data curators, and we compile all the data and evidence that is available out there. And for that, we use different methods to scan the information whenever it's available. Once that the monitoring team has identified a situation of internal displacement, this information is harmonized and is curated. Data on internal displacement is collected by different actors. Governments have some databases, some governments collect the data. In other situations, United Nations is deployed to different countries to respond to different crises, and they collect the data. In other contexts, the NGOs or local organizations collect data on internally displaced people. When we talk about internally displaced people, we talk about persons that have been forced to leave their houses or their habitual places of residence as a consequence or to prevent any negative impact created by disasters or by conflict or violence. Therefore, as you can imagine, the data on internal displacement is composed by different indicators, different terminologies that change very much depending on the context and depending on the country. And basically the work that we do is to harmonize all this data and this information that is published and is accessible worldwide. Whenever data is not available coming from governments, NGOs, or other what we call authoritative sources, what we do is we also implement different media monitoring systems in place to try to fill some data gaps. And all this information ends up in our global database, in our global repository, and it goes through different processes and workflows that clean the data and different steps of the process of the data collection and compilation. And at the end, we have two major data-driven products. We have a lot of other type of research products and publications, but the main data products that we have are the annual reports coming from the Global Internal Displacement Database. Basically, this data is the curated, validated data set that we publish every year that contains all the information and all the evidence of internal displacement that we have found worldwide. And then we have a second data set that is called internal displacement updates. That is, this data set is composed for preliminary data that hasn't gone through different QA and validation processes. But why this data set is important and why I wanted to present this data set today to you is because this data set, what it has is the first estimate of the impact of different disasters worldwide. So before the different teams collect and assess the situation of internal displacement, and we can have a good overview of how many people have been displaced from their houses or their places of residence to a disaster, we need to have an alert that tells us there has been a weather-related event or geophysical event, and it has triggered a displacement. And why is this important? It's because this type of information needs to be fed back to different governments and different agencies that can respond and can assist the people that are affected. Because internal displacement can happen for a short period of time or for a long period of time with lasting impacts in the livelihood of people. So let me go back to the data sets that I just described. The first data set that I presented is the Global Internal Displacement data set that we call the GID. This data set started to be published in 2008, and it has identified more than 12,500 disaster-related displacement events. The database also contains data on conflict situations, but for the purposes of this presentation, I'm just focusing on disasters. All this data has been collected from 205 countries and territories, and it covers 23 different hazard types, subtypes, sorry. And as I mentioned before, the Global Internal Displacement Database has data that has been validated and curated, meaning that the team that collects the data also takes the time to contact local partners, local organizations that collect the primary data, and they try to validate and triangulate the information that we publish. Then the data set is publicly available, is in our website. It has, for disasters, it has information disaggregated by event, by country, and by type of hazard. And the second data set that I presented, that is the internal displacement updates, it has the following characteristics. First of all, it's updated in daily basis. As soon as our analysts identify a situation of internal displacement, they publish the data already, the preliminary estimates into our website. So it's not near real-time data, but it's the closest that you can get to that in terms of internal displacement. And that's part of the added value of this data set for early action and early warning systems. And since the data set was published in 2018, it has covered 12,000 disaster displacement updates in 195 countries and territories. And the data is published, as I mentioned before, on a daily basis. We are trying to make our data open access and as accessible as possible. But for the moment, just the first data set that I presented is available on our website. The second data set is available upon request, but we are working very hard to make this data available for everyone. Now, the next part of my presentation is about how can this data contribute to early action. So when we think about hazard alert systems or weather forecasting, we have strong systems in place. We have Earth observation systems that allow us to have almost near real-time monitoring of what happens all over the world. But when we think about the impacts that these weather or geophysical events could have on people, the data becomes more scarce, more dispersed, and it's not updated with the same frequency that data coming from air observations, for example. Therefore, the data that we provide, at least with internal displacement updates, is the first and the fastest piece of information that you can get that is harmonized at global level, that can give you an idea of the intensity of certain disasters and the human impact of these disasters. Some of the experiments that we have been running in IDMC with partnerships with different universities is to try to see how our data can be used, and our different data sets that we have can be used for forecasting of the impact of disasters, of hazards, sorry. And this is a gift that comes from a paper and a publication that we had with the ETH in Zurich, where we were trying to use our data along with data coming from the European Center for Mid-Range Weather Forecast to try to forecast what would be the impact of tropical storms. This example is in Fiji. But we have been running this type of experiments in different countries, and we are trying to improve the data sets that we provide in order to use them better for this type of applications. Then we also have been exploring with different partnerships with different universities, the use of our data for different machine learning models, the prediction, and for example, with the University of Valencia, the presentation that is coming after me, that is linked with the use of our data for causal models. Now, as you know, displacement data, along with other relevant data, it's needed in order to feed these models and in order to forecast the impact of, for example, a disaster. Along just our data set, with one single data set, sorry, we cannot build a model that can be very useful, but we need additional data sets, sorry. Nonetheless, what I want to highlight today is the importance of our data set. And now I'm going to talk a little bit about what are the improvements that we are planning to implement in our data set in order to make it more usable, more interoperable, and therefore more actionable. So for the moment, we are working on improving the harmonization and standardization of our data. We are doing an historical data revision to guarantee that our data is comparable along the time. We are increasing the interoperability by adding additional columns of information when you download our data, so you can harmonize or compare the impact data that is coming from the internal displacement monitoring center from us with hazard data. As you know, the different hazards have different codings, different unique identifiers, and sometimes it's very difficult to follow up on the impact of a hazard, because the impact data not necessarily keeps track of the same coding mechanisms as the hazard data or the the weather the weather related data. Therefore, we are trying to include this type of information in our data set. So for our data users, it's going to be easier to identify an event from a disaster or hazard alert system, and then to identify the impact from our database. And that's the glide number. We are also including additional pieces of information and increasing the disaggregation of our data, because so far, if you go out to our data set, most of the information is aggregated at country level, but we do have the information disaggregated at subnational level. So we are working on that. We are also working on implementing several automated and semi-automated quality control mechanisms to guarantee the highest standards of quality in our data as much as we can. And we are also harmonizing the location codes of our data. So our data can be matched with humanitarian data sets and also with weather-related hazard alert systems. And we are also incorporated additional metadata that is linked with the information on internal displacement. And to wrap up my presentation, I wanted to present this graphic to you. Basically, this shows the history of internal displacement data. We were created as a project, as I said before, in 1998, and we were created before UN even had guiding principles or a document that defined what was an internal displaced person. Therefore, the importance of having data on the topic, because the data that we had was also important for the adoption or the creation of different policies and actions that came after the creation of the database. What is important for you right now is to pay attention to the orange and the blue lines. The blue line shows since all the time span that we have for disaster-related data, and the orange line shows you for how long we have been monitoring conflict data. As you can see, we started the monitoring in our database of disaster-related internal displacement in 2008. And the data is disaggregated just since 2016. So therefore, this is what this graph shows as well, is the importance of the work that we are doing regarding the historical data revision and making sure that our data set, since we started recording it in our database 25 years ago, is going to be comparable and can be used for different seasonability and time series analysis. So what is the end of all this work and this presentation is that what we are trying to do is that we are trying to go from just publishing data and being a data repository, also to try to see how we can use the data that we have for anticipatory action, transforming our data also in information that can support different stakeholders. That is my presentation. It was focused on the work that we do, the data that we have. And I would like to close by saying that we are doing a lot of work improving the quality of our data. We are very open to have partnerships and to improve the quality of our database, and also to get your feedback as users of our data. Because what we would like to do and we would like to achieve eventually is to have a data set that is useful and actionable for different purposes, including the modeling. So if you are interested in using our data, please use it. Go to our website. You can contact me, and we are going to be happy to receive your feedback and to improve our data and publications. Thank you very much for your time. I think that we can pass to questions.
Thanks very much, Maria Teresa. We have some time for questions. Anyone? Please, Manolis. Please introduce yourself and then, yep.
Okay. Yeah, I can do everything. Yes. Hello, I'm Manolis Koubarakis from the University of Athens. Thanks for the nice presentation. My question is very simple. I would like to ask you, what other kinds of data sources are relevant to be used together with your data for the purposes that you described in your presentation?
Well, that's a very good question. It's kind of complex. It depends a lot on the type of analysis that you would like to do. For example, there are different models that have been built by different organizations to try to estimate and forecast how many people could be displaced due to conflict and disasters. Related to conflict, there are different indicators that can cover human rights situation, the food security in different contexts. One of the best models that I'm aware of has 120 different indicators that go from socioeconomic indicators to human rights indicators, including our data set. Now, to forecast the impact of disasters, basically what we have been doing in IDMC when we try to estimate the risk of displacement is to use 3 different components, like the exposure, that's our data, how many people can be exposed to the hazard data, for that there are many good different data sources, and then the vulnerability. And this is the part that is interesting and complex, because you can have internal displacement with a disaster that is not, it doesn't have a high intensity, but it has a high human impact, because it has the location where the hazard happened or the disaster happened was very vulnerable. And the indicators of vulnerability, at least if you want to do an analysis at global level, change very much, because the vulnerability that citizens in Florida, in the US have, is not the same vulnerability as the population affected by the tropical storms in Madagascar has. So I cannot list the indicators that you can use, but I just wanted to highlight the complexity of the phenomenon and the analysis. Do you have more questions?
Yes. Please go ahead.
Yeah, just to react to the last point you mentioned now, it's how do you build like a kind of global solution, but that fit to the local context?
Yeah, it's quite complicated, but can be achieved nonetheless. What we have been trying to do, and we did in IDMC, is to tackle, we don't want to forecast internal displacement in itself, but what we want to do is to raise awareness, because there are a lot of governments that don't have any mechanism in place, any response plan to address internal displacement. Therefore, what we can do is to try to estimate and to illustrate what could be the risk of displacement. And for that, what we did is some probabilistic analysis to try to estimate what is the probability of people being displaced in average based on historical data. And for that, we use our data set and additional data sets of loss and damage, like how many houses were destroyed after a disaster, and that type of data. And we estimated what would be the probability of people being displaced due to flood, tropical storms, storm surge, and I'm missing one more type of disaster hazard. But yeah, the result of our analysis or a model is basically to have a score that is an average and an average estimate of the potential number of people being displaced with a certain probability of occurrence. Someone else has more questions?
I have one, because you in the last few minutes of your presentation, you mentioned quality control.
Yes.
And I was really curious about uncertainty quantification, because data is coming from different sources with potentially different protocols, different communities collecting data. And data with uncertainty quantification is, well, it's useful, but yeah, it's a bit controversial what you do afterwards with that, right?
Yeah.
So what are the things that you are actually doing along those lines? I mean, on quantify uncertainty or quality control? I would like to know a bit more about that.
Okay, thank you. We do the quality control during different steps of the process of compiling the data. One of the first steps of quality control that we have is the analysis of the data source. different countries have different data ecosystems and data landscapes. And what we do basically is to try to understand what is the data landscape in the country. Then we try to compare what are the different characteristics and the methodologies used to collect the data. Then we compare the methodologies, we compare as well the resolution of the data in time and in space to try to identify what is the best estimate. And based on that, we assign a level of reliability to the source of our data. So we can say in this country, this source has higher reliability than this other source. And this is the first score that we have, but it's not accessible to the public yet, but we are working on making it public. Then we have another, several rounds of assessment of the data that go from automatic error detection to identify duplicates, to do basically a simple data analysis that any data scientist will do when they use a data set, to try to identify anomalies, outliers in the data, and then we try to verify if indeed is an outlier or if it is an error in the system. Then what we have another layer of quality control, that is when our analysts contact the people collecting the primary data and other organizations to try to see if the data that we are publishing has triangulation, it's comparable with other data sets, and if the context of the data makes sense. And we do also some post-processing of the data and some analysis of that. Now, what we are planning to do in the future is to use the triangulation data that we have to provide a measure of the uncertainty of the final estimate that we provide. So basically, for every figure that we publish, we have triangulation information. But at the end, we decide for one figure to be the recommended figure. But so far, we have been publishing all this triangulation information that is going to give you the margin of error of the estimate. But that's something that we are working on, and probably next year we are going to have it in our database.
Fantastic, thank you. Yes, last one question, Vitus, go ahead,
Yes,
please.
Vitus from Max Planck in Jena. So this is an AI question. So you are using mostly data from official sources, I understand, but maybe looking forward, you could also move towards incorporating directly the voices of the people being displaced, for instance, by gathering radio data or social media, if it is available, or newspapers. So basically a lot of text being spoken or written, and use these large language models to gather all the data and summarize it and make it accessible for you. What is your perspective on this? Is there any push to sort of get more independent data in that's not coming directly from the governments, but really from the people themselves?
And as part of our monitoring system, we have a media monitoring in place. So we do collect and we do monitor newspapers, for example. However, as the data that we publish is endorsed by UN and it's a sort of official data, we need to be very careful with the source of the information, because we need to be able to explain and to show the data to any government, and they need to be able to reproduce the analysis that we do. So that's why we try to use as much as we can official data sources, but we do have work and we have explored different unconventional data sets, if you want, like Facebook data, for example, social media data. And we have also explored and developed an NLP model a while ago. Now it's completely obsolete, given some improvements in technology to do some NLP analysis and some classification of newspapers to try to extract information from them and use it as triangulation for our analysis. So for official purposes, we are always going to select the most credible source for our data. But in order to better understand the context and the uncertainty of the data, we are exploring these unconventional data sets as well, but just to complement the analysis, not to publish it as an official statistic. Okay.
Nice, thank you very much, Maria Teresa. I think that we have to, well, first of all, thank her. Now we move to the use of this data with
the presentation by a colleague in the University of Valencia, Jose Maria Tarrega, who will explain us how to use explainable AI and causality. Sir? Not in the right mode. Ah. Again. To link these two presentations, I would like to recall the Patrick Creel saying that he at some point pointed out in a science paper something like data without models are chaos, but models without data are fantasy, right? This is like a kind of a motivational saying for these two pieces of work from Maria Teresa and Jose Maria. Yes,
exactly. Yes. And
Floor is
also,
yours.
thank you, Maria Teresa, for setting the ground. So my name is Jose Maria Targa, and I come from the Image and Signal Processing Group in the University of Valencia. And now what we are going to see is how we can use two different fields of emergent fields in artificial intelligence to actually learn about displacement. And it's going to be two different cases. As Maria Teresa said, internal displacement is a pressing issue in the light of climate change, but it's also a very complex system because you don't have the hazard only, but you also have the society. And it's also a multi-scale problem because you have different timescales involved in space and time. So there are many challenges to understand what's really happening. And here's where machine learning can exploit these complex relationships in the data and try to get to know what's how the patterns and how the different relationships are interacting. So I'm going to present one case for explainable AI and sudden onset disasters at a global scale. And then we are going to move into causality for drought displacement, specifically in Somalia, which has been severely impacted by droughts these years. So first of all, a little bit of context. Climate mobility modeling. Yeah, probably most of the studies are not long enough to attribute climate change, as it has been said. But there are some climate migration myths that have been identified, particularly when talking about how populations are going to adapt to climate change and move as an adaptation technique, especially coming up with mass migration members. And basically what you have is that the context is not well understood. It's a very context-specific context, and you have a lot of relationships going on. And what it may happen is when you try to model this, you may not take into account the sheer complexity of the problem and embed very simplistic assumptions in your models, and probably you will get, for sure, extrapolation issues. And this is to say also that we are very early in the field, and especially when modeling drought displacement because of the creeping nature of the disaster, as I will talk later. So basically, what we need to do here is to understand, and because understanding means better management. And in every phase of disaster management, there are gaps, there are domain knowledge gaps that we can enhance using data. But as we said, we have many problems because this is a very complex system. So first, what we can do is I'm going to present this approach of explainable AI when you have for sudden onset disasters. So with sudden onset disasters, we mean floods, storms, and wet mass movements. And you have this interplay between exposure, hazard, and vulnerability, and this constitutes the risk. And these weather and cultural, economic, and political factors interacting, and they combine to drive displacement. So what we want to use is train machine learning models to feed displacement data, and then use explainable AI to retrieve which are the most important drivers, are also gain insight into the interactions between these drivers. For this, what we do is to build a global database using IDMC data. And we have geolocalized around 2,400 events of floods, storms, and wet mass movements. And as you can see, there are already different regions of the planet being impacted differently in terms of displacement magnitudes, and also that floods and storms are the main drivers of displacement worldwide. And then what we did is to geolocalize these events. So each polygon is a disaster for an event, and we harmonize a database comprising a disaster impact indicator of precipitation and wind speed, but also socioeconomic variables that could drive or explain displacement magnitudes worldwide, such as the absolute wealth index, that is a GDP indicator on a local level. Also conflict variables, population variables, and other variables that can account for exposure or vulnerability. And when we have this set, then we can train machine learning models and target displacement. So we have all these complex patterns that we are trying to unveil. And we train random forest models, and we train a lot of them. To augment the data, we bootstrap, and we get a distribution of the performance. And what we can see is that indeed weather variables play a role in explaining displacement worldwide, but it's not only about weather variables. You have a lot of things, you can explain a lot only with the structural factors, the socioeconomic variables. And once you have these models fit, you can ask the question, okay, but what else can we learn from these models? Or can we trust these models at all? Because they have some predictive power, but they may be right for the wrong reasons. So as it has been mentioned before, there is this field called explainable AI. And what it tries to do is to open the black box and try to explain how the model reached its conclusions, how the model learned. So right now, as you know, we are working in the space of the model. There are many methods that have been applied, and we use Shapley values, which allow you to assign a score for each variable. So what we have here is a ranking of features that are explaining displacement worldwide. And the good thing of Shapley values is that they allow you to infer the direction of the relationship, and even you can go disaster by disaster and get an indicator of which variable was more important to predict that particular event. So how you would read this? You have on the x-axis the value for the variable, so higher precipitation, lower precipitation, and on the y-axis you have the Shapley value that it's telling you how that specific feature contributed towards explaining higher displacement magnitudes or lower displacement magnitudes. So what we see in the first precipitation variable is that higher precipitation values allow the model to explain higher displacement values. And if we go to the second one, which is the absolute wealth index, an indicator of poverty, they tell you that lower AOI values are contributing towards claiming higher displacement magnitude. So we know that the socioeconomic disparity is already playing a role here. So we can zoom a little bit further and do other kind of analysis with these Shapley values. And we can focus on specifically the absolute wealth index indicator. And here what we fit is average trend lines for the below and above certain absolute wealth index values. And this mainly tells us this differential vulnerability concept that you find around literature, mainly that socioeconomic disparity is affecting worldwide people in a different way. And you can see here, for example, if you pick a value for the precipitation, you can see that people that have a higher poverty level, they will get displaced more. And people that have a lower poverty level, they won't get displaced as less in terms of what the model has learned. So we can really see these relationships and explore and do this kind of data analysis on complex models with explainable AI. So now let's move to the other use case, which is coastal machine learning, and we are going to focus specifically on drought and on drought displacement in Somalia. And to set the scene, the Horn of Africa is one of the places where droughts have the worst impacts in terms of human damage. And as of January 2023, there have been 1.8 million people displaced. And we have these impacts by droughts. Drought is a slow onset disaster, so this is a different beast. And we have a lot of uncertainties and challenges when trying to monitor droughts. We have unclear onset times. We have time lags that are affecting the variables at different time scales. So we have accumulated or cascaded impacts. So we have a lot of challenges here. And not only that, is that when you introduce the society into the equation, you have a very complex phenomenon. And for example, on the right image, you can see this graph. On the outside, you have the main drivers of drought displacement, mainly conflict, drought, in Somalia, stress sales of livestock and food security, but you also have a lot of micro factors that are interplaying in the middle, which maybe are not measurable or are not measurable yet, because we don't have the data. So in order to explain these graphs or try to get knowledge about these relationships, we can rely to causal inference. No, and causal inference is not about the what. That's what most machine learning models do. They try to predict, but the why and the what if. So this is a very particular example in which you conclude that storks deliver babies in Germany. And obviously, common sense tells you that this is impossible. And what's really happening there is that you have a confounder that is causing the two variables, so you reach a wrong conclusion. And when you condition for a land area, square kilometers, this relationship completely disappears. So if we have this kind of relationships, we need systems that allow us to understand to deal with these spurious relationships, and concretely with when we have so much variables interplaying. So this is what we try to do, to go beyond association relationships. And on the left, we have a correlation graph. In a disaster management context, a correlation graph is everything is connected. You cannot act on any link. You don't know what's really happening. And what we strive for is for a causal graph, in which you can really tell which variables are affecting each other and how the system will evolve. And it's also because understanding disaster is about answering these causal queries. We don't only want to predict right, but also we want to know how changes in one variable are causing changes in other variables in the whole system. And there are three different fields, let's say, in causal inference that are being developed. The first one is to learn causal relationships from data. This is causal discovery. And this is important when you cannot do the experiments on the field. So traditionally, you do randomized control trial, but in some settings you cannot. So this is where it comes into play. You have causal effect estimation. You want to quantify causal effect relationships, how an intervention was successful or how an intervention had an effect on a particular variable. And finally, counterfactuals. You want to evaluate what if scenarios, taking into account how the whole causal relationships are involved in the system. Still, there are many challenges. It's difficult to identify causation or apply causal queries from data due to many reasons. And one of them is poor data quality. We have also poor data quantity, many factors that are not measurable or difficult to quantify. All these confounders or drivers that are involved in these socioeconomic systems. Also, we have a changing planet, so we have non-linearities and non-stationarities. And in this case of human displacement, we have maybe weak and controversial domain knowledge in some fields. So nonetheless, what we try to do is to apply causal discovery techniques in Somalia. And what we did here was to harmonize databases at the district level. So we have a district, and we already can see how conflict and drought displacement are interplaying. And in each district, we extract a time series from this district, comprising of the main drivers of displacement. So mainly a drought indicator based on precipitation, a conflict indicator based on fatalities, and water security that we proxy as water prices, and food security that we proxy as food prices and also livestock prices, which are very important for pastoralist communities in Somalia. And after we harmonize this data, we can retrieve causal graphs from the time series. And we can retrieve causal graphs that are telling us the relationship between the variables, but also the time lags of causal impacts. So to show you an example, this is a causal graph that we extracted using the PCMCI method in Baidoa district. And just let me tell you how you would read this causal graph. So the nodes are the variables: precipitation, drought displacement, food prices, and you have the links between the variables that, and this indicate how one variable, if one variable is driving the other variable. And the color of the arrows are telling you the direction, an increase or decrease of the variable. For example, food prices, as we have a red link to drought displacement. So we know that increases in food prices are driving displacement. And also we have a number that is the time lapse in which the maximum interaction between these variables is found. So for anticipatory action, you could see the value in these causal graphs, in the sense that if you knew how lack of precipitation would start increasing water prices or start increasing food prices, and then how these food prices at the same time will start driving displacement, if you could assure that this is robust enough, you could have early warning and scenarios potential to extract from this data. And what we see, for example, of course, in the graph, is that we have a strong link of water prices in Baidoa district, and this has been confirmed by local actors, and also that it's not only precipitation driving the system, but you have an interplay of variables. And then this is another application of causal models. Once you have the causal graph, you obtain the causal graph, you can do causal forecasting, and this is just a feature selection technique. But as these systems get strong, get bigger, you may have a lot of variables, and you need to reduce the dimensionality of the models. So in our experiment, for example, to predict this last displacement wave in Baidoa, we can see similar performance in causal and non-causal models, while training with much less features. So to take home, to conclude, I have presented that innovative ML models can be used to understand climate mobilities or displacement in the context of weather hazards, and that we can use explainable AI to learn and inspect from complex models, and that we need to use causal machine learning or causal mathematical background if we want to answer causal questions. So there are here many opportunities and challenges to understand these complex socioeconomic and societal environmental interactions. And for these particular use cases, what you can see is that explainable AI on a global scale reveals compounded effect of different weather and structural factors. And in causal discovery, you also find the same, the interaction between the factors, and also you can learn the time lags and interaction unfolding during drought events. So thanks.
Thank you very much, Jose Maria. Questions out there? Philip, please go ahead.
I might have gotten this wrong, but in your causal graph, you had a link from water price to your drought index. Or was that right? Yes. And I would have expected an opposite direction as well. Your drought index would drive water prices. Do you get something wrong here? Sorry? But drought IDP, what is it? Oh, this is the displacement. Okay. Okay. Okay, makes sense.
Yes.
Might be
Yes.
challenging, but in that graph, do you have any explanation why there is a link, a decreasing link from food prices to water price? Okay.
Sorry, we are trying to we are gathering with the stakeholders and people on the ground so that we can explain certain things. It's also that our study focused on unveiling drought displacement. So we try to gather the main drivers of displacement, but not the main drivers of the rest of the variables. So it's unknown if you have confounders. You have a confounder between food prices and water prices. For example.
Yes, please.
Just a short question. You use PCM-CIA for that. How difficult was it to figure out the right parameters to arrive exactly at this causal graph?
You have different parameters now. You have the alpha values, the p values, and what you try to do is to fit for a lot of alpha values and see if it's stable and robust. And you do this qualitatively. And then you can also see if it's robust under when you shorten your time series. If this causal graph is robust, you can assume that your assumption for causal stationarity is correct, and for different time lags. No, so you have to retrieve causal graphs for all these different parameters, and then you retrieve the causal graph that is that makes the more sense.
Any more questions, curiosities? Do you want the data? You can ask whatever. Yeah, go ahead, please.
Hello, I'm Christina from UNFCCC, and I was wondering whether you can actually interview people that are internally displaced to get more information for your model. Thank you.
Okay, so hard question to answer for me, but yeah. For example, this data is how they collect internal displaced data in Somalia is by running interviews, but are actually the coordinators, the disaster management teams that we are interviewing with to explain and to explain them the models with.
Okay, yes, please. Go ahead.
Hi, so this is Yannis Papoutsis from the National Observatory of Athens. So are you considering all the variables that can contribute to migration? Or if you're missing something, what is the impact of this causal graph?
Okay. So the impact is that you may have totally wrong conclusions. So what you try to do is to go for literature and qualitatively check if these drivers are correct. And has been research done by IDMC on what are the main drivers. And you also, I can tell you that there are indeed more drivers, but the contribution may be marginal, super marginal, for example. And then you will not notice this in the data, they are noise. But it's very challenging. It's a very challenging field. Because there are a lot of drivers that are not being collected or are not released by there are a lot of data gaps here. For example, you have the effect of remittances, like above payments for abroad. We have no data about this. So this is a challenge here still. Yeah. Thanks for your question.
Okay, any further question? I have a curiosity, so Maria, is I know the work very well, but we didn't explore these new sort of causal algorithms that can learn kind of latent variables. But I don't really know if that could be possible. I mean, we are already struggling with the sufficiency assumption. I mean, getting all the potential variables involved and everything. But maybe that could be, what do you think? I mean, that could be a way, or do you expect other things to try out first? Or?
Okay, so we have we have been also exploring how to use the spatial context. So we are not doing any sort of spatial temporal analysis. So you can eliminate confounder or latent factors if you compare situations between districts. So all the stuff that you are not measuring, that would be latent factors, you could eliminate their influence on the model. So yes, thanks for.
Yeah, with the session. Yeah, now let's move to wildfires. We have the pleasure to have with us Ioannis Prapas from the NOAA. And yeah, the floor is yours. Yes. See, this works. You have a video? No, you don't have a video.
Okay, so I'm going to talk about some deep learning methods we used for wildfire danger forecasting at different spatiotemporal scales. This is work done with many different collaborators, many of whom are also in this room. Some are not. And it was done in the context of two European projects, one Ceasefire funded by ESA and the other DeepCube funded by the European Commission. So let's move to why we're doing this. The motivation is kind of clear. We expect that climate change will aggravate fire danger in Europe and globally, actually. So we want to forecast fire danger in the short term, so hours and days, in order to manage resources better and also to plan evacuations. And in the long term, like weeks and months in advance, we want to know what equipment to lease and also how to manage the fuel better. So fire in general is a process that is notoriously hard to model. And the reason is that we have humans, climate, and vegetation, all of them influencing and dynamically changing all the time. So the idea that we're gonna use here throughout the whole presentation is that we want to use machine learning on historical Earth observation data to kind of associate the conditions of the fire drivers to past burnt areas. We start with short-term wildfire danger forecasting. And here, let's see what people are currently using operationally. So we have these fire danger forecasts that are mostly based on fire weather, so meteorological conditions, that are at the resolution of weather prediction, so 8 kilometers. And then it has, so this is a process-based index that assumes pine fuel everywhere. Then we also have, like in Greece, for example, on the right, you can see some national danger maps that are at a regional level, so lower resolution, and also we don't really know how they come into play. So they consider also the fire weather, but also some local conditions. So now after that, what we want to do is to define fire danger in a way that we can approach it with machine learning. So first of all, we use this definition that fire danger assesses the conditions that allow a fire to ignite and spread. In that way, to make it a data-driven fire danger, we want to associate the conditions to large burnt areas, and we will see large what it is when we go to the data side. So when you talk about machine learning, first you talk about data. So here what we did is we gathered different data from the fire drivers, so meteor drivers, satellite observations that can help, like land surface temperature, vegetation indices. soil moisture, some topography variables, land cover, population density, road density, and also the burnt areas that we get from the European Information System for forest fires. So we gather this at 1 kilometer by 1 kilometer by daily resolution for a part that covers Greece and the Eastern Mediterranean. From an initial analysis, we can see that on the bottom right, we can see how the drivers have different values depending on if a pixel is burned or not. But we also see some very mixed values, which makes sense because it's a highly stochastic process. If you don't have any regression, then you don't have a burning. So now we move to the experimental setup. We have this spatiotemporal data set, the data cube, and from this we create machine learning data sets. So first of all, we have a tabular data set that we have all the fire drivers and also some kind of aggregations in time. This is the tabular one. Then we have the time series one that contains basically features, but also in time. And then the spatiotemporal that includes also a spatial context. The target is having these blocks of the fire drivers, having these vectors to predict if a pixel will burn or not the next day. And result to a fire that becomes large. And large, we made it larger than 30 hectares, which is actually also the limit of the satellite. So then negative samples. So you have the positive class that you know, high fire danger when we have a large fire. What about the negative one? So there we choose it to be on days that we have no fires in a large domain. Okay, and then we go to the evaluation. So what we have here is that for 2 years, 2020 and 2021, we measure the performance of the different models. So 2020 was like a normal kind of fire season in Greece, and 2021 was an extreme one. And we can see here that the machine learning models are actually good predictors of fire danger. We also compare with the fire weather index, and we see that all of them are better. I have a better predictive skill for burnt areas. And the temporal and spatiotemporal models are the ones that use the context are the best, with a slight difference between the temporal and spatiotemporal. Then we want to understand what drives the model's prediction. So here we will see the partial dependencies. So in the x-axis, you see, like for a variable, if you perturb it, what's the effect on the fire danger, which is shown on the y-axis. So you can see some patterns that generally make sense. So if you have a higher temperature, higher fire danger, the NDVI in the extreme values, so very low or very high values, lower danger. So it's the middle values that give a higher danger. And this the same interpretable for relative humidity and soil moisture. Like when they diminish, danger diminishes as well. So this is not discovering something new, but it's helping build trust to what the model predicts. And then we also want to see, like, because we input the model some time series, where does the model focus on. And we kind of identify like two different type of focus. So for example, for the wind speed, it seems to only matter the last day, so the day of the ignition, if you have, which is something kind of expected. And then you have some accumulation effects from other variables like total precipitation. So it matters more if it rains the day of the fire, but it also kind of matters the previous day. Okay, so after developing this model in the last summer, we actually applied it with fresh data. So we generated maps every day, and we actually sent maps to officials. So we got some evaluation and some good feedback. And what they liked actually was that was what you see on the right, that the maps, like ours is the middle one, and this map is kind of has a higher precision. So you can see like some specific regions that are in high danger, while in the bottom map you see like the whole map in danger. So the thing that we are working now is the scaling this up to the whole Mediterranean. So we already have a data cube that is much larger, is more than 5 terabytes, and basically it's similar to the previous one, but because we have more data, we can also try more stuff. So we can, except of danger, we can model susceptibility, try also the spread, and also model extreme wildfires. You can see here a teaser figure of what's to come. The data is already public, so you can already access it. And now I want to move to a different subject, which is about subseasonal to seasonal wildfire forecasting. So here, the current status is that what officials use is directly forecasts of weather anomalies. So like temperature, rain anomalies 1 to 6 weeks in advance, or the same for 1 to 6 months in advance. And this is like the long-term forecast provided by the information system, the European information system for forest fires. So again, the context is the same. Now we want the wildfire drivers that are influencing at these scales. So we have, how can I play this? Okay, so this was a video also created by Lazaro. And it was a nice animation. Anyway, we collect data now at a resolution that is much lower, so 8 days temporal and quarter degree spatial. And the target are the burn areas, and we have also included fire emissions. So a first thing that we have tried is to define wildfire forecasting as a segmentation task. So we cut a piece of land and we gather the fire driver variables that we stack them, and we want to predict the presence of burnt area at a future time step. So, and let's see how this goes. So we can, what we have seen is that, okay, of course, performance decreases as the forecasting window increases. The model's predictive skill is better than the seasonal cycle of the burnt areas. And the burnt area patterns can be skillfully predicted even 2 months in advance. Then we can also appreciate this when looking at some global predictions. So you can see the the target in the bottom and the prediction on the top. So kind of the main patterns and the shifts are captured. And the idea here is that this kind of simple model didn't capture that the Earth is an interconnected system, so it didn't capture effects like teleconnections or memory effects. So moving forward, we want models that are able to capture these spatiotemporal interactions. And these interactions we've seen many times in literature that are important for global wildfire forecasting at this scales. So we developed this model. So this combines the local input with some global scale input, but also climatic indices. And for this, what we do is we use the transformer architecture that can be kind of easily used with a multimodal input. So what you have to do is to define a way to tokenize it, to split into tokens, and then you can feed to a transformer network to do the rest of the process. So these are the results that we got. So what we can see initially is that just using the transformer architecture without any additional data is better than the unit architecture, at least for most forecasting horizons. Then when we use these teleconnection-driven transformers, so the ones that use global input and climatic indices, we get a better performance, especially for longer forecasting horizons. And actually, the best performance, we get it when we combine all the inputs. And also, you can appreciate this when you see the difference between the forecasted and the actual pattern. That is quite close. And this is some initial work that we think is very promising. But there is like a lot of things that we want to see next. So of course we want to improve the evaluation, use more baselines. It's nice to see like the relative importance of the indices and the global scale input. So we see that both of them improve the forecasting skill at longer forecasting horizons, but we don't know if it's for the same reasons. It's also interesting to look at the attribution, so maybe the attention maps, time series, and also going beyond burnt area forecasting to some other tasks. So in general, what we've seen today is that machine learning can increase the skill of wildfire danger predictions. In the short-term, temporal context is mostly enough. In the long-term, spatial context becomes more important. And then I think it's very important for this forecasting of wildfires that are meant to be operational in the end. That the evaluation should be in fire danger terms, in terms that people working with fire can understand. So problem-specific metrics to compare many different seasons, so to see if you can capture this interannual variability, and also compare against existing tools to see if the machine learning models are not just good compared with each other, but good in general. And then I have these links. Probably you cannot capture them now, but the presentation will be online. So yeah. Thank you.
Okay, thank you very much. Yeah, we have some time for questions. The discussion. There were many things to talk about here, right? The horizon, the different architectures and models that you used. Yes, Marcus.
Yeah, thanks a lot. It was actually indeed quite impressive. But what I did not quite understand, so basically if you use the whole globe as a predictor, let's say with the transformers, if I understand correctly, then you don't have so many samples at the end. It's just where you just have the time steps as samples. So how do you deal with that actually then the data becomes a bit sparse actually to some extent?
So something that I actually forgot to mention is that the global input is coarsened. So you have like this more high resolution local input that accompanies the global scale. I don't deal with it in any specific way. Like you can have samples that include the same global views. But the domain of the forecast is different.
Is it actually a kind of a trade-off between the amount of data and the resolution that you're using? I mean, did you do this kind of evaluation studies trying to check that trade-off?
Yeah, not yet, but I think it's an important thing to check.
Let's please flip.
I mean, it's an easy default question, but in this case, probably applicable. I mean, how do sort of changes in land management practices and so on get in the way to generalize some of this? Because I think this must change quite a bit.
Just to understand better, you mean how are they included in the modeling, or how?
No, how, say, if in the training period or after the training period, people change their practice in land management in terms of how much wood is left in the woods, how much all these things, how much fuel is there, how much fire suppression is there. It should affect a lot what happens in the future. So is there something you can estimate the uncertainty of, or is that something you just have to live with?
So I'm pretty sure it's important to address that, but we don't do something specific for this. What we are doing is that like just ensuring that the evaluation is correct, is training in the past and predicting in the future. But apart from that, we didn't really manage about this dynamic nature of the human factor.
Gustavo allows me to tag on another question. You predict fire, and then you also predict emissions already? Not yet. Okay.
It's in the data set. Yeah.
Okay. Because in your training data, you use burned area and emissions, but you don't yet predict it. Okay.
So we have it in the big data set from which we sample like tasks.
Yeah.
And this task we didn't use emissions at all.
Okay. Thanks.
Anyone else? Me too. You're a curious guy. Come on.
Yeah, I
Lovely.
I think I got I thought I had understood this already, but I think I didn't.
So how do you deal with the fact that fires are sort of, there's an ignition event and that's maybe hard to predict, or?
Okay, so what we know is that when we have like a fire and it turns out to be big, there is a high fire danger. So these are the positive samples we can be sure that are correct. So for the negative samples, we have to kind of play it safe. So we sample them in days that we have no fire, like no big fire.
So I guess that the trick is in the measure, right? I mean, you can be certain for the, let's say, the sensitivity score, but not that much on the specificity score, right?
And did you play around with like different sort of, you have sort of then a threshold, right, that you manually could tune? Do you play around like?
You mean like where do you get negative samples from?
Yeah, like when is it considered that there is no risk?
Yeah, so this we want to also check more in the Mediterranean cube, like to maybe define it better, the way that we sample negatives. We have also explored some methods that are dealing with uncertain labels, which seems to help. So you kind of sample negatives like more without caring so much. And then you incorporate in the method like this uncertainty of the negative class. And this seems to improve results actually.
Well, thanks very much. I think that we are ready to move to the next speaker. Thank you, Anis, again. Yeah, next speaker is Joachim Denzler from the University of Jena. We'll talk about a nice and intriguing chain of action, right? From anomaly detection to attribution to forecasting. Let's see how it goes. Yeah. Welcome. Thanks for coming. Yeah.
Hopefully it's not just a summarizing talk of what I learned this day, because some of the elements that I'm going to talk about have been discussed before. Just to tell you where I am from, and that I'm not a person working in climate science since many years. I'm heading a computer vision group, and our main business is computer vision and machine learning in these areas. But luckily, we are also involved, thanks to collaboration with Markus Reichstein, to data analysis for ecology and climate science. And first, I will start about one of the terms that I use in the title, the anomaly. What is it? What is anomaly detection? And the first one, I think, is very clear. We want to identify instances or patterns that deviate significantly from the norm. And the other two terms are not to be boring on this first slide already, but just to relate the next slide to what we have done since more than a decade already. And the final one, the third one out of distribution detection, is something that relates to, do we really deal with non-stationary data over time? So I mentioned this already before, that aiming for actions that probably mitigate impact of climate change will also change, of course, the data generation distribution, hopefully, if it's successful. And then, of course, out of distribution detection is also a very important aspect. I start with what we did since almost or already more than one decade, that is a continuous learning cycle in object classification. That might be off topic for this presentation and for this session here, but it's very interesting that most of the elements that we have here that incrementally detect new objects in a scene that a machine should learn and recognize, that this relates also to novelty detection in climate science, because what you need to do is first to detect novel things. You want to integrate this into your model. You want to find new features, such probably in the future we can predict them and learn prior to the event that something will happen, will go on in this direction. And then finally, domain adaptation has also been mentioned today, that you want to consider the distribution shift that you will have over time. And this is something we worked on for a long time. And I show you one example from that is not related to computer vision, but more to signals, but not time variant signals as we have it in climate science, which is a work where we have to detect unknown bacteria from Raman spectroscopy. That's a measurement technique that is seen as a fingerprint of a biological probe. It represents content of this probe. I'm not a biologist. I cannot go into more detail here. And the question is, of course, you want to detect known bacteria in medicine, but also if there's something unknown, you want, of course, to know that this is an unknown one, because this might be even more threatening for the patient. And what we tried here, and this is also important to remind you of, that not only deep learning methods are capable to do something useful. Here we used non-parametric models based on Gaussian processes, and we could here really achieve a significant performance gain, not just to identify correctly unknown bacteria, but at the same time are able to detect known ones with an equal quality. And compared to other state-of-the-art methods here, you see that we have been quite successful with a standard technique, Gaussian processes. We have other work on novelty detection that is not so important for this session. More important is that we somewhat switch to monitoring complex dynamic systems, and there are a lot of around that are also interesting for computer scientists. That's traffic systems. I learned this when I traveled from Jena to Basel with the Deutsche Bahn. It's a highly complex dynamic system that is never in time, but I can complain. I have no idea how to solve the problem. Then personalized health is something which is a medical system is very important nowadays. And finally, of course, to monitor the health status of our Earth. And what we figured out as key elements of such systems that monitor complex dynamic systems is that we want to actively acquire data, keep the human in the loop. That means if the system returns an anomaly, the user needs to interpret this anomaly, because there's no semantic attached to something that is an outlier, at least in the beginning. And we want, of course, continuously update the model over time, such that probably in the next time we can predict that an anomaly, a specific one, will happen soon. Then, of course, the anomaly detection itself, which resides in an open world. We have no fixed anomalies, because if this would be the case, we can enumerate them and label them. And it's also not just about detection a posteriori, offline, but also prediction in an online fashion. And finally, this is, I think, what also clear in some presentations before, that we want to integrate knowledge from the domain, and causality is a very general way to integrate knowledge about physical relationships in variables to, in the end, make a model that we train physically consistent. And at the same time, we can gain insight into dynamic processes by looking at these causal relationships that we detected, and in the end, also be able to explain decisions of such a model, which is important if a human receives some early warning about an event, and it might be wrong. But having an explanation, it could be probably verified and even confirmed or rejected. So all of that, especially the data, the integration of knowledge and data-driven methods, have been published in this paper. And we started working on climate data in the Horizon 2020 project BACHI in 2015. And what we first developed was a kind of index to identify changes in the biosphere-atmosphere interrelationship. And it was a very simple method. So we applied autoregressive models on the data. We checked whether there's a deviation from what the model predicts. And in the end, it was my suggestion to what you have done. We combined it with a spatial relationship technique, Markov random fields, to come up with a map that tells where is an anomaly happening. And then at the same time, we could analyze this autoregressive model in terms of the residuals that are measured, which variables contributed most to this anomaly. And in this case, it was a Russian heat wave, and it's probably not so fascinating that heat is the main driver of the heat wave. But in the end, it was a data-driven method without including any knowledge about climate science. It was just as variables that have been observed over time, and then detection of these spatial temporal anomalies events in this area. Another technique that we find very useful is what that we called maximal divergent intervals, where the idea is the following: you have given a multivariate time series data, and you separate the whole series into an inner and an outer part, and you now want to figure out that inner part that deviates most from the outer part in terms of the statistics. And this could be measured by the Kullback-Leibler divergence. And the only question here is how to estimate the probability density function that are involved here. And it's figured out that kernel density estimation or even simple Gaussian assumption for these distributions are sufficient to, in a purely data-driven manner, return reasonable results. And this is one example. Can we click on this video here? Only for not sure whether it's could be that it's not included here because I just copied the PowerPoint. Anyway, what we did, we applied. Oh, I'm now no longer here. Okay. We applied this on historical data from the Baltic Sea, where there have storms been recorded since, I think, 1957 or so. And out of the 50 most anomalous events, spatial temporal in this case, 48 of them have been historical storms that have been recorded. One was this kind of dead thing when nothing happened. That's of course no storm. So the system doesn't know about storms, it just detected anomalous events. And one was an outlier that could not be associated with any anomalous event in this time period. And this can be also applied to other data, like video data, even for text, if you represent text as a time series data in terms of representation of the individual words. And there's code available. And I mentioned this especially because there's a paper out from 23 that compared different methods, data-driven methods for anomaly detection, and MDI was overall the best, still the best, although deep learning methods have been compared with this method in this paper. Yeah, so this is the first thing, what is anomaly detection? And I showed some of the methods we have developed. And then now is the second part, how can we explain why this anomaly is an anomalous event from the point of view of the machine. And this is because purely data-driven methods like MDI have some shortcomings. They don't know anything about the problem domain. So if you apply them for hurricane detection in simulated data of the climate system, then they will return some hurricane, but also other anomalous events that, of course, are disappointing for people who are just looking for hurricanes. So in this case, they are not applicable. And also the question is, are they do they happen because there are external forces or because the data generation distribution changed? And of course, what you always want to do to integrate as much knowledge as possible for your current domain. And to do all of that is the preliminary to understand the causes or factors that contribute to the anomalies. And that's the reason why we also thought a lot about causal inference. And the reason why it's important is shown on this slide. The left figure shows, of course, this area here that we are discussing today. But the middle one shows that other areas like medicine are also interested in this kind of analysis of time series data in intensive care units, for example. And finally, we can leverage what we get out of these causal inference methods for explainable AI. But let's see what causation is compared to correlation. This has been nicely shown with this figure before. It's here a similar one, and the important aspect is indeed intervention, that you are able to intervene in the system to figure out whether the variable X has a causal effect on Y if you intervene on it. And this is the basis of what we did first to improve anomaly detection by trying to estimate the causal relationship between the variables and then see whether there's a change in the causal links in an anomalous event. And luckily, this could be shown in this example here with 4 variables, air temperature, vapor pressure deficiency, and so on, where we figured out that the average causal links between the variables is the one that is here on the left-hand side, averaged over a period of 12 years, from in August in France. And then we verified this during the heat wave in France in August 2003, where we saw that there's a significant change in the causal link strengths between the variables. And this could be even analyzed in a frequency domain. So the idea here is that we do a vector autoregressive model and applying range causality on that, and then analyzing the results in the frequency domain, because then we figure out that some changes in the causal links are due to short-term events, so low frequency, high frequencies, and others are long-term events represented in low frequencies here in these on these plots here. Yeah, and the same could be done also to explain MDI. So we can go on and so what means we can here explain the results. Yeah, so the domain expert can look at the results and can interpret whether the system, the machine is right or not. The same could be done for explaining MDI, but with a different way. We here intervene on the signal. So if you have detected an anomalous interval by MDI, we just go and substitute one by one the variables with a variable that is not correlated with the original one and does not show any effect on the outcome of the method. And by intervening on those variables and figuring out which is the one that changes the MDI result in the end most, is of course one of the variables that has most effect on the result. And this is done by knock-off methods, by knock-off intervention, which is a standard technique nowadays in causal analysis. And that's the final work that we do in time series analysis, also based on knock-off counterfactuals. What we want to figure out is we want to look at a data stream that we use to train a standard deep AR model. It's a LSTM-based model for time series prediction. And then we substitute again individual variables by their knock-off variables. That means they have the same correlation as the original variable, but no dependency on the output. And then we check the residuals of the trained models on the original data compared to the one where we substitute variables with the knockoff. And if we observe a significant change in the residuals, then there's a difference from there's no change in the prediction. And this is then used by just computing statistics over the change. And you see here on the left-hand side the case that there is a significant correlation, cause-effect relationship between two variables, because if you substitute the variable by its counterfactual knockoff, then you have a significant change in the distribution of the residuals. And in the case that there's no influence of this variable on the other, you see basically no change in the residuals. And this could be evaluated on synthetic data, just to have a significant amount of data to generate box plots like here. And what you see is that here the F1 score of the method that compared to PCM-CI plus, that the F1 score on the synthetic benchmark that we generated is much better than the method of Runge, and even the false positive rates, detecting false links between variables is reduced in a kind of significant way. And if you compare it on data that is also used in this community, also by Jakob Rumi, you see that for this daily river discharge data, you have 3 rivers where you measure the water flow at different positions. And of course, geographically, you know what the correlation, the causal links are between the variables. And the only two causal link is between variables K and D. And what you see that most methods return a lot of false positives, all return the right causal link. And our method with steep RR plus knockoffs is the only one that generates no false positive in this case. Yeah, so I come already to the outlook, because forecasting is for me more outlook, since from a general perspective, it's very difficult to say how do we generate prediction for anomalous events, because anomalous are outliers. We have no mathematical description of it, and how can you predict it? For specific domains, we have seen this in the morning and also in the afternoon. Of course, you can do that for extreme events, for extreme temperature prediction and so on. But the question is, how can we generate such prediction steps? And the only important thing I see is that, of course, it should be spatial temporal one, can be applied to climate science, and it's, of course, necessary to have an online way to do it. So for MDI, for example, it's an offline technique. It cannot be done. Well, one can try to implement it in an online fashion, but it's not as powerful as the offline version. So Kerstin, for example, published a nice paper about this, how to do an anomaly analysis for streaming time series data. Very important. I think only a few papers around that tackle this problem. And then, of course, there are a lot of things to learn from existing systems that focus on a specific extreme event. How can we predict this in the more general setting? Yeah, and then this brings me to my closing remarks. So the questions are, how do we combine data-driven anomaly detection methods with model-based forecasting to arrive in the end at anomaly prediction and together with it attribution? So there might be ideas that you first detect in an unsupervised manner the anomaly and then try to figure out whether representation beforehand, before the event, can be somehow an indicator for the same anomaly later on or a similar one. Could be based on the causal structure of the variables that you observe. This is the second point. I think that it's important to do causal analysis to be able to forecast in a reasonable manner such anomalies. And the final question that is probably more, because we discussed this a lot in Jena, whether foundation models are the right thing to do something like that. And there are indications that it's probably not optimal. I have at the moment no clear opinion on that, but I'm more to apply models that we understand, where we receive uncertainty measures that are worth the name and not to approximate neural networks in terms of uncertainties. And the final thing is also, do we need to keep the human in the loop in such techniques? Because machine will generate false positive in terms of early warning. And the question is, can we integrate the human in the loop like active learning and then use this as feedback mechanism to improve the model over time? And the last point that I mentioned also before with speakers and also by my questions is, how do we consider non-stationary data, which will be the case if we are successful in performing early warning, because then probably less will happen in the future and the data distribution will change that we observe. And this, of course, means we need to be able to consider this, and to retrain everything every 5 years or so is probably not the right thing to do. If we could integrate this kind of effect that our early warning has on society, on different things, then this would be the ultimate goal. Honestly, I have no idea how to do this now. Thanks a lot.
Thanks, Joachim. We have time for questions. Billy.
It's a more philosophical question, but maybe it's a bit too late for that. But
these are the good ones.
I'm not sure exactly what an anomaly is in this context, because when I think of extreme events, there's no anomaly as such. An extreme event is they're just unlikely events, but you can think of a 1 in a year flood, a 1 in a 10-year flood, 1 in a 1,000-year flood, but I'm not sure which one is the anomaly. So more in the general sense, what is an anomaly sort of in a climate change context? It would be interesting.
It was the reason why I put the first slide on, to talk about the terms that are used. The anomaly detection, I think in computer vision is quite clear. It's open set classification problems. You know that you couldn't have trained everything that happens in the world, and that's something you want to detect and include in the model. For anomaly detection, well, it's of course, if you know what you are going to detect, it's probably no longer anomaly detection. That's true. But you have time series, probably you have systems where I don't understand completely what's going on. And I'm not sure, I'm not an expert, but I think that climate system is not that completely well understood in every respect that it could be seen as an.
No, we could end up in different circulation regimes or things we've never seen before. That's true. But I think most of the extreme events are just
extreme events. It is probably, it's also for me not a question of anomaly detection. That's true.
Okay. So just to get this right there.
But what you could do is could learn from how they are detected in terms of what things indicated. That's my hope. Yeah. What?
Reading the room. Most of the examples you showed is quite low dimensional data, so it's often time series data. So how well does it generalize to higher dimensional data? So I'm thinking of 4-dimensional climate data. But we don't know what we're looking for.
Honestly, that's a problem of collaboration, because we can, of course, analyze high-dimensional data. And in the end, it's a suggestion of the machine. This is an anomalous interval. But the explanation needs to come from the domain experts and to say whether it's true or not. And we are lacking just this feedback mechanism. So I would say that in terms of simulations for MDI, we could go to higher dimensions. I think in this paper that they compared, they use standard benchmark data sets from anomaly detection, and they are pretty high dimensional. I think 100 and more variables. So in principle, it's doable, but of course, interpretation, especially if it's based on causal relationship, is something that must come from you. Yeah,
should be interesting.
Okay, so there is no one. Well, I could relate one question with what you just said on the dimensionality. I was super curious about MDI working in I don't know, estimating KLD in high dimensional scenarios is really challenging. And I guess that, I mean, and you mentioned something about the Gaussian assumption, right? I didn't get it quite well, but I suspect that you would run out of samples very quickly, right? So and then your space is empty, and then I don't know how much can you trust these estimates of KLD.
I have the paper not completely in mind, but they used some of the benchmark data set, and I guess, as far as I remember, there was data with 100 dimensions.
Oh, that's
that
impressive.
they applied. It could be that they are densely sampled data that's such that you have, of course, small intervals couldn't be, of course, estimated. The outer is always easy to estimate.
Yes,
yeah, but the inner one, of course, is.
Yeah, exactly.
So,
that's the point.
Yeah. Scale is always an important issue. Yeah.
Yep, Marcus.
Yes, no, I also, maybe it's related to Philip's first question. So basically, I mean, one could actually argue, so if you're able to predict an anomaly, then it's not anymore an anomaly, because basically you have an autoregressive model, and then in your first methods, actually, then the anomaly was something that was not expected given the model. So if you have a model that can predict the anomaly, then it's not anymore. But maybe one needs to have I wonder what you think about it, more of a probabilistic approach. So basically saying, okay, we need to be able to estimate, particularly in dynamic systems where it's not entirely clear, like the ensemble forecast and so on, where we need a probabilistic forecast, and then we can say, what is the expected distribution over the next 3 months or something like this. And then one can, within this distribution, one can basically say, okay, here are very rare or very unlikely things, and these we call possible anomalies or something like this. I don't know if this is something that's possible to do or desirable at the end.
Well, definitely. That's what I mentioned with the Gaussian processes. Yeah, that's
okay.
It's non-parametric. There's a clear probabilistic interpretation of what's going on. Uncertainty is clearly defined. I didn't look into that in more detail because at the moment we are still working with deep learning based methods, but I feel that this will more help than it will.
But would a Gaussian process also be able to do it dynamically when then you have these latent force models or something like this? Or if you want to have it kind of.
I'm not saying that for time series data, the Gaussian processes are the only one that can be applied, but I think that at least deep neural networks probably are not for such to estimate densities, distributions of something in the future is probably not, at least from my experience, not that reliably possible. And others that return real uncertainties and might be better.
Maybe trying to connect the dots and launching another question is you can take the information theory perspective to define what an anomaly is, right? And then you can basically rely on entropy, right? So the surprising thing is the anomaly, right? So something that you do not really expect, and probably that can be linked with the MDI, right? And I was Yeah, I was expecting something more on the, because you mentioned, okay, yeah, we have this problem with online learning, right? So what it is an anomaly now, maybe, you know, in a couple of years, it is no longer an anomaly, right? So you want to keep updating what the concept, elusive concept of anomaly is, right? And yeah, maybe for MDI it's not possible because of the way it is built, but maybe trying to link that to updating information theory concepts through this normalizing flow perspective, or you can work this out. I think there are ways for updating the concept of distribution shift, anomalies, entropies in an online fashion. It is true that, you know, in the end you will run out of samples time. I mean, divided by dimensions. So, but yeah, it's a very challenging problem what you're trying to solve. Yeah. Not even. I mean, I don't want to even talk about non-stationarities, no, because that's a different thing. I mean,
yeah, well, one idea there where we also published in our paper is that we just try to separate the time series data into regimes of similar kind of statistics, and then treat them independently from the others, so that we can apply at least course levels. That's what works in this on this one application quite well. Whether it's can be transferred to others, I don't know. That was just one paper that we have published with colleagues in geography. But this was a link to the lifelong learning cycle. Of course, it's, I think for early warning, it's not so important that, so you know these things that are threatening, the extreme events. But the question is, are some events probably better predictable than other situations, better predictable than others? And if you observe prior to the extreme event or anomaly, some kind of, in some feature space, a representation that indicates something is going on, then you could do that. Even if the extreme event is known, but you know that there's something that in the past have led to an anomalous event, and could use this as a trigger. But I'm just thinking about how to make early warning more practical in complex systems. So for the Earth system, probably you know more about in medicine. There are things that are unexplored so far. Yeah, that we don't know how the brain reacts on some things, and we could have data and want to figure this out.
Yeah, and I guess we stumble again on the problem of the tails, no, the distributions, because they change and you cannot estimate it. Yeah, any further questions on the audience? I was curious about this knockoff technique, but probably, I don't know, maybe it's too technical for this late afternoon thing moment. And yeah, we can discuss this offline, I think. So let's take some minutes to breathe a bit, okay? And then we will start with a panel, okay? Philip wants to have an announcement here, so about the form of the panel.
So it's been a long day. It's been a really great day, and we had lots of good talks. We don't want to stretch everyone's patience forever. So the idea was, instead of having a super structured panel discussions, to get the speakers back out, reflect a little bit briefly at the end of the day, and see not all of the speakers are still here. Some had to travel, but we can just have a good discussion. We don't need to make it too long, but we want to just wrap up things a little bit. But let's maybe take 5 minutes as a breather. All right, so as I said before, we don't want to make this excessive because everyone looks tired, but it's been a really good day. So it's a bit of a time to reflect and to ask last minute questions to the speakers, but also maybe to think of things that you missed or that you'd like to get more explanation on, or what maybe the speakers could add to your experience. So I'll just kick off with opening it to the room again, if people had further thoughts, and then we can go back and hear more from the speakers. Anyone further thoughts from the audience to kick off with? Yep.
Should I use this? Are people?
I'm not sure. There's probably still, yeah, there's still some people.
Okay. So one thing that often comes to my mind is this link between that can exist between physical models and models that learn the dynamics of observations, where we actually try then to interpret via XAI or via causality tools. So I'm always wondering, what is the ability that you see of using physical models to actually test hypotheses about the ability of machine learning approaches to learn the causal relationships that you have in the physical models themselves. And by that, making a demonstration that, at least according, let's say, to the complexity of the physical models that you use, the data streams that you have to constrain them, that you can learn the response, the proper response between the variables that we're using as X variables in our machine learning approaches and the responses. And I think it's something that applies to many of the use cases that were shown here. So I think I'm in the right place to ask this question to a broader audience.
EINN, physics-informed neural networks, that can match with differential equations that you have. This can be used then to train it with in a data-driven manner to fulfill the differential equation, but consider data that you have recorded. So this is something that can be done. Not on climate data. I have no idea about differential equation in this area so far. I think that's possible, but I have no idea how to do it. But that's a fan noise project from aircrafts to study how the noise changes if you change the engines of the. And there are differential equations that tell how this sound is generated and happening. And this can be done. Yeah.
I mean, maybe just to add to this, I think it's spot on. I think it's what we should do to test these methods. So what we do for aerosol cloud interactions that let us, I mean, we just try it out on models, and some of these ultra high resolution models we have now, they have the same scale as satellite data. So it's exactly now where we can do this. First things we've tried actually just showed that the methods struggle. So it's not as easy as you think to just take it out of the box and test all the causal pathways. It was much harder than we thought, but it's exactly, I think, what we should do. Anyone else wants to still add? Okay. Any further?
I have a question. I'm sorry I didn't get to see all of you. But one thing I notice often during climate change conversation is that biodiversity takes a bit of a backseat. So I'm wondering how you feel about that, or what the role should biodiversity have a stronger role? Yeah, thank you.
Very good question, I think. A very good point. I mean, I would have made that point also in the presentation, that I think we are living really in a world where, of course, where we have the climate crisis, but where it interacts with a lot of other things. Health is another one, biodiversity is another one, and I think we really need to see that there are kind of systemic links between these different domains, and so this makes the whole thing even more complicated, also as a prediction task. So when, for example, does an ecosystem collapse under certain climate conditions might depend on the biodiversity or not, and this might also depend on another aspects. So yeah, I think it's a very important question, and so maybe. Climate is basically climate is kind of, for me, is a passport photo for the Earth system, kind of, and everyone knows in the public what is climate. But yeah, but I think it's now is more really like climate is in a broad sense. I mean, it included the carbon cycle at some point because of the kind of climate variable also, and it should also include other aspects of the Earth system. So for me, it's kind of a metaphor. Climate is a metaphor for me personally, but you might have a different.
But I guess the biodiversity community feels exactly like
What it means that machine learning people really have applications, not just by chance because there's someone next to one sitting and big market of that. Which is also inspiring to see. It's useful, not just
It's also not treated as something that's going to be like solve all our problems, but rather very critical as what are we doing with the machine learning models, and is it actually adding anything, or is it maybe just all a hype? I think it was very nice as we reflected on all the different blocks.
Right. I mean, I took the same thing away, that to have all the different agencies also here, and this sort of non-physical climate science input was particular. I mean, maybe I'm a physicist by training, so I'm a bit stuck in there, but to see exactly these applications is really, really fascinating. And it was quite eye-opening to see displacement and things like this. I wouldn't have probably beforehand thought much about how it directly links to the physical climate questions. So I think it was really, really good. Gustavo, are you ready to unleash the power of AI?
Are you ready to take it? I mean, yeah, the prompt was very stupid and simple. I asked ChatGPT that I'm in front of an excellent sort of speaker on climate and AI sustainability, and I asked them, okay, can you give me some questions that have to be precise and thought-provoking? And yeah, of course, yes, I can, blah, blah, blah. Some of them are very bad questions, very cool questions. I selected just a couple. And probably that speaks to my editor, but whoever wants to take it, can take it. So this is something like, what role should governments, industry, and civil society play in shaping the development and the deployment of AI? And how can we ensure that the stakeholders are really engaged and have a voice in this process? It's a challenging one, right? Not bad, yeah? No, I didn't want to put too much pressure on you.
Oh wow, that's a tricky one because it entails so many things, right? If we talk about AI as a broader concept, right now we have a heated conversation about everything that turns around regulation, because we are not ready to talk about regulations. And why do we need to think about regulations? It's because the impact of a lot of models and a lot of products that are putting out there have an impact in society, and we don't know how that is going to impact society, and how can we make accountable a model for taking decisions. So I think that it's a good question in the sense that brings us to the reflection of when to apply certain models, what is the responsibility and the ethics behind it, and who is accountable for decisions that are being taken based on these technologies, right? So I will start by that. Let's talk about the impact and regulations.
Are these discussions going on as well? And I don't know, in WF or how, or what to put it?
Well, partially at least, for example, the work concerns, for example, usage of, for example, news, media, data inside the network, for example, in AI, which kind of data source you use, when what source is considered reliable, can be considered the right to use different sources. And for what concerns the question related to the stakeholders, I think that for us, what was crucial and really was a big turning point in our work was to have really a direct interaction during the development of, okay, we developed this, if you want, you can use it, like, actually, this is the coolest thing, go ahead. This was actually really not working with the stakeholders in this case, perhaps maybe country office, other UN agencies were not engaged, that were not solving or not serving their needs. So tweaking the needs, like our application for their needs and working together for us, I mean, as being for us that are not.
Well, yeah, I was thinking about along similar line. I mean, as long as the stakeholders are government organizations, I'm probably the wrong person to actually judge. But as soon as the stakeholders become kind of private entities, become kind of commercial entities, I think we can observe, for example, in the sustainability side. On the sustainability side, we can see that through the imposing kind of laws in terms of reporting of your CO2 footprint, that these laws have kind of started building up business incentives. They have kind of started creative incentives that you actually want to be part of it, that you actually want to be accurate, because otherwise you won't be able to actually take part in even in the economy because you cannot deliver. So I think in this space as well, if we can create commercial incentives by laws, by regulations to some extent, that people and stakeholders actually want to participate, want to get engaged. I think that's always a very strong, that's a strong point. And you can kind of create like bootstrap an ecosystem. As long as everything is for free, everyone just asks for solutions, nobody's willing to pay. Then also if you can engage the industry, the private sector, then also part of the solutions, like things that like look at SpaceX. I mean, because for decades it was NASA, ESA, and the Russians that like were shooting stuff up. Now all of a sudden it's like private sector that actually provides the entire access to space. It could be the same thing that in the long term, I mean, it's all about regulations in the end as well, and making sure that we still get quality from all the ECMW of the national organizations that is being maintained in the quality that we need for that for the people. But if you can create commercial incentives, that could be important.
So we're not really talking much about how information policy that's exactly the point of my talk, basically, is really trying to put it into a format that developers can kind of used to see, and they're used to parts. So you try and show people the quality of machine learning programs, the sort of acting of a translator between machine learning to ensure or to show the limitations.
Yeah, you want to
Yeah, that's a very good point, and that links as well with some of the comments. When you comment about taking into account the stakeholders when you are building out a model, at least, of course, I come from a different sector, right? From the application, something that is in research, but also humanitarian sector. And one of the controversial projects that people in my sector were talking about, it was one AI, machine learning model that was assigning how much money people should receive as beneficiaries from a UN agency based on a sort of indicators. And the model was very, very robust, very interesting, but it didn't took into consideration a lot of nuances that the people of the context. For example, I think, if I'm not wrong, I think that the project was in Jordan, and it's supposed to give economic incentives to people that were affected by displacement, by COVID, and so on and so forth, other crises. And the model was penalizing, for example, business owners, because they said, okay, you have a business, you are not someone in need. But actually, when you have a country, when you have a situation where a crisis is unfolding, you need to try also to prevent and sustain the economy. And these kind of models, for example, were implemented, and people like that were penalized and didn't receive any economic incentive or assistance. So therefore, this bring us back to always including the stakeholders and the end beneficiaries somehow in models when they are built, and also in the feedback of the models, because models are not just built in a moment, right? They can be also dynamic, something that can be built dynamically. And we always need to take into account who is going to be accountable for the decisions that are being taken in some models. And in some sectors, this accountability is more important than in others, based on the impact that the decisions can have on people's lives. Yeah.
I think this is a very good way to end it. It was good words of wisdom for us, I think. So I think we should probably thank all speakers again for really, really inspiring talks. So that was really good. And thanks to the audience for a lot of stamina. It's been actually a long day, but I hope it was interesting for you. Maybe one thing to say tomorrow, for those of you who stay for the summit as well, we have this event in the Discovery Zone. We went back and forth a bit with the organizers here. It's really meant to be primarily a networking event. It's at 3:20 in the Discovery Zone, wherever this is. and basically where people can get together and talk about climate in a broader sense and AI. But I think that's probably a good time to end, unless conveners have further words of wisdom.
Yeah, I mean, yeah, I think it was a great session. Couple of sessions. We enjoy, I mean, at least personally, I enjoy a lot of perspectives and a lot of problems going on, and a lot of methods to be applied and developed further. Yeah, I think that's perfect wrap up.
Perfect.
Good.
Thanks
Thank you.
everyone.
Thank you very much.
Again.